Hello. When you think about it, when you think about it, when you think about it, it's a sad story. I sing such a sad story.
Produced. It shattered a pulsation rhythm that had been beating steadily for nearly 2 centuries, and the star is still recovering. Then, in 2025, astronomers confirmed something hiding in the chaos, a secret companion star, buried so deep inside Betelgeuse's atmosphere that it took decades of suspicion and 8 years of Hubble observations to prove it was real.
Oh, cute.
Scientists
Making some money.
are not worried that Betelgeuse was
Yeah, it's just nice to make a bit of money. I've got £17 now on my account. That's quite good. That's quite good. I like it.
If you enjoy deep explorations of the universe and the science behind its strangest mysteries, it would mean a lot if you hit that like button and subscribe to the channel. Now, settle in and get yourself comfortable. Let's begin.
I love my fan. Sleep well.
Look up on any clear winter night and find the constellation Orion. It is one of the easiest patterns in the entire sky. 3 stars in a neat diagonal line form the belt. Below them hangs a faint smudge that marks the hunter's sword, and up at the top left corner, marking what ancient astronomers called the shoulder, burns a star that looks nothing like its neighbours. It glows deep orange-red, a colour so distinct that even casual observers notice it without being told what to look for. That star is Betelgeuse. And right now, it is one of the most intensely studied objects in all of modern astronomy. Not because it is rare, not because it is far away, but because over the past several years this star has done things that no one fully anticipated, things that forced scientists to rethink assumptions they had held for decades. To understand why Betelgeuse has the astronomical community so focused, you first need to understand what kind of star it is and why that matters. Betelgeuse is a red supergiant. That classification alone places it among the most extreme objects in stellar physics. A red supergiant is a star nearing the end of its life, a massive sun that has exhausted the hydrogen fuel in its core and begun burning heavier elements in successive shells. As this process unfolds, the star swells to extraordinary dimensions. Its outer layers expand outward, cooling as they go, which is why the surface glows red rather than white or blue. The star becomes enormous but diffuse, a bloated giant radiating energy across a surface area that dwarfs anything in our solar system. In the case of Betelgeuse, the numbers are staggering. Its radius stretches somewhere between 640 and 764 times the radius of our Sun. If you removed the Sun from the center of our solar system and dropped Betelgeuse in its place, the star's surface would swallow Mercury, Venus, Earth, and Mars entirely. It would push outward into the asteroid belt, consuming roughly 3.5 astronomical units of space in every direction. everything inside that boundary would exist within the body of the star itself. Our entire inner solar system would be interior real estate. That is how large Betelgeuse is. And yet, for all that size, the star is not particularly dense. Red supergiants are essentially vast, tenuous atmospheres surrounding a comparatively small and intensely hot core. The outer layers are so diffuse that in some regions the boundary between star and surrounding space becomes genuinely ambiguous. There is no sharp edge. The atmosphere fades gradually into the circumstellar environment, a haze of gas and dust that extends even farther into space. To understand why a star this enormous is also a star that is dying, you need to understand what is happening deep inside it, far below the bloated red surface that we observe from Earth. Every star is a balancing act between two opposing forces. Gravity pulls inward, trying to crush all the stellar material down into the smallest possible volume. Nuclear fusion pushes outward, generating the energy and pressure that resists gravitational collapse. For most of a star's life, these forces hold each other in check. Our Sun has been maintaining this balance for roughly 4.5 billion years, fusing hydrogen into helium in its core at a steady, sustainable pace. It will continue doing so for another 5 billion years or so. The fuel supply is enormous and the burn rate is moderate. Massive stars like Betelgeuse play by different rules. A star born with 15 or 20 times the mass of the Sun burns through its hydrogen fuel not in billions of years but in millions. The greater gravitational pressure in the core demands higher temperatures and more intense fusion to maintain equilibrium. The star burns hotter, brighter, and faster. By the time a star like Betelgeuse exhausts the hydrogen in its core, it has lived only about 10 million years, a blink compared to our Sun's lifespan. But running out of hydrogen is not the end. It is the beginning of the end, a slow cascade of increasingly desperate nuclear reactions that will ultimately seal the star's fate. When the hydrogen in the core is gone, the core contracts under gravity, heating up until it reaches temperatures high enough to ignite helium fusion. Helium atoms begin fusing into carbon and oxygen. This new energy source stabilizes the core temporarily, but helium burns faster than hydrogen did. The fuel runs out sooner. When the helium is exhausted, the core contracts again, heats up again, and begins fusing carbon into neon, magnesium, and sodium. Then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Each successive fuel source burns at higher temperatures and is consumed more quickly than the one before it. The result is a star with an internal structure that resembles an onion. Layers of different elements are nested inside one another, each one representing a different stage of nuclear burning. The outermost envelope is still mostly hydrogen and helium. Beneath that sits a shell where hydrogen is actively fusing. Below that, a helium-burning shell, then carbon, then neon, then oxygen, and at the very center, the innermost core, where the most advanced fusion reactions are taking place. Each layer is hotter, denser, and more compressed than the one above it. The deeper you go, the more extreme the conditions become. This layered structure is beautiful in its physics and terrifying in its implications, because there is a final stage in this sequence that the star cannot survive. When silicon fusion begins in the innermost core, it produces iron. And iron is the end of the line. Every fusion reaction up to iron releases energy, which is what keeps the star alive. But fusing iron does not release energy. It absorbs it. Iron is the ash of stellar nucleosynthesis, the final waste product that cannot be burned further for fuel. Once the core fills with iron, no amount of gravitational contraction can ignite a new energy source. The star has written a check that physics cannot cash. The core collapses in a fraction of a second, triggering a supernova explosion that blasts the outer layers into space at tens of thousands of kilometers per second. We do not know exactly which burning stage Betelgeuse currently occupies. The star is almost certainly past helium burning, and likely engaged in carbon fusion or beyond. But pinning down the precise stage requires knowing the star's mass, distance, an internal structure with a precision that current observations cannot provide. What we do know is that the clock is running. Each successive burning stage is shorter than the last. Hydrogen burning lasted millions of years. Helium burning lasted hundreds of thousands. Carbon burning lasts perhaps 1,000 years. Neon burning lasts roughly a year. Oxygen burning lasts months. And silicon burning, the final stage, lasts approximately 1 day. One single day of silicon fusion, and then the iron core forms, and the star dies. The acceleration is relentless. From the outside, nothing visible changes during these final stages. The surface of the red supergiant looks the same whether the core is burning carbon or oxygen. The death is invisible until the very end. Betelgeuse sits roughly 650 light-years from Earth, although that number carries more uncertainty than you might expect for such a bright, well-known star. Different measurement techniques have produced estimates ranging from around 400 to over 600 light-years. The European Space Agency's Gaia mission, which has revolutionized stellar distance measurements for billions of fainter stars, cannot produce reliable results for Betelgeuse because the star is simply too bright. It saturates the instruments. So one of the most famous stars in the sky still has a distance that astronomers cannot pin down with full confidence. That uncertainty ripples outward into everything else. Distance affects calculations of luminosity, radius, mass, and evolutionary stage. Change the distance, and you change the model. This is one of the first hints that Betelgeuse, despite centuries of observation, remains a more elusive target than its brilliance might suggest. What astronomers do know with confidence is that Betelgeuse is massive. Estimates of its mass range from slightly under 10 to a little over 20 times the mass of our Sun. That spread is wide, and it matters enormously because a star's mass determines its fate. Stars above roughly 8 solar masses are destined to end their lives in a core collapse supernova, one of the most violent events the universe can produce. Betelgeuse sits comfortably above that threshold. Its death, whenever it comes, will be explosive. The core will collapse in a fraction of a second. The outer layers will be blasted into space at tens of thousands of kilometers per second. And for a few weeks, the explosion will shine with the luminosity of billions of suns. That future is not in question. The only question is when. But before we get to the supernova question, there is something else about Betelgeuse that made it uniquely valuable to astronomers long before the recent drama. The star pulsates. Like a slow cosmic heartbeat, Betelgeuse expands and contracts in a rhythm that changes its brightness over time. This pulsation has been documented for nearly 200 years. Observers stretching back to the 1800s recorded systematic variations in the star's magnitude, and by the 20th century, astronomers had established a primary pulsation period of approximately 400 days. Every 400 days or so, Betelgeuse would brighten, then dim, then brighten again. The cycle was not perfectly regular, which is why the star is classified as a semi-regular variable rather than a strictly periodic one. But the pattern was consistent enough that it became one of the defining characteristics of the star. Astronomers used it to study internal structure, to model how energy moves through the convective envelope of a supergiant, and to test theories about how massive stars behave in their final evolutionary stages. There was also a secondary cycle, a longer oscillation, with a period of roughly 2,100 days, about 5 3/4 years. This cycle modulated the star's brightness on top of the primary pulsation, creating a complex pattern that researchers tracked for decades. The origin of this secondary period was unclear. Some scientists attributed it to giant convection cells churning across the star's surface. Others proposed different pulsation modes, interacting with one another. The secondary cycle remained a puzzle, but not an urgent one. Betelgeuse was behaving more or less as expected for a red supergiant. The star was interesting, well-studied, and scientifically productive. But it was not alarming. Then came the winter of 2019. In late October of that year, observers noticed that Betelgeuse was getting dimmer. This was not unusual in itself. The star dims and brightens regularly, but by December, the dimming had accelerated. Betelgeuse was fading faster and deeper than anyone had seen in the modern era of observation. By January 2020, the star had dropped to roughly 65% of its normal brightness. It continued falling. On February 9th, 2020, Betelgeuse reached a visual magnitude of approximately positive 1.64, the faintest it had been in nearly 2 centuries of recorded observation. A star that normally ranks among the 10 brightest in the night sky had slipped below the top 20. You could see the difference with your naked eyes. Orion looked lopsided, its bright shoulder suddenly dimmed to a shadow of its former self. The event became known as the Great Dimming, and it ignited a firestorm of public and scientific attention. Social media exploded with speculation. News headlines screamed that Betelgeuse might be about to explode. The word supernova trended worldwide. Amateur astronomers aimed their telescopes at Orion with a mixture of excitement and dread. Professional observatories redirected resources to monitor the star around the clock. Everyone wanted to know the same thing. Was this it? Was Betelgeuse dying right in front of us? The supernova hypothesis was never the most likely explanation, and most professional astronomers said so at the time. But the public fascination was understandable. Betelgeuse is the nearest red supergiant to Earth. It will go supernova eventually. And its brightness had just plummeted in a way that had no precedent in the historical record. The combination of proximity, inevitability, and unprecedented behavior created a perfect storm of attention. For a few months, Betelgeuse was the most watched star in the world. By March 2020, the star began to recover. Its brightness climbed back toward normal values, and by April it had returned to roughly its pre-dimming luminosity. The immediate crisis was over, but the scientific investigation was just beginning. What had caused such an extreme and rapid drop in brightness? The answer, when it finally came together, was stranger and more dramatic than most people expected. The forensic trail began not with the dimming itself, but with observations taken months earlier. Andrea Dupree and her team at the Center for Astrophysics at Harvard and Smithsonian had been monitoring Betelgeuse with the Hubble Space Telescope's ultraviolet capabilities long before the visible dimming attracted public attention. In the months leading up to the Great Dimming, Hubble detected something unusual. Ultraviolet spectral signatures revealed hot, dense material moving rapidly outward through Betelgeuse's atmosphere. Something energetic had happened deep inside the star and was now propagating through its outer layers at significant velocity. At the time, the significance of this observation was not fully appreciated. It was only later, when astronomers pieced together the full timeline, that the Hubble ultraviolet data emerged as the earliest forensic evidence of what was about to unfold. The hot material Hubble detected was the leading edge of a shockwave, the first visible sign of a convective eruption that had originated deep within the star's interior. That shockwave would take months to fully develop, to reach the photosphere, and to blast material into space. But Hubble caught the early tremors. Astronomers analyzing data from Hubble, the European Southern Observatory's very large telescope, and several other facilities pieced together a scenario that reads more like a disaster movie than a routine stellar observation. In early 2019, months before the visible dimming began, a massive convective plume had bubbled up from deep within Betelgeuse's interior. Convection is the process by which hot material rises and cooler material sinks, the same mechanism that drives weather patterns on Earth and boiling motion in a pot of water. Inside a red supergiant, convective cells operate on a mind-bending scale. This particular plume stretched more than 1 million miles across. It surged upward through the star's outer layers, generating shocks and pulsations as it went. Those shocks did something that had never been directly observed on any normal star before. They blasted a chunk of Betelgeuse's photosphere, the visible surface layer, clean off the star and into space. Astronomers called it a surface mass ejection, and the term barely captures the violence of the event. The ejected material weighed roughly several times the mass of our moon. It was launched outward at significant velocity, tearing away from the star's gravitational grip and expanding into the surrounding space. As this material moved away from Betelgeuse and cooled, it condensed into an enormous cloud of dust particles. That dust cloud, now drifting between Betelgeuse and Earth, blocked a substantial fraction of the star's light from reaching our telescopes. The Great Dimming was not a signal from the star's core. It was not a prelude to supernova. It was the shadow of a wound. Our sun produces something superficially similar, called a coronal mass ejection, where the solar corona throws off bursts of plasma and magnetic field into space. These events can disrupt satellite communications and create beautiful auroral displays on Earth. But the surface mass ejection from Betelgeuse was on an entirely different scale. It blasted off roughly 400 billion times as much mass as a typical solar coronal mass ejection. The comparison is almost absurd. It is like comparing a sneeze to a volcanic eruption. The two phenomena may share some surface-level resemblance, but they operate in fundamentally different regimes of energy and mass. The Very Large Telescope Sphere instrument captured direct images of Betelgeuse's surface during the dimming event, and they were haunting. The star's southern hemisphere had gone visibly dark. What had been a roughly uniform disk of glowing stellar surface now showed a dramatic asymmetry, with one entire quadrant substantially dimmer than the rest. Scientists were literally watching the aftermath of a stellar injury in real time, seeing the wound on the star's face where the photosphere had been torn away. But the Great Dimming itself, as dramatic as it was, turned out to be only the most visible symptom of something deeper. The surface mass ejection did not just create a temporary dust cloud, it fundamentally disrupted the internal mechanics of the star. Remember the 400-day pulsation cycle, that steady heartbeat that astronomers had measured for nearly 2 centuries? After the ejection event, it vanished. The pulsation simply stopped. For more than 2 years following the Great Dimming, Betelgeuse showed no evidence of its familiar 400-day rhythm in either its brightness variations or its radial velocity measurements. 2 centuries of reliable, documented pulsation, gone. Andrea Dupree described the aftermath in vivid terms. The star's interior convection cells, the massive currents of rising and sinking material that normally drive the pulsation, appeared to be sloshing around chaotically. She compared it to the vibrations of an unbalanced washing machine tub. The outer layers of the atmosphere seemed to be recovering, but the surface itself was still bouncing and oscillating erratically. She used another analogy that captured the unsettled state perfectly. The photosphere was rebuilding itself, but it was jiggling like a plate of gelatin on a table, stable from a distance, wobbly up close. This disruption was unprecedented, not just for Betelgeuse, but for any star of this type. Astronomers had theoretical models for how red supergiants pulsate, how convective energy drives rhythmic expansion and contraction, and how those cycles relate to the star's internal structure. But none of those models had accounted for what happens when a star literally ejects a piece of its own surface into space. The event rewrote the textbook on red supergiant behavior in real time. Eventually, signs of recovery appeared. The pulsation began to rebuild, but initially at twice the frequency of the original cycle, a transient response that some researchers compared to plucking a string on an instrument and hearing an overtone before the fundamental note reasserts itself. The expectation was that over time, the familiar 400-day period would eventually return. But the recovery was slow, and the star's behavior remained unsettled and difficult to predict. What made this significant was the sheer amount of mass involved. The material ejected during the surface mass ejection represented a significant fraction of Betelgeuse's total annual mass loss rate. Red supergiants shed mass continuously through stellar winds, a slow but steady outflow of gas that carries material away from the star over millions of years. This mass loss matters because it determines how much material the star retains when it finally explodes. A star that loses more mass before the supernova produces a different kind of explosion, and leaves behind a different kind of remnant, either a neutron star or a black hole, depending on how much core mass remains. The surface mass ejection demonstrated that episodic, violent mass loss events could contribute an amount comparable to the steady stellar wind in a single explosive episode. This was not just a curiosity about Betelgeuse. It was a revelation about how red supergiants in general might shed their mass in the final stages before supernova. If these events happen periodically, if convective plumes routinely build up enough energy to blast photospheric material into space, then the mass loss histories of red supergiants might be far more dynamic and irregular than previous models assumed. Scientists had never directly witnessed a surface mass ejection from a normal star before. Betelgeuse was the first, and the only reason they caught it was because Betelgeuse happens to be enormous and close enough that its surface can be directly resolved by modern instruments. If the same event had occurred on a more distant red supergiant, the dimming would have been noticed, but the surface detail, the asymmetric darkening, the spectroscopic signatures of outflowing material, all of that would have been invisible. Betelgeuse offered a front-row seat to a phenomenon that might be common across the universe, but had simply never been observed in this kind of detail. By 2022, when the full analysis of the surface mass ejection was published, the scientific picture was clearer but no less remarkable. Betelgeuse had experienced the most violent mass loss event ever directly documented on a normal star. The blast had disrupted internal dynamics that had been stable for at least 2 centuries. The star was slowly recovering, but its behavior remained unusual and difficult to model cleanly, and the implications extended far beyond one star in Orion. The event opened a new window into the late-stage evolution of massive stars, a phase that remains one of the least understood chapters in stellar physics. But here is what kept astronomers watching long after the Great Dimming faded from public attention. The surface mass ejection explained the dramatic dimming event. It explained the dust cloud, the asymmetric darkening, the disrupted pulsation. It was a satisfying answer to the most visible question, but it did not explain everything. There was still that mysterious secondary cycle, the 2,100-day brightness oscillation that had been documented for decades before the Great Dimming ever occurred. The surface mass ejection did not account for it. Internal pulsation models did not fully account for it either. Something else was going on with Betelgeuse, something the ejection event had overshadowed but not erased. And in the years that followed, as astronomers continued monitoring the star with Hubble, with ground-based spectroscopes, with every instrument they could bring to bear, they found evidence of something hiding in the data, something small, something that had been there all along, orbiting silently inside the chaos of the supergiant's atmosphere, a companion, and its discovery would change the story of Betelgeuse all over again. The Great Dimming grabbed headlines. The surface mass ejection rewrote textbooks, but even as Betelgeuse was recovering from its most dramatic episode in recorded history, a quieter mystery had been sitting in the data for decades, patiently waiting for someone to solve it. And when the answer finally arrived, it did not come in the form of an explosion, or a dust cloud, or a sudden darkening visible to the naked eye. It came in the form of a tiny, faint point of light that had been hiding in plain sight, buried inside the atmosphere of a star more than 1 billion miles wide. To understand why this discovery mattered so much, you need to go back to the brightness patterns that astronomers had been tracking long before the winter of 2019. Betelgeuse has 2 well-documented cycles of variability. The first is the roughly 400-day pulsation that drives the star's primary brightness changes. That cycle is understood reasonably well. It arises from the Kappa mechanism, a process in which layers of the star's atmosphere become opaque to radiation, trapping heat, expanding outward, then becoming transparent again, releasing the energy, and contracting. This rhythmic breathing is common among pulsating stars, and for Betelgeuse, it had been measured reliably since the 1800s. It is the star's heartbeat, slow and steady, roughly 1 full cycle per year and a month. But underneath that primary rhythm, there was always a second signal, a longer, subtler oscillation with a period of approximately 2,100 days, roughly 5¾ to 6 Earth years. This secondary cycle modulated Betelgeuse's overall brightness on top of the faster pulsation, creating a more complex light curve that required careful long-term monitoring to detect. Astronomers had documented this longer cycle for decades, but its origin remained stubbornly unclear. Several explanations were proposed over the years. One popular idea attributed the secondary period to giant convection cells on Betelgeuse's surface. Red supergiants do not have millions of small convective granules like the Sun. Instead, they have a small number of enormous convective plumes, each one spanning a significant fraction of the star's diameter. These giant cells could, in theory, produce brightness variations as they rise and fall on timescales of several years. The problem was that simulations of convective behavior did not cleanly reproduce the observed periodicity. Convection is inherently chaotic. It produces irregular fluctuations, not the relatively consistent cycle that the observations showed. Another explanation proposed that the secondary period was a different pulsation mode, perhaps a higher-order overtone interacting with the fundamental 400-day mode. This was mathematically plausible but difficult to confirm observationally. The interactions between multiple pulsation modes in a star as complex and poorly constrained as Betelgeuse are notoriously hard to model. Without a clear theoretical prediction that matched the data, this idea remained speculative. A third hypothesis, quieter and less prominent for years, proposed something entirely different. Maybe the secondary cycle was not intrinsic to Betelgeuse at all. Maybe it was caused by something external, specifically by a companion star orbiting the red supergiant with a period that matched the observed brightness modulation. This idea had floated around the edges of Betelgeuse research for a long time, but it faced an obvious challenge. Nobody had ever seen a companion, and given how bright and enormous Betelgeuse is, detecting a small companion star orbiting close to it would be extraordinarily difficult. The glare from the supergiant would overwhelm any faint nearby source. It would be like trying to spot a firefly hovering next to a searchlight. Still, the companion hypothesis had certain advantages. It was clean. A small star orbiting Betelgeuse every 6 years would naturally produce periodic effects on the supergiant's atmosphere. As the companion moved through its orbit, it could stir up gas, modulate dust production, and create observable changes in brightness and spectral features. The period would be regular, tied to the orbital mechanics rather than to the messy physics of convection. And it would explain why the secondary cycle persisted so consistently over decades, while convective models struggled to produce that kind of regularity. The hypothesis gained serious momentum in 2024, when 2 independent research groups published studies that both pointed toward the same conclusion. One team analyzed Betelgeuse's radial velocity measurements, the subtle Doppler shifts in the star's spectral lines caused by the gravitational tug of an orbiting body. Their calculations suggested that a companion with roughly 1.17 solar masses, orbiting at a distance of about 8.5 astronomical units, could account for the observed 2,100-day periodicity, the fluctuating radial velocity measurements, and even certain characteristics of Betelgeuse's relatively moderate radius and low variation in effective temperature. The second team took a different approach, examining brightness records spanning more than a century. They independently arrived at a similar conclusion, proposing a close-in stellar companion with an orbital period of approximately 5.78 years, possibly less massive and less luminous than our Sun. Neither study claimed a confirmed detection. The companion remained hypothetical, inferred from indirect evidence rather than directly observed. But the convergence of 2 independent analyses pointing toward the same answer was compelling. The astronomical community began treating the companion hypothesis as a serious leading candidate rather than a fringe idea. Then came May 2025. A team studying Betelgeuse in ultraviolet and X-ray wavelengths published results that narrowed the possibilities significantly. Their observations effectively ruled out the chance that the companion was a compact object, meaning it was not a white dwarf and not a neutron star. Those types of stellar remnants produce characteristic X-ray signatures that were simply not present in the data. Whatever was orbiting Betelgeuse, it appeared to be a normal, low-mass, relatively young star. The team estimated that the companion's mass was likely less than 1.5 solar masses, and possibly less than 1 solar mass. This was consistent with the earlier predictions, and further tightened the theoretical picture, but direct visual detection remained elusive. The companion was still, at that point, an invisible gravitational ghost inferred from its effects on the supergiant. The breakthrough arrived in July 2025, and it came from an instrument specifically designed to see things that are very close to very bright objects. A team led by Steve Howell at NASA's Ames Research Center used the Alupeke instrument on the Gemini North Telescope in Hawaii. Alupeke is a speckle imaging camera, a device that takes extremely rapid exposures and uses computational techniques to cut through the blurring caused by Earth's atmosphere. It is purpose-built for resolving fine details near bright stars, exactly the kind of observation needed to spot a faint companion hiding in Betelgeuse's glare. The team employed a clever observational strategy built on a specific prediction. If a companion existed with the orbital parameters proposed by the 2024 studies, then its position relative to Betelgeuse as seen from Earth would be predictable. At certain points in its orbit, the companion would be directly behind or in front of the supergiant from our line of sight, making it undetectable. At other points, it would swing out to its maximum angular separation, the moment when it would be easiest to spot against the overwhelming brightness of its giant host. Howell's team compared 2 sets of Alupeke observations. The first was taken in 2020, during the Great Dimming event. At that time, the companion was predicted to be almost directly aligned with Betelgeuse along our line of sight. If the companion existed, it should have been invisible in those images, and it was. No companion appeared. The second set of observations was taken in December 2024, just 3 days after the predicted moment of greatest elongation, the point in the orbit when the companion would be at its widest apparent separation from the supergiant. The team processed the data, applied their speckle imaging techniques, and looked for any faint source near the expected position. There it was, a tiny point of light, roughly 6 magnitudes fainter than Betelgeuse, positioned at an angular separation of 52 milliarcseconds, east of north. The location matched the dynamical predictions with remarkable precision. It was exactly where the models said a companion should be, at exactly the time the models said it should be visible. The detection was not overwhelming in statistical significance. The team reported it at roughly 1.5 sigma, which in normal circumstances would be considered tentative. But the alignment with prior predictions was striking. The companion appeared at the right position, the right time, the right brightness, and the right angular separation. Each of those independent agreements added weight to the detection beyond what the raw signal-to-noise ratio alone might suggest. The team characterized the companion as likely being about 1.6 solar masses, larger than some earlier estimates, but consistent with a young, hot, pre-main sequence star of spectral type F, meaning it would glow with a blue-white color, utterly different from the deep red of its supergiant host. The companion was given a name. The discoverers proposed Siwaha, an Arabic word meaning her bracelet. The choice was deliberate and poetic. Betelgeuse's own name derives from an Arabic phrase, often translated as the hand of Al-Jaza, a reference to a female figure in Arabic astronomical tradition, a bracelet on the hand. The name was officially recognized by the International Astronomical Union's Working Group on Star Names in September 2025. What had been a hypothesis, then a candidate, now had an identity. But the discovery of Siwaha was not the end of the story. It was, in many ways, just the beginning. The detection showed that the companion existed. The next question was whether it was actually doing what theorists had predicted it was doing. Was Siwaha really interacting with Betelgeuse's atmosphere? Was it truly responsible for the mysterious secondary brightness cycle? Was it physically shaping the behavior of the supergiant? Answering those questions required a different kind of observation, not just spotting the companion, but tracking its influence over time. That answer came in January 2026, and it came from one of the most storied instruments in the history of astronomy. Andrea Dupree, the same Harvard astronomer who had led much of the surface mass ejection research, presented new results at the 247th meeting of the American Astronomical Society in Phoenix. Her team had combined nearly 8 years of observations from the Hubble Space Telescope with data from ground-based observatories at the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory. What they found was not just evidence that Siwaha existed. It was direct evidence that Siwaha was altering the physical environment around Betelgeuse in detectable, measurable ways. The key discovery was a wake. As Siwaha orbits Betelgeuse, it does not simply circle at a safe distance through empty space. It plunges through the supergiant's vast, extended outer atmosphere. Betelgeuse's atmosphere stretches far beyond what you might think of as the star's surface, an enormous envelope of gas that reaches outward for astronomical units. Siwaha's orbit, at roughly 4 astronomical units from Betelgeuse's center, places it squarely inside this extended atmosphere. As the companion moves through this tenuous material, it carves a path. Gas is disrupted, compressed, and stirred in its passage. A trail of denser material forms behind it, exactly like the wake left by a boat moving through water. Dupree's team detected this wake through careful spectroscopic analysis. They tracked changes in the specific wavelengths of light produced by different elements in Betelgeuse's atmosphere, and measured shifts in the speed and direction of gas flows in the outer layers. These changes showed a repeating pattern that aligned perfectly with the predicted orbital period of approximately 2,100 days. Every time Siwaha crossed in front of Betelgeuse, relative to our line of sight, the wake became detectable in the spectroscopic data. The trail of denser gas appeared, expanded outward, and gradually dissipated before the next orbital passage brought a fresh disturbance. The detection was elegant and decisive. It transformed Siwaha from a probable companion seen in a single tentative image into a confirmed physical actor in the Betelgeuse system. The companion was not just there, it was doing something. It was churning up the atmosphere of the supergiant with every orbit, leaving behind a swirling trail of disrupted material that Hubble and ground-based telescopes could track across years of patient observation. Dupree described the effect vividly. The companion creates a ripple effect in Betelgeuse's atmosphere that astronomers can actually see in the data. For the first time, they were seeing direct signs of the wake, confirming that Betelgeuse really does have a hidden companion shaping its appearance and behavior. The discovery resolved one of the most enduring puzzles surrounding the star, and that puzzle was the secondary brightness cycle. With the wake confirmed, the explanation became straightforward. Every 6 years, as Siwaha completes an orbit through Betelgeuse's outer atmosphere, the dense trail of gas it leaves behind absorbs and scatters some of the supergiant's light. This creates periodic changes in the brightness reaching Earth, changes that match the long-observed 2,100-day cycle. The secondary period was not caused by convective cells. It was not a second pulsation mode. It was the fingerprint of a tiny companion star dragging a curtain of disrupted gas through a giant's atmosphere once every 6 years. This realization fundamentally changed how astronomers interpreted Betelgeuse's recent history. Consider what this means for the Great Dimming. The surface mass ejection remains the primary explanation for the dramatic brightness drop of 2019 through 2020. The convective plume, the photospheric ejection, the dust cloud, all of that still holds, but the timing now looks different. The Great Dimming occurred near a minimum in the secondary cycle, meaning Siwaha's orbital effects may have been contributing additional variability on top of the intrinsic pulsation and the surface mass ejection. The coincidence of the primary 400-day pulsation minimum with the secondary cycle minimum may have amplified the dimming event beyond what either mechanism alone would have produced. Some researchers had already noted this suspicious alignment and speculated about it. The companion discovery provided the missing piece. The deepest dimming in nearly 2 centuries may have been partly a matter of unfortunate timing. multiple dimming mechanisms stacking on top of each other simultaneously. The companion also provided new context for Betelgeuse's mass loss behavior. Red supergiants shed material through stellar winds, and Betelgeuse's circumstellar environment is known to be complex, with multiple shells of expelled gas and dust detected at various distances from the star. Siwaha's repeated passage through the outer atmosphere stirs up material that might otherwise remain relatively quiescent. The companion could be enhancing dust formation, modulating the density of the circumstellar environment, and contributing to the episodic mass loss that characterizes Betelgeuse's late evolutionary stage. In other words, the companion is not just passively orbiting, it is actively participating in the processes that govern how the supergiant sheds its outer layers in preparation for its eventual death. The nature of Siwaha itself added another layer of fascination, based on the combined evidence from speckle imaging, spectroscopy, ultraviolet and X-ray observations. The companion appears to be a low-mass star, roughly 1.5 times the mass of our Sun. It is likely a young pre-main sequence star, meaning it has not yet fully settled into the stable hydrogen-burning phase that our Sun occupies. This is consistent with a star that formed alongside Betelgeuse roughly 10 million years ago, from the same molecular cloud, born as a sibling rather than a captured interloper. But while Betelgeuse, with its much greater mass, raced through its nuclear fuel and ballooned into a red supergiant, Siwaha evolved far more slowly. A star of 1.5 solar masses has a main sequence lifetime measured in billions of years. It is still in its stellar youth while its massive companion is approaching death. The orbital dynamics paint a dramatic picture of the future. Tidal interactions between the two stars are expected to gradually pull Siwaha inward. As Betelgeuse continues to expand and shed mass, the companion's orbit will decay. Current estimates suggest that Siwaha will be engulfed by Betelgeuse within approximately 10,000 years, swallowed whole by the supergiant's bloated atmosphere. Long before Betelgeuse goes supernova, its companion will have been consumed. The bracelet will be absorbed into the hand, but that future drama is secondary to what the companion means for the present. The confirmation of Siwaha provided astronomers with something they desperately needed: a concrete physical mechanism to explain behavior that had previously been attributed to vague internal processes. Before the companion was confirmed, every unusual brightness change, every spectroscopic anomaly, every unexpected shift in gas velocity had to be explained through the messy, poorly understood physics of convective envelopes and pulsation mode interactions. Now, a significant fraction of those variations could be attributed to a simple and well-understood mechanism: a small star orbiting inside a big star's atmosphere, stirring things up on a predictable schedule. This does not mean Betelgeuse is suddenly a solved problem. Far from it. The companion explains the secondary brightness cycle and provides context for some of the star's more puzzling atmospheric behavior. But it does not explain the surface mass ejection. It does not explain why the 400-day pulsation was disrupted for more than 2 years. It does not resolve the uncertainties in Betelgeuse's distance, mass, or evolutionary stage. And it introduces new questions of its own. How exactly does the companion interact with the convective plumes that drive the primary pulsation? Does its orbital passage trigger or suppress mass loss events? Could the interplay between Siwaha's wake and Betelgeuse's intrinsic variability produce effects that are more than the simple sum of 2 separate mechanisms? These questions matter because Betelgeuse is not just any star. It is the closest red supergiant to Earth, and one of the most scientifically accessible massive stars in the final stages of evolution. Every observation of Betelgeuse contributes to our broader understanding of how massive stars evolve, shed mass, and eventually explode. The companion adds a new variable to an already complicated system, making the star simultaneously better understood and more challenging to model. The October 2025 findings from Carnegie Mellon University added yet another wrinkle. That team's observations suggested the companion star was not quite what earlier predictions had expected. Rather than a tiny, faint object at the end of its life, Siwaha appeared to be a somewhat larger and more luminous young star. This did not contradict the detection, but it refined the picture, hinting that the Betelgeuse system is more complex than even the companion hypothesis initially suggested. The properties of Siwaha affect how strongly it interacts with Betelgeuse's atmosphere, how much material it stirs up, and how detectable its effects are from Earth. Getting those properties right matters for every model built on the companion's influence. The next major observing opportunity will come in November 2027, when Siwaha is predicted to reach its widest apparent separation from Betelgeuse as seen from Earth. At that point, astronomers will have the best chance to study the companion with direct imaging techniques, potentially with instruments more sensitive than those used in the 2024 detection. Multiple observatories will train their instruments on the system, seeking to refine Siwaha's mass, temperature, luminosity, and orbital parameters. Each measurement will tighten the constraints on theoretical models and clarify how the companion shapes the supergiant's behavior. But even before 2027 arrives, the companion discovery has already reshaped the scientific narrative around Betelgeuse. For years, every unusual behavior from this star was filtered through a single dramatic question: is it about to explode? The great dimming fed that narrative. The brightness fluctuations fed it. The disrupted pulsation fed it. Media coverage amplified the supernova angle relentlessly, even when most scientists cautioned against it. The confirmation of Siwaha provides a powerful counterweight to that narrative. The long, mysterious secondary cycle was not a countdown to destruction. It was the signature of a companion star, a gravitational dance that has been going on for millions of years and will continue for thousands more. This does not eliminate the supernova question. Betelgeuse will still explode, that is not in doubt. But the companion discovery demonstrates that much of the behavior that excited public speculation and fueled dramatic headlines can be attributed to a process that is fascinating but not catastrophic. A small star carving a wake through a giant's atmosphere is remarkable, but it is not a death knell. What it is, though, is a reminder that even the most closely watched stars in the sky can harbor secrets that take decades of observation and multiple generations of instruments to uncover. Astronomers have been staring at Betelgeuse for centuries. They have measured its brightness, analyzed its spectrum, modeled its pulsation, and mapped its circumstellar environment. Through all of that, a companion star was orbiting inside the atmosphere, invisible, influencing the data, shaping the observations, and evading detection until the right combination of predictions, instruments, and patience finally brought it into view. Siwaha was there the whole time. And now that scientists know what to look for, Betelgeuse's story has become richer, more complex, and far more interesting than the simple question of when it will blow up. But as we are about to see, even with the companion confirmed, Betelgeuse continues to challenge clean explanation. The star is better understood than it was 5 years ago. It is not yet understood well enough. It would be satisfying to end the story here. A massive star dimmed dramatically. Scientists figured out that a surface mass ejection caused it, and then they discovered a hidden companion that explained the long-standing secondary brightness cycle. Mystery solved, case closed. Move on to the next star. But Betelgeuse does not cooperate with tidy narratives. The companion discovery and the surface mass ejection analysis answered specific questions with remarkable clarity. They resolved puzzles that had persisted for years and even decades. And yet, step back from those individual answers and look at the full picture of what scientists actually know about this star. And what emerges is not a portrait of a well-understood object. What emerges is a portrait of a star that remains, in fundamental ways, deeply and stubbornly uncertain. The more astronomers learn about Betelgeuse, the more they realize how much they still cannot pin down. And that persistent uncertainty is, in many ways, the real reason scientists are worried right now. Start with the most basic question you can ask about any star. How far away is it? For most bright stars in the night sky, this question was settled decades ago. Modern instruments, particularly the European Space Agency's Hipparcos satellite in the 1990s and the Gaia mission beginning in 2013, have measured stellar distances with extraordinary precision. Gaia alone has catalogued parallax measurements for nearly 2 billion stars, nailing down their positions to fractions of a milliarc second. For the vast majority of nearby stars, the distance question is closed. The numbers are in the database, verified and reliable. Betelgeuse is not in that database, not with useful precision anyway. Gaia's instruments are designed for stars of moderate brightness. Betelgeuse is far too luminous. It saturates the detectors, overwhelming the sensitive optics that work beautifully on fainter targets. The result is that Gaia cannot produce a reliable parallax measurement for one of the most scientifically important stars in the sky. Betelgeuse was excluded from both Gaia Data Release 2 in 2018 and Data Release 3 in 2022. The most precise parallax measurement still available comes from the older Hipparcos mission, which placed Betelgeuse at a distance of roughly 643 light-years with a substantial margin of error. Other techniques have produced different estimates. Some studies, incorporating stellar modeling and evolutionary considerations, have suggested distances as low as roughly 400 light-years. Others cluster around 500 to 550. The commonly cited figure of approximately 650 light-years represents a reasonable middle ground, but the honest range spans from around 400 to over 600 light-years. The context, that is a spread of more than 50%. Imagine being told that the somewhere the uncertainty would change the Betelgeuse, the uncertainty changes everything. Distance is not just a number in stellar astronomy. It's the foundation on which virtually every other physical property is calculated. The luminosity of a star, its total energy output, is derived from its apparent brightness combined with its distance. Get the distance wrong, and the luminosity is wrong. Luminosity, in turn, feeds directly into calculations of the star's radius, its mass, its surface temperature, and its evolutionary stage. A Betelgeuse at 400 light-years is a significantly different physical object than a Betelgeuse at 650. It would be less luminous, probably less massive, potentially at a different stage in its nuclear burning sequence. The models built on that distance would predict a different remaining lifetime, a different massive star, a different supernova outcome. This is not a hypothetical concern. A 2020 study led by Meredith Joyce at the Australian National University used the timing of Betelgeuse's pulsation modes to constrain its physical properties and concluded that the star might be closer and smaller than traditional estimates suggested. Their analysis favoured a distance of roughly 530 light-years, a current mass of around 16.5 to 19 solar masses, and a radius of about 764 times the Sun's radius. Other groups, using different methods and assumptions, have arrived at different distances. The lack of consensus on something as fundamental as distance means that every model of Betelgeuse is built on a foundation that can shift. Mass is equally problematic. The mass estimates we mentioned earlier, spanning 10 to over 20 solar masses, represent more than just imprecision. That is not a minor discrepancy. A star of 10 solar masses follows a substantially different evolutionary path than a star of 20. The mass determines the sequence and duration of nuclear burning stages in the core. It determines how much material remains in the core when fusion finally ceases. It determines whether the remnant left behind after the supernova is a neutron star or a black hole. And it determines the approximate timeline of the explosion itself. The more massive faster and has a shorter remaining lifetime. The less massive one will be. The difference between these scenarios is thousands of years, which might sound academic until you realise that it also changes the probability of the supernova occurring during a particular stretch of human history. The mass uncertainty is not just a matter of imprecise measurement. it reflects genuine physical complexity. Betelgeuse has been losing mass throughout its red supergiant phase, shedding material through stellar winds and episodic ejection events like the surface mass ejection. The rate at which this mass loss occurs affects the star's current mass, its remaining lifetime, and the nature of its eventual explosion. But mass loss rates for red supergiants are themselves poorly constrained. Different observational methods produce different estimates, and theoretical models of mass loss in these late evolutionary stages carry significant uncertainties. The surface mass ejection demonstrated that episodic events can eject as much material in a single blast as the steady stellar wind produces over an entire year. If such events occur regularly, the cumulative mass loss over thousands of years could be substantially higher than models based only on steady wind measurements would suggest. This connects to a deeper problem that extends well beyond Betelgeuse. Red supergiants in general are among the most difficult stars to model accurately. They are enormous, with extended, tenuous atmospheres that defy simple physical descriptions. Their surfaces are not smooth and well-defined like the Sun's photosphere. Instead, they are dominated by a small number of giant convective cells, massive upwellings and downwellings of hot and cool material that create a roiling, constantly shifting surface. Direct images of Betelgeuse's surface, captured by instruments like the Sphere camera on the Very Large Telescope, show this dramatically. The star's disk is not a uniform circle. It is mottled, asymmetric, with bright and dark patches that change over time as convective cells rise, evolve, and sink. These convective cells are not just surface features. They extend deep into the star's interior, connecting the outer atmosphere to the nuclear burning shells below. Modeling them accurately requires three-dimensional hydrodynamic simulations that push the limits of current computational resources. The challenge is that convection in a red supergiant does not prove like convection in smaller stars. In the Sun, millions of small convective granules churn across the surface, each one perhaps 1,000 kilometers across. The overall effect is relatively smooth and predictable when averaged over large areas. In Betelgeuse, the convective cells are so large that only a handful fit on the visible surface at any given time. Each cell spans a substantial fraction of the star's diameter. This means that individual convective events can have global consequences. A single massive plume rising from the interior can brighten an entire hemisphere, alter the spectral signature of the whole star, and even trigger mass ejection events. The surface mass ejection of 2019 was likely caused by exactly such a plume, a convective upwelling more than 1 million miles across that produced shocks powerful enough to blast off a piece of the photosphere. This inherent turbulence creates a problem for astronomers trying to separate different physical effects. When Betelgeuse's brightness changes, is the cause a pulsation cycle, a convective event, the passage of Siwaha through the atmosphere, or some combination of all three? The answer, frustratingly often, is that all of these processes are happening simultaneously, and they interact in ways that are not yet fully understood. The companion's wake stirs up gas that may interact with convective fluids. Pulsation-driven expansion and contraction changes the density of the atmospheric material through which Siwaha moves. Convective events can trigger mass loss episodes that alter the circumstellar dust environment, which in turn affects how much light reaches Earth. The system is coupled and dynamic, with multiple processes feeding back on each other in the tangled processes of inevitable separation. This is why the companion discovery, as significant as it is, does not simply solve Betelgeuse. Siwaha explains the secondary brightness cycle beautifully, but the star's behavior is not just the sum of two neat periodic signals. It is a complex nonlinear interaction of pulsation, convection, mass loss, and orbital dynamics, all occurring inside a star whose basic parameters remain uncertain. Scientists can explain specific phenomena, the secondary cycle, great dimming, the disrupted pulsation, but they cannot yet produce a single unified model that consistently reproduces everything Betelgeuse does over time. The aftermath of the surface mass ejection illustrates this difficulty. The disruption of the 400-day pulsation cycle was one of the most striking consequences of the 2019 event. For more than 2 years, the familiar rhythm vanished from the data. When signs of recovery began to appear, the oscillations initially showed up at twice the original frequency, a transient response that researchers expected would eventually settle back into the fundamental mode. But the recovery was not smooth. Betelgeuse's brightness and radial velocity measurements showed irregular fluctuations that did not fit neatly into any single pulsation model. The star was rebuilding its internal rhythm, but the process was messy and protracted. Then, in late 2023, Betelgeuse did something unexpected again, but this time in the opposite direction. The star surged in brightness, climbing to approximately magnitude 0, significantly brighter than its recent average. For a brief period, it rose to become roughly the 7th brightest star in the entire night sky, noticeably more luminous than it had been in years. If the Great Dimming represented an unprecedented drop, the 2023 brightening represented an unusual spike. And it arrived at a time when the star's behavior was supposed to be settling back toward normalcy after the surface mass ejection. The brightening reignited public speculation about an imminent supernova, just as the Great Dimming had 3 years earlier. Once again, headlines appeared suggesting Betelgeuse might be about to explode. Once again, most professional astronomers cautioned that brightness variations, even unusual ones, are not reliable indicators of core collapse. But the episode was scientifically significant, regardless of whether it had anything to do with the star's eventual death. It demonstrated that Betelgeuse was still producing behavior that fell outside the expected range. The pulsation was supposed to be recovering. The star was supposed to be settling down. Instead, it brightened to a level that had not been seen in recent observing history. The cause of the 2023 brightening remains debated. Some researchers attributed it to a particularly vigorous convective upwelling that temporarily increased the photospheric temperature across a large fraction of the visible surface. Others suggested it might reflect the ongoing recovery from the surface mass ejection, with the star's pulsation overshooting its equilibrium brightness as the internal oscillations re-establish themselves. The companion adds yet another possibility. If Siwaha's orbital position at that time placed its atmospheric wake away from the line of sight between Betelgeuse and Earth, the absence of the wake's dimming effect could allow the star to appear brighter than during phases when the wake partially obscures its light. Disentangling these possibilities requires precisely the kind of multivariable modeling that remains beyond current capabilities. The 2023 brightening joined the growing list of Betelgeuse events that can be described but not yet definitively explained. Some of the pulsation irregularity might also be attributable to the companion. Siwaha's orbital passage disrupts the atmospheric material through which pulsation waves propagate. If the pulsation is trying to re-establish itself while the companion is simultaneously stirring up the outer layers, the two effects could interfere with each other, producing the kind of erratic behavior that observers documented. But this hypothesis, while plausible, has not been rigorously tested against the data. Separating Siwaha's influence from the ongoing pulsation recovery requires disentangling two periodic signals of different timescales that are both embedded in a noisy background of convective variability. It is a signal processing challenge of considerable difficulty. The circumstellar environment adds yet another layer of complexity. Betelgeuse is surrounded by multiple shells and arcs of expelled material at various distances from the star. These structures, detected through infrared and radio observations, record the history of mass loss over thousands of years. Some of the material was ejected by stellar winds. Some may have been produced by past surface mass ejection events, assuming the 2019 event was not a unique occurrence. And some may have been influenced by Siwaha's orbital dynamics, with the companion stirring up material that was then expelled more easily into the circumstellar environment. Understanding this environment matters because it affects observations of the star itself. Dust between Betelgeuse and Earth dims and reddens the star's light. The The amount and distribution of circumstellar dust changes over time as new material is ejected and older material disperses. This means that the apparent brightness of Betelgeuse is not just a function of what the star itself is doing. It is also a function of what the material around the star is doing. Separating intrinsic variability from circumstellar effects requires multi-wavelength observations that probe different layers of the system. Optical light for the photosphere, ultraviolet for the chromosphere, infrared for the dust, and radio for the extended gas environment. Modern observatories can do this, and they have. But even with data spanning the electromagnetic spectrum from multiple world-class facilities, the picture remains incomplete. Each wavelength reveals a different aspect of the Betelgeuse system, and fitting all those aspects into a single coherent model is a problem that has occupied researchers for decades without a fully satisfying solution. This might seem like a failure of science, but it is actually the opposite. Betelgeuse's persistent complexity is scientifically invaluable, precisely because it exposes the limitations of current models. Red supergiants are critically important objects in astrophysics. They are the immediate progenitors of core collapse supernovae. The explosions that produce neutron stars and black holes forge heavy elements like iron, gold, and platinum, and inject energy and enriched material into the interstellar medium. Every atom of carbon in your body, every atom of oxygen you breathe, was manufactured inside a star that once looked something like Betelgeuse. The elements were scattered into space when that star exploded. Understanding how red supergiants behave in the final stages before the explosion is essential for understanding the cosmic processes that make planets, chemistry, and life possible. But here is the problem. Betelgeuse is the only red supergiant close enough and large enough to study in this kind of detail. Other red supergiants exist. Antares in Scorpius is the next most prominent example, but none of them offer the combination of size, proximity, and brightness that makes Betelgeuse so uniquely accessible. Betelgeuse was the first star other than the Sun to be directly imaged, back in 1996 when the Hubble Space Telescope captured its disk and revealed hot spots on the surface. Even today, it remains one of the very few stars whose surface features can be directly imaged. This means that essentially all of our detailed observational knowledge about the surfaces, atmospheres, and circumstellar environments of red supergiants comes from a single object. That is an extraordinarily narrow foundation on which to build a general understanding of how massive stars die. If Betelgeuse is somehow atypical, if its mass loss behavior, its convective dynamics, or its companion interactions make it unusual among red supergiants, then the models we build from its observations might not apply well to the broader population. Conversely, if Betelgeuse is representative, then the complexity and uncertainty we encounter in studying it suggest that our models of all red supergiants are significantly oversimplified. The companion discovery highlights this tension. Before Siwaha was confirmed, models of Betelgeuse's variability had to explain everything through intrinsic processes: pulsation, convection, mass loss. Now we know that an external perturber has been influencing the data all along. How many other red supergiants might have undetected companions altering their observed behavior? Binary and multiple star systems are common in the galaxy. More than half of all Sun-like stars have at least one companion. For massive stars, the fraction is even higher. It is entirely plausible that other red supergiants are orbited by companion stars, whose effects are currently misinterpreted as intrinsic variability. This has implications for supernova predictions. One of the long-standing goals of stellar astrophysics is to identify observational signatures that indicate a massive star is approaching the final stages before explosion. Changes in brightness, pulsation period, mass loss rate, and surface temperature have all been proposed as potential pre-supernova indicators. But if companion interactions can mimic or modulate these same signatures, the diagnostic power of any single indicator is weakened. An unusual brightness change might signal approaching core collapse, or it might signal the passage of a companion through the extended atmosphere. Without knowing whether a companion exists, Interpreting the observation becomes ambiguous. Betelgeuse also challenges models in a more fundamental way. The star is a runaway. Observations show that it is moving through the interstellar medium at approximately 30 kilometers per second, fast enough to have been ejected from its birth association in the Orion OB1 group, the region of hot young stars that includes the 3 stars of Orion's belt. Runaway stars are typically produced by dynamical interactions in dense stellar environments, either through close encounters with other stars that gravitationally sling one member out of the system, or through the supernova explosion of a binary companion whose death kick sends the surviving star flying. This velocity is not just an entry in a catalogue. It has physical consequences that are directly observable. Betelgeuse is ploughing through the interstellar medium so fast that it creates a bow shock, a curved wave of compressed gas and dust piled up ahead of the star like the wake in front of a speeding boat. This bow shock is enormous. It stretches roughly 4 light-years across, a structure so vast that if you placed it at the distance of Alpha Centauri, it would span most of the gap between our Sun and the nearest star. The bow shock was detected in infrared observations, glowing faintly as the compressed interstellar material is heated by the collision. Behind the bow shock, extending away from the star's direction of motion, trails a complex structure of expelled material, gas and dust, shed by Betelgeuse's stellar wind over thousands of years, now left behind as the star races onward. The bow shock is more than a visual curiosity. Its shape and size depend on the balance between the ram pressure of the star's motion through the interstellar medium and the pressure of the stellar wind pushing outward. Measuring the bow shock's geometry provides independent constraints on Betelgeuse's mass loss rate and wind velocity. But those constraints depend on knowing the density of the local interstellar medium, which is itself uncertain. So even this dramatic, directly observable structure becomes another variable in the web of interconnected uncertainties that defines Betelgeuse research. The bow shock tells us something about the star's mass loss, but only if we know the properties of the material it is crashing through. And the properties of that material are not known with precision. If Betelgeuse was ejected by a companion supernova, that adds another dimension to the star's history. It would mean Betelgeuse once had a more massive binary partner that already exploded, possibly enriching Betelgeuse's atmosphere with heavy elements and altering its rotational dynamics. This is distinct from the Siwaha companion, which is a smaller, younger star that would not have been involved in a prior supernova event. The runaway velocity and the current companion may be entirely separate aspects of Betelgeuse's history, each adding complexity to a system that was already difficult to model. Rotation is another poorly constrained parameter. Betelgeuse rotates slowly, with a measured surface velocity of about 5.5 kilometers per second, giving it a rotation period of approximately 36 years at its current size. The rotation axis appears to be inclined at roughly 60 degrees to our line of sight. Both of these values carry significant uncertainty, and they matter because rotation affects how material mixes inside the star, how convective cells organize on the surface, and how the star loses angular momentum through its stellar wind. Changes in rotation rate could affect pulsation properties, mass loss patterns, and the distribution of heavy elements in the outer layers. All of these feed into evolutionary models that attempt to predict the star's remaining lifetime and eventual supernova characteristics. Magnetic fields add yet another poorly understood factor. In 2010, spectropolarimetric observations detected a weak magnetic field on Betelgeuse's surface. The role of magnetic fields in red supergiant evolution is not well established, but theoretical work suggests that even moderately strong fields could influence dust formation, wind dynamics, and mass loss rates. If magnetic fields interact with convective plumes, or if they channel outflowing material in preferential directions, they could contribute to the asymmetric structures observed in Betelgeuse's circumstellar environment. The cumulative effect of all these uncertainties is that Betelgeuse remains, despite centuries of observation and decades of intensive study with modern instruments, a star that defies complete and confident characterization. Scientists know a great deal about it. They know it is a red supergiant, They know it pulsates. They know it has a companion. They know it experienced a surface mass ejection of unprecedented scale. They know it will eventually explode. But when you push past these established facts and ask more precise questions, how massive is it exactly? How far away is it exactly? How does its internal convection couple to its pulsation and mass loss? How does the companion interact with intrinsic variability? The answers dissolve into ranges, estimates, and competing models. This is the real source of scientific concern. When astronomers say they are worried about Betelgeuse, they do not mean they are lying awake at night expecting an explosion. They mean that one of the most important objects in stellar astrophysics, a star that serves as the primary observational laboratory for understanding the final evolutionary stages of massive stars, continues to produce surprises that expose the gaps in current understanding. The Great Dimming was a surprise. The Companion was a surprise. The disrupted pulsation was a surprise. The anomalous brightening of 2023 was a surprise. Each surprise was eventually given a plausible explanation, but each explanation raised new questions that have not yet been answered. The worry is not that the star will explode tomorrow. The worry is that the star is telling us something about the physics of red supergiant evolution that we are not yet equipped to fully understand. And since red supergiants are the stars that produce the supernovae that seed the universe with the heavy elements necessary for planets and life, what we do not understand about Betelgeuse is, in a very real sense, something we do not understand about the cosmic processes that made our own existence possible. Every new instrument that observes Betelgeuse reveals new layers of complexity. Every new dataset raises questions alongside the answers it provides. The star cooperates just enough to keep scientists coming back, offering tantalizing clues about its nature, then retreating behind walls of noise, uncertainty, and physical intricacy that prevent a final, definitive characterization. Betelgeuse is not a solved problem. It is an ongoing investigation. And the next step in that investigation, the one that addresses the question everyone really wants to ask, depends entirely on how honestly we confront what we still do not know. There is a question that has been hovering over this entire story. The question that brought most of you here in the first place. The question that generates headlines and social media speculation. Every time Betelgeuse does anything unexpected, will it explode? And if so, when? The honest answer is both simple and deeply unsatisfying. Yes, Betelgeuse will explode. That is not speculation, not hypothesis, not a matter of scientific debate. A star of this mass, at this evolutionary stage, burning through the final sequences of nuclear fuel in its core, has exactly one possible endpoint: core collapse, supernova. The physics is settled. Betelgeuse will die in one of the most violent events the universe can produce. But when? That is where honesty becomes uncomfortable. The best current estimate, based on the full range of stellar evolutionary models and the admittedly uncertain physical parameters of the star, is that Betelgeuse will go supernova sometime within the next 100,000 years. That is not a typo. 100,000 years. The window is so wide that it encompasses the entire span of recorded human history more than 10 times over. It could happen tomorrow. It could happen when our descendants have colonized other star systems, assuming we survive that long. It could have happened already, 650 years ago, with the light from the explosion still racing toward us through the void, not yet arrived. Some researchers have tried to narrow this window. A 2023 paper generated significant attention by suggesting that Betelgeuse might be in the late stages of carbon burning in its core, which would place the supernova on a timescale of tens of years rather than tens of thousands. The paper, titled "The Evolutionary Stage of Betelgeuse, Inferred from its Pulsation Periods," used the star's observed pulsation characteristics to constrain which nuclear burning phase it currently occupies. If the pulsation periods correspond to a star that has already progressed through helium and carbon burning and is approaching the final stages of neon or oxygen fusion, then the remaining lifetime could be dramatically shorter than the standard estimate. The paper attracted enormous public interest, which is understandable. The idea that the nearest red supergiant might explode within a human lifetime is irresistible, but the broader stellar evolution community received the claim with considerable skepticism. The analysis depends heavily on the assumed mass, distance, and internal structure of the star, all of which remain uncertain. Different assumptions about these parameters lead to different conclusions about the current burning stage. Most specialists in massive star evolution continue to favor the longer timescale, placing the supernova most likely within the next 100,000 years rather than the next few decades. The uncertainty in Betelgeuse's fundamental properties simply does not allow the kind of precision needed to narrow the window to tens of years with any confidence. This ambiguity is itself revealing. It underscores the central theme of this story. Even for the most studied red supergiant in the sky, the star whose surface has been directly imaged, whose companion has been detected, whose mass ejection has been documented in real time, we cannot determine the remaining lifetime to better than 5 orders of magnitude, somewhere between tomorrow and 100,000 years. That is a humbling range for a civilization that can measure the age of the universe to within a fraction of a percent. To appreciate why the timing is so difficult to predict, it helps to think about the pacing of those final nuclear burning stages we described earlier. We already know that each successive phase is shorter than the last, that the clock accelerates from millions of years down to a single day of silicon fusion before the iron core forms. But what matters for prediction is not the pacing itself. It is where the boundary of visibility falls. Carbon burning, which lasts perhaps 1,000 years, represents approximately the last stage where astronomers might hope to constrain the timeline through indirect observational signatures. Everything after carbon happens too fast and too deep to detect from outside. After carbon, the star enters a phase of terminal acceleration that is completely hidden from view. The final year of neon burning, the final months of oxygen burning, the final day of silicon fusion, all of it occurs in the innermost core, shielded by hundreds of solar radii of opaque stellar material. No photon from those reactions reaches the surface. No change in luminosity or temperature betrays what is happening below. Within seconds of the iron core reaching a critical mass, roughly 1.5 times the mass of the Sun packed into a volume the size of Earth, the core collapses at roughly 1/4 of the speed of light. The implosion triggers a bounce, a rebound shockwave that reverberates outward through the falling material, and eventually, aided by an enormous flood of neutrinos, blows the star apart. This hiddenness is the central problem. The star's surface, that vast red supergiant photosphere stretching outward for astronomical units, is completely decoupled from the core's final drama. The surface temperature does not change appreciably during the transition from one late burning stage to the next. The luminosity does not shift in any diagnostic way. The pulsation behavior is driven by the envelope, not by what is happening at the center. An astronomer observing Betelgeuse on the last day of silicon burning would see a star indistinguishable from one still centuries away from collapse. There is no warning. The only signal comes when the core has already collapsed and the neutrinos are already on their way. This is why no astronomer can tell you when Betelgeuse will explode. It is not a matter of needing better telescopes or more data. It is a fundamental limitation. The information we need, the current composition and burning stage of the innermost core, is physically inaccessible. It is locked inside the densest, hottest region of the star, unreachable by any electromagnetic observation. The only messenger that could carry that information to us before the explosion is the neutrino, and neutrinos from the normal burning stages are too few and too low in energy to detect at interstellar distances. We will know Betelgeuse's core has collapsed only when millions of neutrinos hit our detectors in a 10-second burst. At that point, the star is already dead. The light show follows hours later. But suppose it does happen. Suppose the core of Betelgeuse collapses while we are still around to witness it. What would we see? The first signal would not be light. It would be neutrinos. When a massive star's iron core collapses, the implosion produces an extraordinary flood of neutrinos, subatomic particles that interact so weakly with matter that they pass through the collapsing star itself almost unimpeded. These neutrinos would race outward from the core at nearly the speed of light, arriving at Earth several hours before any visible light from the explosion. We know this because it happened before. In 1987, a supernova erupted in the Large Magellanic Cloud, a satellite galaxy roughly 168,000 light-years away. 3 small neutrino detectors operating at the time registered a total of about 24 neutrinos from the event. 24 particles, from an explosion 168,000 light-years distant. That detection confirmed decades of theoretical predictions about how core collapse supernovae work. Today, the neutrino detection infrastructure is incomparably more capable. Facilities like IceCube at the South Pole, Super Kamiokande in Japan, and numerous other detectors around the world are orders of magnitude more sensitive than what existed in 1987. And Betelgeuse is roughly 260 times closer than that 1987 supernova was. The inverse square law means the neutrino flux at Earth would be roughly 70,000 times stronger. Instead of detecting 24 neutrinos, modern observatories would register millions, perhaps tens of millions, in a burst lasting 10 to 15 seconds. The signal would be unmistakable, a screaming alarm in every neutrino detector on the planet, announcing that a star 650 light-years away had just died. An international system called the Supernova Early Warning System, or SNEWS, already exists for exactly this scenario. It links neutrino detectors around the world into a network that automatically triggers an alert when multiple facilities register a simultaneous burst. The alert would go out to observatories worldwide within minutes, giving astronomers a precious window of several hours to train every available telescope on Betelgeuse before the visible fireworks begin. It would be the most anticipated astronomical observation in history, a supernova announced in advance by the particles from its own death. For a few hours after the neutrino burst, nothing visible would happen. The shock wave from the collapsing core would still be propagating outward through the star's interior, plowing through layers of silicon, oxygen, carbon, helium, and hydrogen. The star's surface would show no sign of what was happening deep inside. Observers watching Betelgeuse through telescopes during those hours would see a perfectly normal red supergiant. But underground, in laboratories around the world, physicists would be racing to analyze the neutrino data, already knowing that the sky was about to change. Then the shock wave would reach the surface. The breakout, as astrophysicists call it, would produce a sudden, intense flash of ultraviolet and X-ray radiation as the superheated shock front ripped through the photosphere and into space. Within hours, the visible brightness would begin climbing. It would climb fast. At peak luminosity, a Betelgeuse supernova would shine approximately as bright as the half moon. Not as bright as the full moon, which is a common exaggeration, but roughly comparable to a half moon. That is still astonishingly bright for a single point of light. It would be easily visible during the daytime, a brilliant pinprick in the blue sky near the constellation Orion. At night, it would cast shadows. You could read by its light. It would dominate the sky in a way no star has done since the Crab Nebula supernova of 1054, and it would be significantly closer and brighter than that event was. That comparison to historical supernovae is worth pausing on. Humanity has a surprisingly thin record of witnessing stellar explosions within our own galaxy. Chinese astronomers recorded a brilliant guest star in the year 1054 that was visible in daylight for 23 days and remained visible to the naked eye for nearly 2 years. The remnant of that explosion is the Crab Nebula, roughly 6,500 light-years away, 10 times farther than Betelgeuse. In 1572, the Danish astronomer Tycho Brahe observed a new star in the constellation Cassiopeia that rivaled Venus in brightness. That supernova, roughly 10,000 light-years distant, helped dismantle the ancient belief that the heavens were fixed and unchanging. In 1604, Johannes Kepler observed the last supernova, visible to the naked eye in our galaxy, in the constellation Ophiuchus. roughly 20,000 light-years away. That was more than 4 centuries ago. No supernova has been observed within the Milky Way since, not with the naked eye and not with any telescope ever built. 422 years. That is how long it has been since a human being witnessed a supernova in our home galaxy. Every advance in astronomical instrumentation, every major telescope built, every detector conceived and constructed, none of them have ever been turned on a galactic supernova in real time. Our understanding of core collapse explosions comes entirely from studying supernovae in other galaxies, millions of light years away, where the events appear as tiny points of light in distant systems. A Betelgeuse supernova would be the first time in the history of science that humanity observed a nearby stellar explosion with the full power of modern technology. The data would be transformative in ways that are difficult to overstate. The spectacle would last for months. Peak brightness would persist for several weeks before the supernova began to fade. Over the following months, the light would gradually diminish, but the object would remain visible to the naked eye for the better part of a year. Orion would look permanently altered, its familiar shoulder replaced by a blazing point of light that would slowly wane over the course of seasons. Eventually, over years and decades, the expanding remnant would become a diffuse nebula visible through telescopes, a glowing scar in the sky where a star used to be. The question that inevitably follows is whether we should be afraid. The answer, supported by every relevant calculation, is no. Betelgeuse is too far away to harm Earth. The dangerous effects of a supernova, intense radiation, high-energy particles, blast waves, all diminish with the square of the distance. Studies have estimated that a supernova would need to occur within roughly 160 light-years of Earth to pose a genuine threat to the biosphere. Betelgeuse is approximately 4 times farther away than that danger threshold. The explosion would be spectacular, historically unprecedented in the era of modern science, and completely harmless. No increase in radiation exposure, no disruption of the atmosphere, no mass extinction. Just the most extraordinary light show any living human has ever witnessed. For professional astronomers, the event would be a once-in-a-civilization scientific windfall. No galactic supernova has ever been observed with modern instruments. Not with spectroscopes, not with radio dishes, not with X-ray satellites, not with neutrino detectors. A Betelgeuse supernova would provide an unprecedented opportunity to study every phase of a core collapse explosion in real time, across every wavelength from radio to gamma rays, with gravitational wave detectors, neutrino observatories, and space telescopes all trained on a single event happening in our cosmic backyard. The scientific return would be incalculable. Entire careers would be built on the data. Textbooks would be rewritten. Our understanding of how massive stars die, how neutron stars or black holes form, how heavy elements are forged and dispersed into the interstellar medium, all of it would advance by decades in a matter of months. But all of this is contingent on timing, and the timing, as we have established, is unknowable. Betelgeuse could explode tonight. It could explode after every person alive today has been dead for 10,000 generations. There is no observational signature that reliably predicts the final collapse more than hours in advance. The neutrino burst is the only confirmed precursor, and it arrives only hours before the light. By the time we know it is happening, it is already done. This brings us to Siwaha, and what the companion's future tells us about the system as a whole. Current models predict that tidal interactions will gradually drag Siwaha inward toward Betelgeuse. As the supergiant continues to evolve, its outer layers will expand further, and the companion's orbit will decay. Within approximately 10,000 years, Siwaha is expected to be engulfed entirely, pulled into the body of the red supergiant and consumed. The bracelet will disappear into the hand that wears it. This engulfment would itself be a dramatic event, though nothing compared to a supernova. As Siwaha spirals inward and enters the denser layers of Betelgeuse's atmosphere, the interaction would release gravitational energy, heat the surrounding material, and potentially trigger enhanced mass loss or outbursts. The final absorption might produce observable effects from Earth, though predicting exactly what those effects would look like requires modeling capabilities that do not yet exist for systems this complex. The important point is the timeline. Siwaha is expected to be engulfed in roughly 10,000 years. Betelgeuse is expected to go supernova in roughly 100,000. If both estimates are correct, the companion will be long gone before the explosion occurs. The star will die alone, having already consumed its closest neighbor. But these timelines carry their own large uncertainties, and the possibility that the engulfment and the supernova might be separated by less time than currently estimated cannot be ruled out. If the companion's inward spiral accelerates due to factors not yet modeled, or if the supernova timeline is shorter than the standard estimate, the two events could be closer together than current predictions suggest. The next major observing opportunity for the Siwaha system will come in November 2027, when the companion is predicted to reach its widest apparent separation from Betelgeuse as seen from Earth. At that point, astronomers will have the best geometry for direct imaging and spectroscopic characterization. Multiple observatories are already planning dedicated observation campaigns for that window. The goal is to refine Siwaha's mass, temperature, luminosity, and orbital elements with much greater precision than the current tentative detection allows. Each improvement in these parameters will tighten the constraints on how the companion interacts with the supergiant and how the system will evolve in the coming millennia. But 2027 is not the only milestone on the observational horizon. Several next-generation instruments and facilities are poised to study Betelgeuse with capabilities that did not exist even a few years ago. The James Webb Space Telescope, already the most powerful infrared observatory ever launched, can observe the material ejected during the 2019 surface mass ejection as it continues drifting away from the star. That dust cloud is still out there, expanding and cooling, carrying information about the composition and physics of the ejection event encoded in its infrared emission. Webb sensitivity at these wavelengths far exceeds anything previously available. Detailed spectroscopy of the ejected material could reveal what fraction of Betelgeuse's photosphere was removed, what elements it contained, and how the dust grains formed as the material cooled. Each of these measurements feeds back into models of mass loss, dust production, and circumstellar environment evolution that are central to understanding late-stage stellar physics. On the ground, the Vera C. Rubin Observatory, with its legacy survey of space and time, will begin a decade-long survey of the entire visible sky every few nights. While Betelgeuse itself is too bright for the survey's primary science goals, the observatory's cadence and coverage will provide continuous, systematic monitoring of the star's brightness with a consistency that no previous facility has achieved. More importantly, Rubin's survey will discover and characterize thousands of variable stars and transient events across the galaxy, providing a statistical context for Betelgeuse's behavior. If surface mass ejections turn out to be common among red supergiants, Rubin has the best chance of catching all of the stars, offering comparative data that Betelgeuse alone cannot provide. The next generation of extremely large telescopes currently under construction, including the extremely large telescope being built by the European Southern Observatory in Chile, will bring angular resolution capabilities that surpass anything available today. These instruments will be able to resolve finer details on Betelgeuse's surface, track the motion of convective cells with greater precision, and potentially image Siwaha directly during favorable orbital geometry, without relying on the specialized speckle imaging techniques that produce the current tentative detection. The ability to routinely image a red supergiant surface at high resolution will transform Betelgeuse from a star observed in snapshots into a star observed in continuous, detailed motion. Quietly, steadily, neutrino observatories around the world continue their vigil. Detectors like IceCube, Super Kamiokande, the Sudbury Neutrino Observatory successor, and newer facilities like the Jiangmen Underground Neutrino Observatory in China stand ready to catch the burst that would signal the end. The supernova early warning system links them together, ensuring that when the moment comes, whether tonight or in 10,000 years, The alert will go out, and the scientific community will have its precious hours of advance notice. These detectors do not sleep. They do not take nights off. They watch patiently for a signal that might never come in our lifetimes, but that physics guarantees will come eventually. But stepping back from the specific scientific questions, there is a larger significance to the Betelgeuse story that deserves reflection. This star has become something rare in modern astronomy. It has become a laboratory where the unknown is not hidden behind billions of light years of distance or billions of years of cosmic time. It is right there, 650 light years away, glowing in the shoulder of Orion, visible to anyone who steps outside on a clear winter night and looks up. The mysteries of Betelgeuse are accessible in a way that most cosmic mysteries are not. You can see the object of study with your own eyes. You can point at it and say, that is the star that tore off a piece of its own surface and hurled it into space. That is the star with a hidden companion carving a wake through its atmosphere. That is the star that will someday produce one of the most spectacular events any human will ever witness. And yet, for all that accessibility, for all the centuries of observation and the decades of modern study, Betelgeuse continues to surprise. It continues to reveal behavior that was not predicted, that challenges existing models, that forces scientists to revise their assumptions and expand their understanding. This is not a failure of the scientific process. It is the scientific process working exactly as it should. Nature is under no obligation to conform to our models. When observations contradict predictions, models must change. And Betelgeuse has forced more model revisions in the past 6 years than most stars produce in a century. None of the major discoveries of the past 6 years were anticipated by the models that existed before them. The theoretical framework for red supergiant evolution contained no mechanism for a star to eject a chunk of its own photosphere in a single violent episode. The models that explained Betelgeuse's secondary brightness cycle relied entirely on intrinsic processes, convection and pulsation mode interactions, with no provision for an external companion orbiting inside the atmosphere. The understanding of stellar pulsation assumed that a 49-day fundamental mode, once established, would persist until the star's death, and be shut down for years by a surface eruption. In every case, the observation came first and the explanation followed. The models did not lead. They were dragged. This pattern of reactive understanding expanded the space of what astronomers considered possible for red supergiants. Each one added new variables to an already complicated system. And each one came from the same star, the one we know best, the one we have studied the longest, the one closest to Earth. If this star, the single most observed red supergiant in the sky, can still produce fundamental surprises, what does that say about the thousands of other red supergiants scattered through our galaxy? Stars that are too distant for surface imaging, too faint for high-cadence spectroscopic monitoring, too obscured by intervening dust for detailed characterization. How many of them harbor unseen companions? How many of them have experienced surface mass ejections that went unrecorded because no one was watching closely enough? How many of them are behaving in ways that would challenge our models if only we could see them clearly? This is the question that gives Betelgeuse its deepest scientific significance. It is not just one interesting star. It is a window into an entire class of objects that we understand far less well than we would like to believe. Red supergiants are the final act in the lives of massive stars. They are the precursors to the explosions that forge heavy elements, create neutron stars and black holes, and shape the chemical evolution of galaxies. Getting the physics of red supergiants right is essential for understanding supernovae, and getting supernovae right is essential for understanding the origin of the elements that make up planets, atmospheres, oceans, and living organisms. The stakes are not abstract. They are about the fundamental processes that connect stellar death to the chemistry of existence. And right now, the best laboratory we have for studying those processes is a single, complicated, surprising, maddeningly uncertain star in Orion. That star has told us more about late-stage stellar evolution in the past 6 years than many researchers expected to learn in a career. but it has also shown us how much remains unknown. The surface mass ejection revealed a mass loss mechanism that had never been directly observed. The companion revealed an external influence that had been misinterpreted for decades. The pulsation disruption revealed a fragility in a process that had seemed permanent and stable. Each discovery was a triumph of observation. Each discovery was also a reminder of how much our models were missing. When scientists say they are worried about Betelgeuse, this is what they mean. The worry is not that the star will explode and harm us. It will not. The worry is not that a supernova is imminent. It almost certainly is not, at least not on any timescale relevant to anyone alive today. The worry is something more subtle and more profound. It is the recognition that one of the most famous, most visible, most intensely studied stars in the entire sky is still capable of revealing behavior that no one predicted and that existing models cannot fully explain. That kind of worry is not anxiety. It is the productive discomfort that drives science forward. It is the awareness that the universe is more complex than our equations currently capture, and that the gap between observation and understanding is wider than we might wish. Every surprise Betelgeuse produces is an invitation to build better models, develop more sensitive instruments, and ask sharper questions. Every anomaly is a clue, a fingerpost pointing toward physics that has not yet been written into the textbooks. And so astronomers continue to watch. They monitor the star's brightness with ground-based photometry. They track its spectral changes with high-resolution spectrographs. They resolve its surface features with interferometric imaging. They model its interior with three-dimensional hydrodynamic simulations. They wait for Siwuha to emerge into better viewing geometry in 2027. They wait for the James Webb Space Telescope to reveal new details about the ejected material still drifting away from the star. They wait for the next generation of enormous ground-based telescopes to bring Betelgeuse's surface into sharper focus than ever before. They wait, above all, for the next surprise. Because if the past 6 years have taught them anything, it is that Betelgeuse will provide one. Look up on a clear winter night and find Orion. Find the bright orange-red star at the hunter's shoulder. It has been there for as long as humans have looked at the sky. Ancient Egyptians tracked it. Greek astronomers named the constellation around it. Arabic scholars gave it the name we still use today. For millennia, it was simply a bright star, beautiful and constant, a fixed point in the turning sky. It is not constant. It never was. It is a dying giant, shedding its skin, shaking from internal convulsions, orbited by a companion it will eventually swallow, destined for an explosion that will outshine every other star in the galaxy for weeks. It is a star with processes so complex that even now, with every telescope humanity can muster aimed in its direction, we cannot fully describe what is happening inside it. We cannot say when it will die. We cannot predict what it will do next. And that uncertainty, that irreducible gap between what we can observe and what we can explain, is not a limitation to be ashamed of. It is the frontier. It is where science lives, the space between what we know and what we do not yet know, lit by the red-orange glow of a star that has been trying to tell us something for centuries. We are only now learning how to listen. Betelgeuse is not a crisis, it is a conversation between a dying star and a species just barely old enough to understand what it is looking at, and that conversation is far from over. Long does not belong in any category that the word travel can meaningfully describe. It is not a voyage, it is a geological process, and even light speed itself, the absolute maximum velocity permitted by the universe, does not rescue the situation. It only reveals the depth of the problem in its purest form. At exactly the speed of light, the journey to Andromeda takes 2.5 million years, no less. 2.5 million years is not a number you can contextualize through human experience, because human experience does not extend that far. Civilization does not extend that far. The entirety of what we call history, the 5,000 or 6,000 years of recorded events that constitute the full memory of our species, fits inside the light travel time to Andromeda, roughly 400 times over. The light travel time to Andromeda is not a historical duration. It is a biological one. It belongs to the timescale on which species evolve, diverge, and go extinct. So let us walk backward through it. Let us stand at the present moment and step backward in time, year by year, and see what we pass as we rewind through 2.5 million years of history. This is how long the light you see from Andromeda tonight has been traveling. Every milestone we pass is a milestone that light has already outlived on its journey to your eye. Start walking backward. 500 years ago, the Renaissance was reshaping Europe. Christopher Columbus had just crossed the Atlantic. Light from Andromeda was already ancient beyond measure, and still had 500 years of travel left. 1,000 years ago, the Viking Age was ending. The Song dynasty ruled China. The light kept coming. 2,000 years ago, the Roman Empire straddled the Mediterranean. Jesus of Nazareth was alive. The light did not care. 5,000 years ago, the first cities rose in Mesopotamia. Writing was invented. History began. The light from Andromeda, already in transit for 2,495,000 years, had barely started its final approach. Keep walking. 10,000 years ago, the last ice age was ending. Agriculture was being invented independently in multiple regions. Humans were beginning to settle into permanent communities. The light had been traveling for 2,490,000 years and still had 10,000 left to go. 50,000 years ago, anatomically modern humans were painting caves in Europe, crafting bone tools, developing language complex enough to tell stories. They were crossing oceans, colonizing new continents, reshaping ecosystems with fire and ingenuity. The light had 2,450,000 years behind it, and 50,000 remaining. A blink. An afterthought. 300,000 years ago, the earliest known Homo sapiens appeared in the fossil record in North Africa. This is roughly the full span of our species' existence. The light from Andromeda had already been traveling for 2,200,000 years when our species was born. We are not even a footnote in the duration of that journey. We are a parenthetical remark inserted into the final entry of an encyclopedia that has been writing itself for millions of years. Keep going. 2.5 million years ago, the genus Homo had only just emerged in East Africa. The earliest members of our lineage had recently begun chipping crude stone tools from river cobbles, a behavior barely 100,000 years old at that point. And this is precisely when the light you see tonight from Andromeda left its source galaxy. The photons departed 1 trillion alien suns during the same narrow window of geological time, in which the first beings who could arguably be called human were learning to shape rocks into cutting edges on the African savanna. The entire lineage of humanity, every species of Homo that has ever existed, from habilis to erectus to heidelbergensis to neanderthalensis to sapiens, every one of them lived and died within the travel time of that light. The light is as old as our genus. It departed Andromeda within the same sliver of geological time that produced the first recognizably human species on Earth. It arrived tonight. Every species of Homo that has ever existed has lived and died within the travel time of that light. But that walk backward through time began broad strides. Let us slow down and feel the full weight of the elapsed duration by placing more markers along the path, because 2.5 million years contains far more than the story of human evolution. It contains chapters of Earth's history that make our species look like a postscript scribbled in the margin. 2.5 million years ago, when the light from Andromeda began its journey, the Earth was entering the Pleistocene epoch. The planet was cooling. Ice sheets were beginning to advance across the northern hemisphere in cycles that would persist for millions of years. Mastodons roamed North America. Giant ground sloths the size of elephants browsed the forests of South America. Saber-toothed cats stalked prey across grasslands that stretched from modern-day Texas to Patagonia. The Mediterranean Sea, which had catastrophically dried out and refilled millions of years earlier during the Messinian salinity crisis, was once again a stable body of water. The Isthmus of Panama had recently closed, connecting North and South America for the first time, triggering the Great American Interchange, one of the largest migrations of land animals in geological history. The light from Andromeda departed during a world that looked like a nature documentary set on an alien planet, filled with megafauna that would not survive to greet the species that would eventually build telescopes. As that light crossed the first 500,000 light-years of void, the genus Homo was already diversifying across Africa. Homo habilis was giving way to new species, some with larger brains and longer limbs than any hominin before them. Stone tools remained crude, simple choppers and flakes struck from river cobbles, but they were spreading to new regions as early humans expanded their range across the continent. Stone tools grew gradually more sophisticated, brain volume increased, bipedalism refined. Fire may have been used opportunistically, but no language existed, no art, no symbolic thought. These were clever apes learning to survive on a changing continent, while a photon from a distant galaxy crossed a quarter of the intergalactic abyss above their heads, unnoticed and unimaginable. With 1 million light-years still remaining, the light from Andromeda had already been traveling for 1.5 million years. On Earth, Homo erectus was the dominant hominin species. On Earth, Homo erectus was the dominant hominin species. They had spread out of Africa into Asia and parts of Europe. They used Acheulean hand axes, symmetrical teardrop-shaped stone tools that represented a genuine cognitive ability. They may have controlled fire deliberately. They hunted large game. They persisted as a species for nearly 2 million years, an astonishing run by any evolutionary standard. And yet even Homo erectus, one of the most successful species in the history of our lineage, would be gone long before the photon arrived. At 500,000 light-years remaining, the light had been traveling for 2 million years. Homo heidelbergensis walked the Earth, ancestral to both modern humans and Neanderthals. Early evidence of shelters, of wooden spears, of coordinated hunting strategies, the stirrings of something approaching culture, though still nothing resembling language or art as we understand them. The photon was now closer to Earth than to Andromeda, and still had farther to travel than the entire width of the Milky Way multiplied by 5. At 100,000 light-years out, Homo sapiens had already been walking the Earth for 200,000 years. Anatomically modern humans had spread beyond Africa, developed specialized tools, and begun burying their dead with apparent intention. They were beginning to craft specialized tools, to use pigments, to bury their dead with apparent intention. They had not yet left Africa in significant numbers. They had not painted caves. They had not domesticated animals. They had not invented the wheel, or the bow, or the boat. The photon had 99.996% of its journey behind it, and still had 100,000 years of travel remaining. That residual distance, the last tiny fraction of the crossing, is the entire width of the Milky Way galaxy. At 10,000 light-years remaining, humanity had built Göbekli Tepe, the oldest known monumental structure. Agriculture was spreading. Cities were forming. Writing was about to be invented. The photon was in the final 0.4% of its journey. The distance remaining was still 10,000 light-years, a gulf that light needs 10 millennia to cross, a span that contains the entire history of what we call civilization. And it was a rounding error, a decimal point, an afterthought at the end of a 2.5 million year sentence. These milestones are not decorations, they are the point. 2.5 million years is not an abstraction when you fill it with the lives and extinctions and evolutionary experiments that actually occupy that time. It is not a number when you populate it with mastodons and ice ages, but the slow, painful emergence of consciousness from the raw material of primate neurology. It is a duration that contains the entire story of everything we are. And it is the time required for a single photon, moving at the fastest speed the universe permits, to cross the gap between us and the galaxy next door. That is what 2.5 million light years feels like when you translate it into time. Not a number, not a distance, a biological epoch. A span of time long enough for evolution to produce an entirely new kind of animal, from the first stone tool to the smartphone, from the African savannah to the Sahara, all of it contained within one photon's commute. And here is the detail that turns distance into something closer to imprisonment. Suppose you wanted to communicate with someone in the Andromeda galaxy, not travel there, just talk. Send a message and receive a reply. You encode a radio signal, aim it at Andromeda, and transmit it at the speed of light. The signal departs Earth and begins crossing the intergalactic void. 2.5 million years later, it arrives. Whatever civilization receives it, assuming one exists and is listening, decodes your message. They compose a reply, they transmit it back at light speed. Another 2.5 million years pass. The reply arrives at Earth. Total elapsed time for a single exchange, 5 million years. A round-trip conversation with Andromeda takes 5 million years at the fastest speed the universe allows. 5 million years ago, our ancestors had only recently diverged from the lineage leading to chimpanzees. They were early hominins, creatures partway between ape and human, walking upright some of the time and climbing trees the rest. If a human civilization had somehow existed 5 million years ago and sent a greeting to Andromeda, the reply arriving today would reach a planet populated by beings who share no language, no culture, no institutional memory, and arguably no species identity with the senders. The civilization that sent the message would be as alien to the civilization receiving the reply as Australopithecus is to a modern-day astronaut. Communication with Andromeda is not impractical. It is incoherent. The timescale destroys the very concept of a conversation because no entity on either end persists long enough to participate in both halves of the exchange. This is the dimension of the problem that raw distance fails to convey. When you say 2.5 million light years, it sounds like a measurement, a fact about geometry. But when you convert it to time, it becomes a fact about mortality, about the impermanence of species, about the terrifying brevity of everything we are compared to the gaps between the structures we inhabit. The distance to Andromeda is not a wall you could theoretically climb, given enough time and technology. It is a wall built from time itself, and it is taller than our species is old. Now consider what this means for the visual paradox that opened this entire story. You can see Andromeda. It is right there in the sky, a smudge of ancient light visible to the naked eye, beautiful and beckoning. Astronomers have mapped it in extraordinary detail. The Hubble mosaic resolved 200 million individual spots across its disk. We know its rotation rate, its chemical composition, its merger history, the mass of its central black hole. We have studied it for over 1,000 years. In every scientific sense, Andromeda is one of the best understood objects in the sky. We know it intimately, and yet it is separated from us by a gap that would swallow 4 billion years of travel at our fastest speed. We can see it, we can study it, we can photograph it, we can never touch it. This is also where the most recent scientific discoveries sharpen the blade of the paradox rather than dulling it. In January of 2025, the Hubble Space Telescope completed the most ambitious photographic survey of Andromeda ever attempted. The Panchromatic Hubble-Andromeda Treasury, its successor, the Panchromatic Hubble-Andromeda Sun Treasury, combined more than 600 overlapping entities taken over a decade of observation, requiring over 1,000 Hubble orbits to produce a 2.5 billion pixel panoramic mosaic of the entire Andromeda disk. The image resolved more than 200 million individual stars, each one a nuclear furnace burning hydrogen, many of them likely hosting planetary systems, all of them separated from us by 2.5 million light-years of impassable void. The level of detail is astonishing. Astronomers can distinguish individual stellar types, trace dust lanes threading between spiral arms, identify thousands of star clusters embedded in the disk, and reconstruct Andromeda's merger history by analyzing the ages and chemical compositions of stellar populations across the galaxy. We now know that Andromeda experienced a major merger with another galaxy approximately 2 billion years ago, an event that reshaped its structure and triggered waves of star formation still visible in the distribution of young blue stars. We know that its evolutionary history differs markedly from the Milky Way's, with a more active recent history of collisions and accretion. We know, from spectroscopic follow-up observations at the Keck Observatory, how individual stars within the disk move, how the galaxy rotates, and what that rotation implies about the distribution of mass, including dark matter, throughout its structure. Every one of these discoveries deepens our knowledge of Andromeda, and every one of them deepens the cruelty of the distance, because the more we learn, the more real Andromeda becomes. The more real it becomes, the more painful its inaccessibility feels. This is not a vague smudge of unknown origin. This is a galaxy we have mapped star by star, whose history we can reconstruct, whose future we can model, whose internal dynamics we can observe in real time through the motions of its stellar populations. We know Andromeda better than we know most countries on the planet. We will never set foot in it. The very question of whether the Milky Way and Andromeda will physically merge has itself become uncertain. For decades, the collision was treated as settled science, a gravitational inevitability expected to occur in roughly 4.5 billion years. But a 2025 study published in Nature Astronomy by Til Sawala and colleagues, using 100,000 simulations incorporating the latest Hubble and Gaia data, along with the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, found that the probability of a merger within the next 10 billion years may be only around 50%. The Large Magellanic Cloud, orbiting the Milky Way with roughly 15% of its mass, exerts a gravitational pull perpendicular to the Milky Way Andromeda orbital plane that could deflect our galaxy's trajectory enough to prevent a direct collision. A subsequent 2026 study by Wu and collaborators, using updated Gaia proper motion measurements for stars in Andromeda, pushed the merger probability back up to approximately 90% over 10 billion years, with a median merger time of roughly 6.5 billion years. The science remains unsettled, with further Gaia data releases expected in the summer of 2026 to refine the measurements. But the very fact that the outcome is debated underscores the scale of the system. Two galaxies separated by 2.5 million light-years, approaching each other at 110 kilometers per second, and astronomers still cannot say with certainty whether they will collide, because the distances and timescales involved are so enormous that tiny uncertainties in velocity and mass propagate into radically different outcomes, billions of years in the future. The gap between us and Andromeda is so vast that even gravity, the most patient force in nature, takes billions of years to close it, and the outcome of that closing remains a coin flip. This contradiction between visual accessibility and physical inaccessibility is not a minor irony. It is the central cruelty of intergalactic distance. The universe lets you look. It lets you gather photons that have been crossing the void since before your species existed. It lets you build instruments that can resolve individual stars in a galaxy millions of light years away. It gives you knowledge, but it does not give you access. Knowledge and access are not the same thing, and the The distance to Andromeda is the clearest proof that the universe treats them as entirely separate gifts. They know everything about the galaxy next door. You will never go there. The light bridge connecting you to Andromeda is one directional. Information flows in. Nothing flows out. You are an observer, permanently. A prisoner with a window but no door. And this brings us to one final calculation that deserves to sit in the mind like a weight. We have considered the journey at the speed of our fastest spacecraft. We have considered it at 1%, 10%, and 100% of the speed of light. Every result was measured in millions or billions of years. But what if we abandon realism entirely? What if we ask the most generous possible question? How fast would you need to travel to reach Andromeda within a single human lifetime? Assume a generous lifespan, say 80 years. To cross 2.5 million light years in 80 years of ship time, you would need to travel at a speed so close to the speed of light that relativistic time dilation compresses the journey from the traveler's perspective. Special relativity permits this in principle. If you accelerate continuously at 1g, a comfortable Earth-like acceleration, you could theoretically reach velocities arbitrarily close to light speed. At such velocities, time aboard the ship slows relative to time in the outside universe. The traveler ages 80 years, but the universe outside ages millions. The math allows it. The physics, in principle, does not forbid it, but the energy requirements are beyond anything humanity can currently contemplate. Accelerating even a modest spacecraft to 99.9999% of the speed of light would require more energy than human civilization currently produces in centuries. And when you arrived at Andromeda, 80 years older, you would step out into a galaxy where 2.5 million years had elapsed back home. Earth would be unrecognizable. Everyone you knew would be not merely dead but fossilized, their bones compressed into geological strata, their civilizations erased, their languages forgotten. You would arrive at Andromeda as the last relic of a world that no longer exists. The journey would not connect two civilizations. It would orphan one traveler from everything they ever knew. Think about what awaits that traveler. They step out of the spacecraft 80 years older, biologically intact, mentally continuous with the person who boarded. Their memories of Earth are vivid. The faces of the people they left behind are still sharp. The language they speak is the language of the launch day. But behind them, across 2.5 million light years of void, the Earth they remember has been dead for geological ages. The continents have drifted. The oceans have changed shape. The species that built the spacecraft, Homo sapiens, may have evolved into something unrecognizable, or gone extinct entirely, or been replaced by successor species that have no memory of ever having launched a ship toward Andromeda. Every city the traveler remembers has been ground into sediment by ice ages and tectonic shifts. Every nation dissolved, every language fossilized into silence. The traveler carries in their living memory a civilization that exists nowhere else in the universe. A ghost world preserved only inside one skull crossing the intergalactic void. Arrival at Andromeda would not be an achievement. It would be the loneliest moment in the history of consciousness. A single mind standing on the shore of an alien galaxy, with nothing behind them but extinction and nothing ahead but the unknown. Even the most exotic physics does not solve this. It only reshapes the tragedy. Time dilation can shorten the traveler's experience of the crossing, but it cannot shorten the crossing itself. The 2.5 million light years remain real. The void remains real. The photons still take 2.5 million years to make the trip, and any physical object must do at least as badly. The universe does not offer shortcuts across intergalactic space. It offers only the hard geometry of distance and the hard arithmetic of speed. And both of them conspire to produce the same verdict. Andromeda is beyond reach. Not beyond reach in the way that the deep ocean was beyond reach before submarines, or the moon was beyond reach before rockets. Those were engineering problems. This is a physics problem. The distance to Andromeda is woven into the fabric of space-time itself. The No technology that obeys the known laws of the universe can overcome it in any time frame that preserves the identity or continuity of the travelers. So here we are, standing on a small planet orbiting an average star in a galaxy that contains 400 billion other stars, staring across 2.5 million light years at another galaxy, equally vast, equally magnificent, burning with 1 trillion suns. We can see it, we can study it, we can measure every detail of its structure, with instruments so precise they resolve individual stars at a distance that light takes longer than the age of our species to cross. We cannot go there, not in a century, not in a millennium, not in 1 million years. The nearest major galaxy, the one we call our neighbour, the one whose light decorates our autumn sky with that soft, ancient glow, sits behind a barrier of distance so absolute that it makes the boldest dreams of interstellar travel look like stepping across a mountain. And this, it turns out, is not even the most disturbing part, because the distance to Andromeda is not exceptional. It is not an outlier, not a worst-case scenario, not an unusually wide gap in an otherwise navigable universe. Andromeda is the closest major galaxy. It is the best case. Every other large galaxy in the universe is farther, most of them enormously so. If even the nearest one sits behind more than 4 billion years of travel time, what does that say about the rest of the cosmos? What does it say about the 2 trillion other galaxies scattered across 93 billion light-years of observable space? What does it say about the universe we can someday explore? That is the question this story has been building toward, and the answer is not what you want to hear. There is a moment in every child's life when they look up at the night sky and feel the universe orbiting. The stars seem like destinations. The darkness between them seems like a sea waiting to be crossed. Every science fiction story reinforces this instinct. Warp drives, hyperspace, stargates, generation ships. The cultural mythology of space travel assumes that distance is a problem to be solved, a barrier to be broken, a chapter in a longer story that ends with humanity spreading across the cosmos like seeds of wind. And within the solar system, within the cocoon of space we actually inhabit, that mythology holds a kernel of truth. We have walked on the moon, we have driven robots across Mars, we have dropped probes onto Titan, threaded spacecraft through the rings of Saturn. The distance within the solar system is an engineering challenge, not a physical impossibility. The mythology breathes because local reality gives it just enough oxygen to survive. The distance to Andromeda suffocates that mythology. It does not challenge it or complicate it or push it to its limits. It kills it, because the distance to Andromeda is not an engineering problem awaiting a clever solution. It is a statement about the geometry of the universe itself, written in the language of space-time, enforced by the speed of light. And that statement says something that no amount of technological optimism can argue away. The nearest major galaxy is already so far that the word loses its meaning when applied to the crossing. If even the closest galactic neighbour requires billions of years to reach at our fastest speeds, or millions of years at speeds we cannot achieve, or 2.5 million years at the cosmic speed limit itself, then intergalactic travel is not a distant dream. It is a category error, a misapplication of a concept that works at one scale to a problem that exists at an entirely different one. Calling the crossing to Andromeda a journey is like calling the Pacific Ocean a puddle. The word does not shrink to fit the reality. It simply stops being the right word. This is where the real terror lives, not in the fact that Andromeda is far away. You already knew that. Everyone knows that galaxies are far away. The terror lives in the fact that Andromeda is the nearest major galaxy. It is already this far. The distance to Andromeda is not the problem at its worst. It is the problem at its best. It is the absolute minimum intergalactic distance available to us, the shortest possible crossing to another major galaxy, and it already sits beyond any conceivable reach. This means the problem is not about Andromeda specifically. It is about the architecture of the universe. Galaxies are separated from each other by voids measured in millions of light years. That is not an accident. That is not bad luck. That is how the cosmos is built. The large-scale structure of the universe consists of galaxies clustered along filaments of the cosmic web, separated by enormous bubbles of cosmos. The average spacing between major galaxies in the cosmos is several million light years. Some cluster together in dense cluster environments, where dozens or hundreds of galaxies crowd within a few million light years of each other. But even those crowded environments involve distances that dwarf everything inside any single galaxy by factors of tens or hundreds. The local group, our own little gravitational body, spans roughly 10 million light years and contains about 100 known galaxies. The overwhelming majority of those are dwarf galaxies, tiny systems containing a few million or a few billion stars, scattered through like crumbs on a vast tablecloth. The only two major galaxies are the Milky Way and Andromeda. They dominate the group, accounting for most of its mass and virtually all of its large-scale structure. The Triangular Galaxy, the third largest member, is a modest spiral containing roughly 40 billion stars, significant but not comparable to the two giants. Everything else is small, faint, and isolated. The local group is not a bustling neighborhood. It is two mansions surrounded by dozens of garden sheds, scattered across a landscape 10 million light years wide. And this is one of the denser galactic environments in the universe. Beyond the local group, the distances explode. The nearest major galaxy cluster, the cluster, lies approximately 54 light years away. It contains over 1,300 galaxies. The nearest comparable supercluster structure, the Laniakea supercluster to which our own local group belongs, spans roughly 500 million light years. The observable universe stretches 93 billion light years from edge to edge and contains an estimated 2 trillion galaxies. Those galaxies are not evenly distributed. They cluster along filaments separated by cosmic voids that can stretch hundreds of millions of light years across. Voids so empty that if you were placed at the center of one, the nearest galaxy might be invisible to all but the most powerful telescopes. This is the cosmos. Not a garden of reachable destinations, but an archipelago of island galaxies separated by oceans of nothing. Each ocean so wide, crossing the narrowest one, the one between us and Andromeda, already requires more time than our species has existed. Think about what this means for the wider universe. If Andromeda, at 2.5 million light years, requires 4 billion years of travel at our fastest speed, then the Virgo cluster, at 54 million light years, would require approximately 85 billion years. The observable edge of the universe, at 46.5 billion light years, require a travel time so vast it takes a string of zeros to write. And those are the distances to objects we can see, objects whose light has reached us. The universe almost certainly extends far beyond the observable horizon, possibly infinitely. And every additional light year of distance adds another possibility on top of the impossibilities already stacked in the ceiling. The 2 trillion galaxies we can detect are 2 trillion destinations. They are 2 trillion windows. You can look through them. You can study what lies beyond, but you cannot climb through the glass. And this is where the emotional weight of Andromeda's distance settles onto the chest and refuses to lift, because the universe is beautiful, staggeringly, heartbreakingly beautiful. Hubble, Webb, and ground-based observatories show us galaxies in every stage of evolution. Chaotic protogalactic clumps in the deep field images to grand design spirals with arms as elegant as cubes. We have seen galaxies colliding in slow-motion gravitational dances that last hundreds of millions of years. We have seen starburst galaxies igniting with the fury of simultaneous stellar births. We have seen elliptic galaxies glowing with the amber light of ancient stars that formed when the universe was young. We have seen lenticular galaxies, ring galaxies, irregular galaxies shaped by collisions and tidal forces into forms that look like abstract art. The universe is the complex gallery of structure and light and motion. Every piece in the gallery is locked behind a barrier of distance so extreme that observation is the only relationship between it. Andromeda is the one piece of light that is close. It is the galaxy we want to feel connected to the larger cosmos. The galaxy we include in collision simulations. We say will merge with our Milky Way someday. It makes us feel like participants in a galactic story rather than isolated spectators. And all of that is true in science. Milky Way and Andromeda are gravitational. They're approaching each other. 5 billion years or 10, they pass each other and loop back. As the most recent studies suggest is possible, they are part of the same gravitational system. But gravitational interaction is not the same as accessibility. Two objects can be gravitationally bound across a distance that no physical traveller can cross within any meaningful time frame. The Moon is gravitationally bound to the Earth and we can reach it in 3 days. Andromeda is gravitationally bound to the Milky Way. We cannot reach it in 4 billion years. Gravity connects them. Distance isolates them. Both facts are true simultaneously. The second one is the one that matters for the question about what humans can actually do. Here is another way to feel great. Consider what you are seeing in Andromeda on a clear night. You are seeing light that left that galaxy 2.5 million years ago. You are looking at the past, not the recent past, the deep past. The Andromeda galaxy you observe tonight is the Andromeda galaxy as it existed before the emerged on Earth. If an observer in Andromeda aimed a sufficiently powerful telescope at our planet right now, they would not see human civilization. They would not see cities or agriculture or language. They would see a world of Australopithecus, an early Homo species, checking stones and avoiding predators on the African savanna. That is the temporal displacement created by 2.5 billion years. It does not merely separate 2 points in space, it separates 2 points in time. Andromeda, as it exists right now, at this very moment, is invisible to us. We will not see the Andromeda of today until 2.5 million years from now. Long after every human has been dead for longer than civilization has existed. This temporal isolation compounds the spatial isolation and makes the neighbour almost cruel. You do not just live in an era, you live in a different era. What you see is ancient. The Andromeda exists. The two are separated by a time gap so vast that no meaningful real-time relationship between them is possible. We are neighbours in space, strangers in time. The distance between us causes both forms of separation simultaneously. Now we turn to the central question this story was always building toward. What does the distance to Andromeda actually mean? Not as a number, not as a travel time, but as a truth about the universe and our place within it. Because the real revelation is not that Andromeda is far. The real revelation is that Andromeda's distance tells us about everything else. The nearest major galaxy sits behind a wall of 200 years, and the universe is not a space we look through, it is a space we look at. So the cosmos, with its 2 trillion galaxies and its trillions of stars, is a panorama of empty territory. It is something we can map, photograph, study and admire, but not something we can inhabit in a tiny galactic corner. The distance to Andromeda draws a line. On one side of that line sits the point we can plausibly reach, even in the most wildly optimistic projections of future technology. The nearest stars, maybe in some unimaginably distant future, the nearest regions of our own galaxy, that is the magical universe. It is a bubble, perhaps a few thousand light years in radius. Most of it is a thin shell wrapped around one ordinary star with a spiral arm. On the other side of the line is everything else. Every other galaxy, every galactic cluster, every structure of the cosmic web, every world, every star, every possible civilization that exists inside our local bubble. All of it is visible. All of it is knowable through light. None of it is Andromeda is the closest thing on the far side of that line. And the line is not holding, it is retreating. The isolation that Andromeda's distance represents is not a fixed condition of the cosmos. It is a worsening one, because the universe is expanding, and that expansion is accelerating, driven by dark energy, a mysterious repulsive pressure that constitutes roughly 68% of the total energy content of the cosmos. Within the local group, gravity is strong enough to resist this expansion. The Milky Way and Andromeda and their retinue of dwarf satellites are gravitationally bound, falling toward each other despite the stretching of space around them. But beyond the local group, dark energy wins. Galaxies outside our gravitational family are being carried away from us by the expansion of space itself, and they are receding faster the farther away they are. The Virgo cluster, 54 million light-years distant, is receding at roughly 1,100 kilometers per second. More distant structures move faster still. At a distance of approximately 14 billion light-years, the recession velocity reaches the speed of light. Galaxies beyond that threshold are moving away from us faster than light can travel, not because they are physically moving through space at superluminal velocities, but because the space between us and them is stretching faster than photons can cross it. This means those galaxies are already beyond our reach, not merely beyond our ability to travel to them, but beyond our ability to ever communicate with them, even in principle, even with signals moving at the cosmic speed limit. Light we send in their direction will never arrive. Light they send in their direction will never reach us. They have crossed the cosmological event horizon, defined not by a wall or a barrier, but the geometry of expanding space-time itself. Today, more galaxies cross that horizon. Cosmic expansion is carrying objects moving at an accelerating rate. The observable, the sphere of space from which light is not growing fast enough to compensate. The number of galaxies we could theoretically influence is shrinking, not growing. The universe is getting linear. The implications over cosmic time are staggering. In roughly 100 billion years, every galaxy in the local group will have receded beyond the observable. Future astronomers, if any exist, will look out into the sky and see nothing but the merged remnant of the Andromeda and its attendant dwarfs floating over the empty cosmos. The cosmic background radiation will have been stretched away to detect. The evidence for the Big Bang, for expansion, for the existence of other galaxies vanished. A civilization arising from that event to discover that the universe was ever anything but a single galaxy surrounded by infinite emptiness. The knowledge that we possess today, the knowledge of 2 trillion galaxies and a cosmos 93 billion, will be physically inaccessible to them, not hidden, not encrypted, the dimension of space itself. This future destination matters for the story of Andromeda because it reveals that the isolation we feel now, the horror of realizing that the nearest major galaxy is beyond meaningful reach, is a full picture. It is the beginning of a process that leads to cosmic solitude. Andromeda is the one major galaxy we will ever interact with, because it is the only one gravitationally bound tightly enough to resist the expansion of everything else away. In a sense, the merger of the Milky Way and Andromeda, whenever it occurs, is not just a collision. It is a consolidation. The universe is our final companion, and then slowly, removing every other galaxy from the sphere. What remains after the merger? The combined elliptical galaxy, sometimes called Milkomeda, lonely home. The nearest major galaxy is already millions of light years away and getting farther. Andromeda is not just our nearest neighbor, it is, for all practical and physical purposes, this is what makes the distance to Andromeda terrifying and nearly impressive. It is not the size of the number, it is what the number reveals about the boundary between the experience. Humanity can know the universe. We have proven that beyond any doubt. It is galaxies 13 billion light years away. We can measure the cosmic microwave background radiation left over from the birth of the cosmos. We can infer the existence of dark matter and dark energy, substances we have never directly observed, through their gravitational effects on physical structures. Our knowledge of the universe is vast, precise, and growing, but our experience of the universe is confined to one galaxy, one island, in an archipelago of 2 trillion. And the nearest neighbouring island is already so far that crossing to it would take longer than our planet has existed. There is a philosophical tradition that finds comfort in cosmic scale. The overview effect, experienced by astronauts who see Earth from orbit, often produces feelings of unity and transcendence. The knowledge that we are small can feel liberating, release from the petty concerns of individual life into a larger perspective that encompasses stars and galaxies and cosmic time. There is real beauty in that perspective. The universe is magnificent. Its structures are elegant, its processes are awe-inspiring, but the distance to Andromeda introduces a different emotional register. Not awe, not wonder, something closer to grief, because the distance tells you that the magnificence is real and untouchable. The universe spread its galaxies across a canvas so large that no single species, no matter how intelligent or technologically advanced, could ever visit more than an infinitesimal fraction of the whole. The cosmos built cathedrals of light, and then surrounded each one with moats of emptiness, millions of light years wide. It created a universe worth exploring, and then made exploration, in any galactic sense, physically impossible. This is not a limitation of human technology. It is a limitation of physics. The speed of light is not a speed limit that might someday be bypassed by better engineering. It is a fundamental property of space-time. Nothing that carries information or mass can exceed it within the framework of general relativity. And general relativity is the most thoroughly tested theory in the history of science. Speculative concepts like wormholes and warp drives exist as mathematical curiosities within the equations, but no physical evidence suggests they can be realized. And the energy requirements for even the most favorable theoretical models exceed the total energy output of stars. These are not doors waiting to be opened. They are equations waiting to be constrained by experiments that will almost certainly show they cannot describe real constructible objects. And so the universe remains what it has always been, an immensity that allows observation but forbids participation. A gallery whose paintings you can study but never enter. The distance to Andromeda is the first and most visceral expression of this truth, because Andromeda is the closest major galaxy, and it is already impossibly far. If the nearest painting is already behind glass so thick you cannot break it, then every other painting in the gallery is behind glass thicker still. The universe is not withholding intergalactic travel as a challenge to be overcome. It is expressing, through the geometry of its own structure, a fact about the relationship between matter, distance, and time that no amount of ingenuity can overrule. And yet Andromeda is approaching. This is the final paradox, the last twist that makes the story complete. Despite everything we have established about the impossibility of crossing the gap is closing on its own. Andromeda is moving toward the Milky Way at roughly 110 kilometers per second. The two galaxies are gravitationally bound and have been drawing toward each other for billions of years. Whether the outcome is a direct collision and merger, as models long predicted, or a series of close encounters and eventual coalescence, as the most recent simulations suggest, the result is the same. Billions of years from now, the two galaxies will interact, their stars will intermingle, their structures will reshape. The two largest members of the local group will become one, but that merger, when it comes, will not be a journey. No one will travel from here to there. No consciousness will cross the void. The galaxies will simply fall together underground, a process as mindless and impersonal as water flowing downhill. The stars of both galaxies are so widely spaced that virtually none of them will physically collide. Our sun, if it still exists, will be relocated to a different orbit within the merged structure, but it will not be destroyed. The night sky will change, Andromeda's stars will appear as individual points of light scattered among our own. 2 island galaxies will become one. The 2.5 million light years that once separated them will be compressed to zero, not by technology, not by ambition, not by human effort, but by the slow, patient, indifferent work of gravity operating across cosmic time. There is something almost mocking in that. The distance that is utterly impassable to any traveller will be erased by the universe itself, simply because it has billions of years to work with and no consciousness to grow impatient. Gravity does not care about the distance. Gravity does not feel the weight of 2.5 million light years. It simply pulls, second by second, millennium by millennium, epoch by epoch, until the gap closes. What is impossible for any living being is trivial for the cosmos. The universe can cross its own distances. We cannot. And that, in the end, is the terrifying truth this story has been building toward. The distance to Andromeda is not a fact about one galaxy. It is a fact about every galaxy. It is a fact about the structure of reality itself and the place of conscious beings within that structure. We live in a universe that permits intelligence, permits curiosity, permits the construction of telescopes and the measurement of cosmic distances, but does not permit the crossing of those distances on any scale larger than the local. We can see the universe. We can understand it. We can map its structures to the edges of the observable horizon, but we cannot enter it. We are confined to one galactic island, surrounded by an ocean of distance that no ship, no signal, no technology bound by the laws of physics can meaningfully cross. Andromeda hangs in the autumn sky tonight, the same faint smudge of silver light that Al-Sufi recorded 1,000 years ago. It looks close. It looks like a destination. It looks like the kind of place a sufficiently advanced civilization might someday reach, given enough time and ambition and ingenuity. But the light telling you it is there has been travelling for 2.5 million years. And when it reaches your eye, it carries a message that most of us spend our lives refusing to hear. The galaxy next door is not next door. It is 2.5 million light years away. It is 4 billion years away at our fastest speed. It is separated from us by a void so wide and so empty that the entire history of the human species fits inside the travel time of a single photon crossing it, and it is the closest one. Every other major galaxy in the universe is farther, many millions of times farther. The cosmos built its galaxies and then placed them at distances that turn the spaces between them into walls no living thing can climb. You're standing on a rock orbiting a star in a galaxy that contains 400 billion other stars. Across 2.5 million light years of darkness, another galaxy burns with 1 trillion suns. You can see it with your naked eye on any clear autumn night. It is the nearest major galaxy in the universe. And it is so far away that the word nearest means nothing, and the word journey means nothing. And the distance between you and the galaxy next door is not a gap to be crossed, but a boundary to be accepted. The universe is not a room you can walk across. It is an ocean you can see the far shore of but never swim to. And the far shore begins at Andromeda, 2.5 million light years away, visible, beautiful, knowable, and forever out of reach. 2 spacecraft built in the 1970s are at this exact moment travelling through a region of space where the sun's power fades and something far more hostile begins. They've been moving through the darkness for over 45 years and have barely crossed the first of several critical boundaries. What awaits beyond those boundaries is not simply more empty space. It is a radiation-saturated, particle-thin, magnetically alien environment that makes every planet and moon in our solar system look like a protected sanctuary by comparison. The sun has been shielding your planet from continuous galactic assault for the entire history of life on Earth, an assault of high-energy cosmic rays and interstellar plasma pressing inward from all directions. We cross that boundary together and examine exactly what the instruments actually found waiting on the other side. If you enjoy learning about space and the real science behind it, then a quick like and subscribe really does help this channel. Now, get yourself comfortable. Let's begin. Ask most people where our solar system ends. They will say Neptune. It is a reasonable answer. Neptune is the eighth and outermost of the recognized major planets, orbiting the Sun at an average distance of approximately 30 astronomical units, where 1 astronomical unit equals the average distance between Earth and the Sun, roughly 93 million miles. That number is difficult to hold in the mind. Light, traveling at approximately 186,000 miles per second, takes over 4 hours to cross it. The Voyager 2 spacecraft, launched in 1977 and flung outward through carefully calculated gravity assist maneuvers at Jupiter, Saturn, and Uranus, still needed 12 years of continuous travel to reach Neptune's neighborhood. By any measure built from human experience, Neptune sits at a distance so remote it barely registers as real, and yet it is not the edge, not even close. The solar system does not end at Neptune. It does not end at the Kuiper Belt, a broad, flattened disk of icy objects extending from roughly 30 to approximately 50 astronomical units from the Sun, home to hundreds of thousands of bodies larger than 100 kilometers across, including the dwarf planets Pluto, Eris, Makemake, and Haumea. It does not end at the scattered disk, that dynamically chaotic population of icy objects beyond the Kuiper Belt, whose orbits have been distorted by Neptune's gravitational influence over billions of years into steeply inclined, enormously elongated paths. None of these structures mark the physical limit of the Sun's reach. None of them represent a true boundary between our solar system and what lies beyond it. The boundary of our solar system is defined by something more fundamental, more precise, and dramatically more distant than any planet or belt of icy debris. It is defined by the Sun itself, not as a source of light and gravity, which extends technically without limit across all space, but as an active, continuously outputting physical object whose influence on the surrounding plasma environment has a measurable, definable outer edge. To understand what that edge is and how it works, you need to understand something that most people who learned about the solar system in a classroom were never told. The Sun does not simply sit in space and shine. Every single second of every single day, it breathes matter into the space around it, and that breath defines our home in a way that nothing else does. The Sun's outer atmosphere is called the corona. It extends millions of kilometers above the visible solar surface. The photosphere and its properties are so extreme they initially seem contradictory. The photosphere, the bright surface of the Sun you see when you look at it through a solar filter, has a temperature of approximately 5,800 Kelvin. As you move upward through the chromosphere and into the corona, the temperature does not decrease as you would expect when moving away from a heat source. It rises dramatically. The corona reaches temperatures exceeding 1 million Kelvin, approximately 170 times hotter than the visible surface directly below it. The precise mechanism responsible for this counterintuitive heating has been one of the central unsolved problems in solar physics for decades. While leading theories point to the dissipation of magnetohydrodynamic waves propagating upward through the solar atmosphere, the full picture remains an area of active research. What matters for our story is what those extraordinary coronal temperatures produce. At 1 million Kelvin, the thermal energy of individual electrons and protons in the corona exceeds the gravitational binding energy that would otherwise hold them in place close to the Sun. The particles are simply moving too fast for the Sun's gravity to restrain them at that altitude. The result is a continuous, permanent outflow of charged particles, primarily protons and electrons, with smaller contributions from helium ions and trace amounts of heavier elements, streaming radially outward from the Sun in all directions at speeds between approximately 250 and 500 miles per second under typical conditions. This outflow is the solar wind. It is not occasional. It is not intermittent. The solar wind has been blowing continuously for the entire 4.5 billion year lifetime of the Sun, and it will continue for approximately another 5 billion years until the Sun exhausts its hydrogen fuel, expands into a red giant and fundamentally changes its character. Every single second, the Sun's outer atmosphere, the corona expels approximately 1 million tons of charged particles outward into space in all directions. Over the entire history of the solar system, the Sun has lost a total mass roughly equivalent to approximately 1/4 of the mass of Saturn through this continuous outpouring, a tiny fraction of its total mass, but a staggering quantity of material when considered in absolute terms. The solar wind carries with it something even more consequential than matter. It carries the Sun's magnetic field. The corona is a plasma, an electrically conducting gas. In such a medium, the magnetic field behaves differently than it does in ordinary materials. In a perfectly conducting plasma, the magnetic field lines are effectively frozen into the material. They cannot diffuse through the plasma independently. They must move with it. This principle, called magnetic flux freezing or the ideal magnetohydrodynamic approximation, means that as the solar wind streams outward from the Sun, it drags the Sun's magnetic field along with it, stretching those field lines away from the solar surface, carrying them outward into the surrounding space. Now add the Sun's rotation. The Sun completes approximately one rotation every 25 to 27 days. Depending on latitude, it rotates faster at the equator than at the poles, a consequence of being a gaseous body rather than a solid one. As the solar wind streams outward while the Sun rotates beneath it, the magnetic field lines being carried outward are wound into a large-scale spiral pattern. In the same way that water from a rotating garden sprinkler traces a spiral on the lawn rather than a straight radial line. The result is a structure called the Parker spiral, named for astrophysicist Eugene Parker, who mathematically predicted its existence in 1958, an idea so seemingly audacious at the time that the reviewers of his original submitted paper rejected it as physically impossible, which was confirmed by direct spacecraft measurement just 4 years later by the Mariner 2 mission en route to Venus. The Parker spiral is not merely a geometric curiosity, it is the magnetic architecture of the entire solar system. Every planet, every moon, every asteroid, every comet, every spacecraft humanity has ever launched exists within this spiraling, magnetized outflow. The solar wind and its embedded magnetic field fill every cubic kilometer of space within an enormous bubble surrounding the Sun, a bubble whose physical properties are fundamentally different from the space outside it. This bubble has a name, the heliosphere. The concept the heliosphere represents is straightforward even if its physics are complex. The Sun is constantly inflating and maintaining a vast region of space filled with its own plasma and its own magnetic field, pressing outward against the surrounding interstellar medium of the galaxy. Everything inside this bubble exists within an environment, actively created and maintained by the Sun. Everything outside it exists in a different physical environment, entirely, one governed not by our star but by the collective processes of the galaxy itself. The heliosphere is not a perfect sphere. Its shape responds to the structure of the surrounding interstellar medium and to the Sun's variable output. The side facing the direction of the solar system's motion through the galaxy, called the nose, is compressed by the ram pressure of the interstellar medium flowing past, in the same way that the front of a moving boat compresses the water ahead of it. The trailing side, the tail, or heliotail, extends downstream in the direction away from the solar system's motion, stretched out by the combined effect of the solar wind's outward pressure and the heliosphere's motion through the surrounding medium. Early models predicted an extremely elongated comet-shaped heliosphere with an enormous tail extending perhaps several thousand astronomical units downstream. More recent data from NASA's Interstellar Boundary Explorer satellite, which has been observing the heliospheric boundary remotely from Earth orbit since 2008, suggests the actual shape is more complex, possibly more rounded than the comet model predicted, with magnetic lobes and structural features that early models did not capture. The precise shape of the heliosphere's tail remains an area of ongoing scientific investigation. The heliosphere is also not static. It breathes in rhythm with the sun's approximately 11-year activity cycle. Every 11 years, the sun oscillates between a period of relative calm solar minimum, characterized by fewer sunspots, a quieter corona, and a less vigorous solar wind and solar maximum, characterized by intense flaring activity, frequent coronal mass ejections, and a generally denser, faster, more energetically charged solar wind. During solar maximum, the increased outward pressure from the more vigorous solar wind pushes the heliosphere's outer boundary. During solar minimum, the reduced outward pressure allows the surrounding interstellar medium to compress the heliosphere slightly inward. The boundary of our solar system literally contracts and expands by tens of astronomical units over the course of each solar cycle. The edge of our home is not fixed. It is a dynamic equilibrium that responds to the sun's heartbeat. As the solar wind travels outward from the sun, it gradually loses energy. It thins out over the ever-increasing surface area of the expanded sphere it must fill. Its particle density falls with the square of the distance. Its temperature drops. Its speed decreases. By the time the solar wind has traveled to the outer solar system somewhere in the range of 75 to approximately 94 astronomical units from the sun, depending on the direction and the current phase of the solar activity cycle, something physically dramatic happens. The solar wind, which has been traveling outward at supersonic speeds throughout the entire planetary region of the solar system, abruptly slows down. To understand why this is significant, we need to understand what supersonic means in this context. Sound speed in a plasma is not the same as sound speed in air. It is determined by the plasma's temperature, density, and magnetic field strength. The solar wind, for most of its journey from the sun to the outer solar system, travels faster than the natural wave speed in the medium it is moving through. This is the definition of supersonic flow. When a supersonic flow encounters an obstacle it cannot push through in this case, the pressure of the surrounding interstellar medium, it cannot gradually slow down and adjust. The information about the obstacle travels at the wave speed of the medium, which is slower than the supersonic flow approaching it. The result is a shock wave, a thin region where the flow transitions abruptly from supersonic to subsonic, and where the kinetic energy of the bulk supersonic flow is converted into heat, magnetic turbulence, and particle acceleration. This standing shock wave in the outer heliosphere is called the termination shock. It is one of the most important boundaries in the solar system, and it sat entirely beyond human direct observation until November of 2004, when NASA's Voyager 1 spacecraft crossed it at approximately 94 astronomical units from the Sun. The data from Voyager 1 and the termination shock were exactly what theory predicted, and the confirmation was enormously satisfying to the scientists who had spent decades waiting for it. The solar wind velocity dropped from approximately 250 miles per second to approximately 80 miles per second, a reduction by a factor of roughly 3 in the thin crossing region. The plasma temperature jumped sharply as the kinetic energy of the bulk flow was converted into thermal energy. The magnetic field became compressed and disordered, its smooth Parker spiral geometry disrupted by the shock's turbulence. The density of the solar wind plasma increased. Every instrument reading was consistent with the signatures of a supersonic to subsonic transition, confirming that Voyager 1 had passed through the termination shock. The asymmetric termination shock distances already established by both spacecraft 94 astronomical units on Voyager 1's side, 84 on Voyager 2's, had confirmed the heliosphere was genuinely asymmetric. That same asymmetry now extended outward through the heliosheath itself. The termination shock is closer to the Sun on one side than the other, reflecting the uneven pressure of the surrounding interstellar medium. The interstellar medium is not pressing equally on all sides of the heliosphere. It has a preferred direction, organized by the local interstellar magnetic field and the flow of the local interstellar cloud relative to the solar system. Our protective bubble is pushed in, slightly but measurably, on the side facing into the interstellar headwind. Beyond the termination shock lies a region that neither spacecraft had ever previously sampled, a zone of turbulent, heated, slowed, magnetically disordered solar plasma that has passed through the shock and is now being redirected by the interstellar medium pressing in from outside. This region is called the heliosheath. It is not a thin transition layer. It is a thick, physically complex buffer zone that both Voyager spacecraft spent years traversing. Voyager 1 crossed the termination shock in 2004 and did not reach the outer boundary of the heliosheath until 2012, 8 years of travel through this intermediate region, covering approximately 30 astronomical units. Voyager 2 crossed the termination shock in 2007 and reached the outer boundary in 2018, 11 years in the heliosheath. Both spacecraft collected invaluable data during these traversals, revealing a region far stranger and more physically complex than pre-mission models had predicted. One of the most striking discoveries in the heliosheath was the behavior of galactic cosmic rays. As Voyager 1 moved outward through the heliosheath toward the outer boundary, its cosmic ray instruments recorded a pattern unlike the smooth, gradual increase that simpler models had anticipated. Instead, the stepwise cosmic ray pattern already established throughout the heliosheath traversal continued toward its conclusion. Each layer of magnetic structure providing slightly less shielding than the one before it, the barriers thinning as the heliopause approached. The heliosheath was announcing its own end through the instruments. Simultaneously, the instruments measuring solar energetic particles, the high-energy protons and electrons, accelerated by the sun's flares and coronal mass ejections, and flung outward through the heliosphere, showed a complementary decline. As Voyager 1 approached the outer edge of the heliosheath, solar energetic particle intensities dropped progressively, absorbed and scattered by the magnetic structures of the outer heliosphere before they could reach the spacecraft. These two trends, galactic cosmic rays rising in steps, solar energetic particles falling, were converging toward a dramatic meeting point that both spacecraft would eventually reach. But before describing that meeting point, we need to understand what the heliosphere's architecture is actually protecting against, because most people have never been told. The answer is genuinely alarming. The space beyond the heliosphere is filled with galactic cosmic rays. These are not a gentle background radiation similar to the natural radioactivity of rocks and soil that living things on Earth have been accustomed to for billions of years. Galactic cosmic rays are individual atomic nuclei that have been accelerated by astrophysical processes to velocities approaching the speed of light. The typical galactic cosmic ray is a proton carrying approximately 1 billion electron volts of kinetic energy. The most extreme examples detected at ground-based observatories carry individual particle energies exceeding 10 to the 20th power electron volts, a quantity that becomes physically comprehensible when expressed as approximately the kinetic energy of a baseball thrown by a professional pitcher, concentrated into a single subatomic particle, moving at a velocity indistinguishable from light speed. These particles originate primarily from supernova remnants distributed throughout the Milky Way. When a massive star exhausts its nuclear fuel and detonates in a core-collapse supernova, the expanding shockwave tears through the surrounding interstellar medium at velocities of thousands of miles per second. Charged particles, protons, helium nuclei, the nuclei of heavier elements interact with this shockwave repeatedly, bouncing back and forth across the shock front in a process called diffusive shock acceleration. Each crossing of the shock adds energy to the particle. Over thousands of years of these repeated interactions, a fraction of the particle population accumulates enough energy to escape the shock entirely and stream outward into the broader galaxy. The galactic cosmic ray population, a cumulative product of millions of years of supernova remnant acceleration already described, fills the entire galaxy as an approximately isotropic background flux. The heliosphere does not block galactic cosmic rays completely. What it does is modulate them and reduce their intensity, particularly for lower energy particles, with a scattering and deflecting effect through Parker's spiral magnetic field. A cosmic ray proton trying to travel inward through the heliosphere does not travel in a straight line. The magnetic field scatter off magnetic irregularities and random walk inward rather than streaming freely. For lower energy cosmic rays, this process is so effective that their intensity inside the heliosphere is significantly reduced compared to the interstellar level. For higher energy particles, whose trajectories are less deflected by the heliospheric field strength, the reduction is smaller. What the Voyager missions directly confirmed is that the intensity of galactic cosmic rays at 1 astronomical unit, the distance from the Sun where Earth orbits, is roughly half of what it is in the interstellar medium, immediately outside the heliopause. Our planet's entire evolutionary history, the development of every living thing that has ever existed on Earth, has occurred inside a magnetic bubble that reduces the cosmic ray background by approximately 50% compared to what the interstellar medium delivers. That is not a trivial difference. Galactic cosmic rays are a significant source of genetic mutation. They penetrate biological tissue, deposit ionizing energy along their tracks through cells, enrich DNA. A planet receiving twice the galactic cosmic ray flux of Earth over billions of years would face a different biological mutation landscape. The heliosphere is not an interest in astrophysics. It is a component of the conditions under which life here became possible. The heliosphere also deflects the interstellar neutral gas flow. The local interstellar cloud, the specific region of interstellar gas in which our solar system is currently embedded, is moving relative to the Sun at approximately 52,000 miles per hour. Neutral hydrogen and helium atoms from this cloud can penetrate the heliosphere because they are electrically neutral and therefore not deflected by the heliospheric magnetic field. They stream inward freely and have been detected directly by spacecraft instruments, including the Interstellar Boundary Explorer satellite. But the plasma component of the interstellar medium, the ionized portion, which constitutes roughly 20 to 30% of the local interstellar cloud, cannot penetrate the heliopause. The heliospheric magnetic field and the pressure balance of the outer boundary deflect the interstellar plasma around the heliosphere rather than allowing it to flow inward. Without the heliosphere, the inner solar system would be bathed in interstellar plasma of a character fundamentally different from the solar wind environment that has characterized it for 4.5 billion years. All of these protective functions, cosmic ray modulation, interstellar plasma deflection, the provision of a magnetically structured plasma environment, distinct from the broader interstellar medium, emerge from one continuous physical process. The Sun blowing its wind outward and maintaining the pressure balance at the heliosphere's outer boundary. Every day that the Sun continues to output its solar wind, the heliosphere persists, the boundary holds. The protection continues. This has been the case since before the Earth had oceans. The full scale of this protective structure deserves to be stated precisely, because imprecision here obscures something important. The heliosphere, measured to its outer boundary, extends approximately 120 astronomical units from the Sun in the direction of the interstellar headwind, the nose side, and likely farther on the downstream tail side, though the exact extent of the tail remains uncertain. 120 astronomical units equals approximately 11 billion miles. To cross from the Sun to the heliopause at the speed of a commercial airliner, approximately 560 miles per hour would require approximately 2.2 million years. Light itself, traveling at 186,000 miles per second, takes approximately 16.6 hours to make the crossing. Neptune, the outermost planet, sits at 30 astronomical units. The heliopause is at approximately 120. Everything between Neptune's orbit and the heliopause, a vast annular volume of space containing the Kuiper Belt, the scattered disk, tens of billions of miles of effectively empty solar wind-filled space sits comfortably within the Sun's protective domain. Even the hypothetical Oort cloud, the distant spherical reservoir of comets believed to extend from approximately 2,000 to perhaps 100,000 astronomical units, may have its inner regions partially within or near the heliospheric influence, though the outer Oort cloud is almost certainly beyond any meaningful solar protection. It is worth pausing to recognize how thoroughly this picture overturns the intuitive model of the solar system that most people carry. In the common mental image, the solar system is the planets. Beyond Neptune, there is perhaps a vague awareness of Pluto, and then space becomes foreign territory. The reality is that the solar system, defined by the sun's physical reach, by the domain of its plasma and magnetic field, extends approximately 4 times farther than Neptune, encompassing a volume of space 800 times larger than the sphere bounded by Neptune's orbit. We live in a solar system whose true size dwarfs what astronomy textbooks typically communicate, and whose protective function extends to distances that no planetary mission has ever been designed to reach. The termination shock at approximately 90 astronomical units marks the first major boundary within this vast domain, the point where the solar wind's supersonic flow gives way to the turbulent, compressed, heated plasma of the heliosheath. The heliosheath itself extends another 30 to 40 astronomical units outward, a thick buffer zone of disordered solar plasma that has passed through the shock and is being gradually turned and mixed by the opposing pressure of the surrounding galaxy. And at the outer edge of the heliosheath, approximately 120 astronomical units from the Sun, lies the boundary that changes everything. The boundary where the Sun's plasma ends and the galaxy's plasma begins. The boundary where the heliosphere terminates and interstellar space commences. The boundary that 2 spacecraft have now crossed and returned, or rather, transmitted data from, the heliopause. Understanding what the Voyager missions found at and beyond that boundary, and what the instruments measured in the moments of crossing, reveals something far more dramatic than any simple description of the boundary can convey. The heliopause is not a gradual fade. It is not a transition region where solar conditions slowly become interstellar conditions over thousands of astronomical units. The spacecraft data shows it to be sharp, physically distinct, and surprisingly thin. On one side, solar plasma, solar magnetic field, the extended domain of a star. On the other side, something categorically different, something that has never been touched by our sun, something that has been filling the spaces between the stars for longer than the solar system has existed. What waits on the other side is not simply more space, it is the galaxy itself, direct physical contact with our instruments for the first time. And the measurements that both spacecraft made in the moments of and immediately following their crossings tell a story that no description of the heliosphere's interior can fully prepare you for. 8 years is a long time to travel through a single region of space. Voyager 1 crossed the termination shock in approximately 2004, entering the heliosheath, that thick, turbulent buffer zone of slowed, compressed, heated solar plasma that lies between the termination shock and the outer heliospheric boundary. From that moment, its instruments reflected data from a region no spacecraft had ever previously sampled, transmitting measurements back to Earth across distances so enormous that each signal, travelling at the speed of light, required over 13 hours to arrive. The spacecraft was functioning on computing systems designed in the early 1970s, running on approximately 280 watts of electrical power, generated by decaying plutonium, enough to power a few household light bulbs, and transmitting its data home on a signal of just 22 watts. Pointed at Earth by a 3.7 meter dish antenna, was returning data at a rate slower than the dial-up internet connections of the 1990s. For 8 years, crossing approximately 30 astronomical units of the heliosheath, it kept transmitting. What those 8 years of heliosheath data revealed was an environment far more complex than the relatively smooth, gradually weakening solar wind environment in the heliosphere. The heliosheath was structured, turbulent, and full of surprises. The solar plasma within it was not simply slow and hot, though it was both of those things. The bulk solar wind velocity having dropped from roughly 300 miles per second before the termination shock to approximately 100 miles per second afterward, and the plasma temperature having jumped sharply at the shock crossing. Within the heliosheath, the plasma was also being continuously redirected. The outward radial flow of the solar wind, which had been the defining motion of the plasma for the entire journey, from the sun to the termination shock, was gradually being turned by the interstellar medium's pressure. The Plasma was being bent deflected from its radial outward path toward a downstream direction, being swept toward the heliotail rather than continuing to press outward symmetrically in all directions. This deflection was not uniform, and the instruments captured its variability in remarkable detail. The magnetic field within the heliosheath showed none of the smooth Parker spiral organization that characterizes the inner heliospheric field. It was disordered, folded back on itself, turbulent at multiple scales simultaneously. The termination shock had randomized the field's direction, and the compression of the outer heliosheath by the surrounding interstellar medium introduced additional structural complexity. The plasma flow within the heliosheath carried magnetic field lines that were being tangled, compressed, and in some regions reconnected, a process in which opposing magnetic field lines break and reconnect in new configurations, releasing stored magnetic energy and accelerating particles in the process. Magnetic foam structures already detected throughout the outer heliosheath, those discrete reconnected magnetic bubbles whose existence no pre-mission model had predicted, continued to influence cosmic ray penetration. During this period, scattering lower energy particles in ways that smooth field models could not accurately replicate, those models had generally assumed the outer heliosphere would contain a progressively weaker, smoother version of the inner heliospheric field. The reality was more physically interesting and more consequential for the heliosphere's protective function. Magnetic foam provides a different kind of shielding against galactic cosmic ray penetration than a smooth, coherent field does. Cosmic ray particles entering a foamy magnetic environment encounter a complex maze of closed field lines and reconnection boundaries that scatter them in ways that smooth field models cannot accurately predict. Understanding the actual magnetic structure of the outer heliosphere turned out to be essential for accurately modeling how cosmic rays penetrate inward toward the planets. Through all of this, Voyager 1's cosmic ray instruments were tracking the stepwise increase in galactic cosmic ray intensity, described in the previous section, each step corresponding to the spacecraft, crossing a boundary between magnetic structures in the heliosheath, each step bringing the measured cosmic ray flux closer to its full interstellar value. And simultaneously, the solar energetic particle instruments continued recording the same progressive decline, the sun's reach fading instrument reading by instrument reading as the heliopause drew closer. Both trends were approaching their final values simultaneously, the instruments counting down from opposite directions toward the same boundary. The only question was exactly when and at what distance the crossing would occur. The answer came in the summer of 2012. In late July and early August of 2012, Voyager 1's instruments recorded a set of changes that, in retrospect, marked the definitive crossing of the heliopause. The galactic cosmic ray intensity, which had been climbing in the characteristic stepwise pattern throughout the heliosheath, made a final sharp jump, not a step like the ones before it, but an abrupt, sustained rise to a new stable level that did not subsequently decrease. Simultaneously, the solar energetic particle flux, which had been declining throughout the heliosheath, dropped to essentially zero. Not to a very low level, not to a reduced level, zero. The sun's energetic particles, which had been detectable throughout the entire journey from Earth to the outer heliosphere, vanished from the instruments. These two changes, the cosmic ray jump and the solar energetic particle disappearance, occurred within approximately 3 days of each other in early August 2012. The convergence was exactly what the theory had predicted. The instruments had been counting down, and they had hit zero simultaneously from opposite directions at the same location in space. But scientists wanted corroboration beyond the particle data before announcing that Voyager 1 had crossed into interstellar space, the expected signature that many had anticipated most strongly, a clear rotation in the direction of the magnetic field. From the solar field's orientation to the interstellar field's orientation did not materialize clearly at the August crossing point. The magnetic field direction did change somewhat at the crossing, but not by the dramatic angle that many models had predicted. This unexpected behavior in the magnetic field created genuine scientific uncertainty about the interpretation of the August 2012 data. The team spent over a year carefully analysing what they had measured before publishing their conclusions. The confirmation came from an entirely different type of measurement, one that required waiting for a specific event to occur. The Sun periodically produces large-scale pressure disturbances in the solar wind called global merged interaction regions that form when multiple coronal mass ejections and high-speed solar wind streams merge over time as they travel outward, creating a coherent high-pressure wave that propagates through the heliosphere. Such a wave reached Voyager 1's location in April of 2013. When the wave arrived, it compressed the local plasma and caused it to oscillate at its characteristic resonant frequency, plasma frequency, which depends directly on the local electron density. Voyager 1's plasma wave instrument detected these oscillations and measured their frequency precisely. The calculation was straightforward. From the measured plasma oscillation frequency, the local electron density could be derived. The result was approximately 80 electrons per cubic centimeter, a value approximately 40 times higher than the electron density, measured by the same technique inside the heliosheath shortly before the crossing. This dramatic density jump was unambiguous. The plasma immediately surrounding Voyager 1 was not thinned out, rarefied solar wind plasma. It was the denser, partially ionized plasma of the local interstellar cloud. Voyager 1 was definitively in interstellar space. The team published their conclusion in the journal Science in September 2013. The crossing had occurred in late August 2012, at a distance of approximately 121.6 astronomical units from the Sun. The heliopause had been crossed. For the first time in history, a human-made object had left the Sun's domain and entered interstellar medium. 6 years later, Voyager 2 provided a second crossing, and in many ways, a scientifically richer one, because Voyager 2 carried an instrument that Voyager 1 did not, a functioning plasma science instrument capable of directly measuring the solar wind, velocity, temperature, and density in real time. Voyager 1's plasma science instrument had failed in 1980, 37 years before it would have reached the heliopause. The loss was significant. It meant that at the most important moment of the mission, the crossing of the last boundary between the solar system and interstellar space, Voyager 1 could not directly measure the plasma properties on either side of the transition. The electron density measurement from plasma wave oscillations provided crucial information, but it was an indirect technique, available only when a specific type of solar disturbance happened to arrive at the spacecraft's location. Direct plasma measurements at the crossing itself were impossible. Voyager 2 crossed the heliopause on November 5, 2018, at approximately 119 astronomical units. Its plasma science instrument was operational and collecting data throughout the crossing. The results were extraordinary. The solar wind velocity, which had been approximately 95 miles per second coming out of the heliosheath just before the crossing, dropped to essentially zero within the heliopause boundary layer. This was not a gradual deceleration spread over tens of astronomical units. The solar wind, the continuous outflow of solar plasma that had been the defining physical feature of the spacecraft's entire journey from Earth, stopped within a boundary layer estimated to be less than approximately 0.1 astronomical units thick, less than approximately 9 million miles. On one side of that 9 million mile layer, the solar wind was full. On the other side, it was absent. The sun's breath ended there, as sharply as if a valve had been closed. The corresponding behavior of the cosmic ray and energetic particle instruments matched Voyager 1's experience precisely. The galactic cosmic ray flux jumped to its full interstellar level. The solar energetic particle flux dropped to zero. Both changes occurred in the same location as the solar wind velocity drop at the same sharp boundary, within the same thin crossing region. 3 independent measurements, 3 independent instrument types, all converging on the same boundary at the same distance. Voyager 2's plasma science instrument also provided the first direct measurement of the temperature of the interstellar plasma immediately outside the heliopause. The interstellar electron temperature in the local interstellar cloud, just beyond the boundary, was measured at approximately 30,000 to 50,000 Kelvin. This number is worth examining carefully because it contains a surprise. The plasma just outside the heliopause in the interstellar medium is actually cooler in terms of individual particle temperatures than the plasma just inside the heliopause in the outer heliosheath. The compressed, shock-heated solar plasma of the heliosheath reaches temperatures approaching 1 million Kelvin. The interstellar plasma outside measures 30,000 to 50,000 Kelvin. Crossing the heliopause outward means moving from hotter individual particles to cooler ones, but into an environment that is nonetheless fundamentally more hostile because the nature of the threat changes entirely from thermal to radiative. Voyager 2's magnetometer provided another crucial measurement: the interstellar magnetic field strength immediately outside the heliopause. The field measured approximately 0.4 nanotesla, enormously weaker than Earth's surface magnetic field of approximately 50,000 nanotesla, and significantly weaker than the solar magnetic field at Earth's orbital distance of approximately 5 nanotesla. To put this in perspective, the interstellar magnetic field threading the local interstellar cloud is roughly 100,000 times weaker than the magnetic field at Earth's surface. It is so weak that human instruments capable of measuring it had to be designed with extraordinary sensitivity. And yet this extraordinarily weak field organizes the flow of interstellar plasma across distances of light years, and channels the propagation of galactic cosmic rays across the entire local galactic neighborhood. The magnetometer data also revealed something physically intriguing about the heliopause itself. The interstellar magnetic field direction measured just outside the heliopause, pointing approximately toward the galactic plane, differed only slightly from the direction of the solar magnetic field measured just inside the outer heliosheath. This small difference explained why the magnetic field rotation at the heliopause had been less dramatic than many pre-mission models predicted. The interstellar magnetic field in the local interstellar cloud is roughly aligned with the heliospheric field at the crossing point, rather than being oriented at a large angle to it. This alignment is not coincidental. The interstellar magnetic field partially controls the orientation of the heliosphere itself, contributing to the pressure that shapes the heliopause and influencing the direction in which the heliospheric current sheet, the vast, wavy surface separating regions of opposite solar magnetic polarity within the heliosphere, is oriented. The heliospheric current sheet deserves a brief explanation because it is one of the solar system's most remarkable structural features, and one whose effects extend all the way to the heliopause. The Sun's magnetic field has two hemispheres of opposite polarity, a north magnetic hemisphere and a south magnetic hemisphere, analogous in a very rough sense to the north and south poles of a bar magnet, though the solar field is far more complex. The boundary between these two hemispheres, carried outward by the solar wind, forms a vast undulating surface called the heliospheric current sheet. Because the Sun's magnetic axis is tilted relative to its rotation axis, the current sheet is not flat, it is warped into a wavy, rippled surface that rotates with the Sun, creating a structure that has been described visually as resembling a ballerina's spinning skirt. The current sheet extends throughout the spacecraft also activates the Sun rotates to detect alternating sectors of inward and outward magnetic field polarity. In the outer heliosheath, the current sheet becomes compressed by the surrounding interstellar pressure, contributing to the magnetic complexity that both Voyager spacecraft detected in that region. Near the heliopause, the current sheet is further distorted by the interaction with the interstellar magnetic field draping around the heliosphere's outer boundary. The interplay between the heliospheric current sheet and the interstellar field at the heliopause contributes to the structural details of the crossing, including the thin boundary layer of anomalously high plasma temperature that Voyager 2 detected just inside the heliopause during its crossing. That anomalous boundary layer, a thin zone of extremely high plasma temperature detected by Voyager 2 between the outer heliosheath and the heliopause proper, was one of the most scientifically intriguing discoveries of crossing. In the crossing data, The instruments detected a region roughly 0.3 astronomical units thick just inside the heliopause, where the plasma temperature was dramatically higher than either the general heliosheath temperature or the interstellar temperature outside. This localized heating is consistent with theoretical predictions of intense magnetic reconnection occurring at the heliopause boundary, a process in which the solar magnetic field and the interstellar magnetic field press together at the contact surface, break and reconnect in new configurations, releasing stored magnetic energy that heats the local plasma. The heliopause is not simply a passive pressure balance surface. It is an active site of magnetic interaction between the Sun's magnetic domain and the galaxies. Both crossings, Voyager 1 in 2012, Voyager 2 in 2018, also confirmed something important about the geometry of the heliopause relative to the termination shock. Voyager 1 crossed the termination shock at approximately 94 astronomical units, and the heliopause at approximately 121 astronomical units, a heliosheath thickness of approximately 27 astronomical units on that side of the heliosphere. Voyager 2 crossed the termination shock at approximately 84 astronomical units, and the heliopause at approximately 119 astronomical units, a heliosheath thickness of approximately 35 astronomical units on the side. The heliosheath is not the same thickness in all directions. It is thinner on the nose side, the side facing into the interstellar headwind, where the interstellar medium's ram pressure compresses the heliosheath most effectively. Thicker on the flanks and tail side, where the pressure is lower, the asymmetry extends through every layer of the heliosphere, from the termination shock inward to the heliopause outward. Voyager 1 is currently traveling in the general direction of the constellation Ophiuchus, roughly toward the nose side of the heliosphere, the upstream direction of the interstellar wind. Voyager 2 is traveling in a direction roughly toward the southern hemisphere of the heliosphere, at a substantial angle from Voyager 1's path. The fact that two spacecraft traveling in significantly different directions both cross the heliopause at distances within a few astronomical units of each other provides confidence that the heliopause is a roughly consistent boundary in terms of distance, even accounting for the measured asymmetry. The heliosphere does not have a dramatically thin side and a dramatically thick side. It has a modestly compressed nose and a modestly extended tail, and both Voyager crossings sampled the mid-latitude flanks of this overall structure at distances that are broadly representative of the heliopause's general location. After crossing the heliopause, both spacecraft continued transmitting data. Voyager 1, as of the time of writing, is at approximately 160 astronomical units from the Sun, 40 astronomical units beyond the heliopause, measuring properties of the local interstellar medium at the greatest distance from Earth ever achieved by any human technology. Voyager 2 is at approximately 130 astronomical units, approximately 10 to 15 astronomical units, beyond its heliopause crossing point, sampling the interstellar medium at a different location and different direction than Voyager 1. The data both spacecraft have returned from beyond the heliopause has been consistent and mutually confirming. Galactic cosmic ray fluxes are stable at their elevated interstellar levels. Solar energetic particles are absent. The solar wind is undetectable as a bulk flow. Plasma properties match those of the local interstellar cloud within measurement uncertainties. The magnetic field is weak, stable, and organized by interstellar rather than solar processes. Neither spacecraft has detected any evidence of a bow shock, a shock wave that some models predicted would form upstream of the heliosphere, where the interstellar wind rams into it. The absence of a detectable bow shock suggests that the interstellar medium in our immediate neighborhood is moving relative to the solar system too slowly to create a supersonic shock upstream of the heliopause, though the question remains partially open as measurements continue. What the heliopause crossing data from both Voyager missions reveals, taken together, is a boundary that is real, sharp, physically distinct, and thinner than many pre-mission models anticipated. The transition from heliospheric plasma to interstellar plasma occurs within a boundary layer of only a few tenths of an astronomical unit, a few tens of millions of miles. At Voyager speeds, both spacecraft cross this layer in a matter of days to weeks. On one side, the Sun's plasma, the Sun's magnetic field, elevated solar energetic particle intensities, reduced galactic cosmic ray flux. On the other side, interstellar plasma, interstellar magnetic field, zero solar energetic particles, full galactic cosmic ray intensity. The boundary is not gradual, it is a wall. Once crossed, there is no ambiguity about which side you are on. This sharpness matters for several reasons beyond its intrinsic scientific interest. It means that the heliosphere's protective function does not fade gradually over tens or hundreds of astronomical units. It ends. A spacecraft at 120 astronomical units is inside the heliosphere and enjoys all the protections that it implies. A spacecraft at 121 astronomical units is in the interstellar medium and is exposed to the full galactic cosmic ray background, the full interstellar plasma environment, and the complete absence of solar energetic particle input. The transition between these two states happens within approximately a distance that light crosses in approximately 48 seconds. The universe has a sharp edge here, and both Voyager spacecraft have confirmed exactly where it sits. For any future mission designed to operate beyond the heliopause, whether a dedicated interstellar probe carrying more advanced instruments than the Voyager spacecraft, a generation ship intended for eventual stellar transit, or any other object meant to function in the interstellar medium, the heliopause crossing defines a fundamental mission phase transition. Before crossing, operating in a heliospheric environment with familiar properties shaped by decades of spacecraft observations. After crossing, operating in an environment whose properties are characterized only by the limited data returned by two-agent spacecraft, by remote sensing observations that cannot replace in situ measurement. The interstellar medium immediately beyond the heliopause is the least directly characterized environment that human technology has ever encountered, and the measurements that define it come from instruments that were never designed to survive this long or travel this far. Both Voyager spacecraft are losing power. Each radioisotope thermoelectric generator loses approximately 4 watts of electrical output per year as the plutonium-238 fuel decays. Both spacecraft have already shut down multiple instruments to conserve power for the instruments considered most scientifically valuable in their current environment. Voyager 1 has turned off its camera system, its ultraviolet spectrometer, and its low-energy charged particle instrument, among others. Voyager 2 has made similar power conservation decisions. Mission teams estimate that one or both spacecraft may lose the ability to power their remaining instruments sometime around the late 2020s or early 2030s, ending the data return from the only human-made objects that have directly sampled the interstellar medium. When those transmissions finally cease, humanity will lose its own in-situ sensors beyond the heliopause. The interstellar medium will return to being characterized entirely by remote observation, spectroscopy, starlight absorption, energetic neutral atom imaging from Earth orbit, theoretical modeling constrained by the Voyager data. The direct measurement window opened by the Voyager missions will close, and what will remain is a set of irreplaceable measurements from 2 specific locations, 2 specific trajectories through the immediate heliospheric vicinity, a data set that will be analyzed and reanalyzed for decades, but that cannot be expanded without a new mission. The physical environment those measurements have revealed, the interstellar medium and the local interstellar cloud in the immediate vicinity of the heliosphere, is the subject of what comes next. Because understanding what the heliopause separates our solar system from requires characterizing the interstellar medium not just as measured by the brief Voyager crossings, but as an extended environment with specific, quantifiable properties that make it fundamentally different from anything inside the heliosphere: the particle density, the radiation field, the magnetic structure, the temperature, the absence of anything resembling solar protection. The interstellar medium is not simply space with the solar wind removed. It is a different physical regime, governed by different dominant processes, presenting different challenges to any unprotected object within it. And understanding those challenges in precise physical terms, not in vague descriptions of darkness or emptiness, but in actual measured quantities with actual physical consequences, is what reveals why the boundary both Voyager spacecraft crossed represents something more than a line on an astronomical chart. It represents the edge of the only cosmic environment in which life on this planet has ever existed. The word environment implies something habitable. A forest is an environment. A coral reef is an environment. Even the surface of Mars, barren, radiated, bitterly cold. With an atmosphere too thin to breathe and soil chemistry toxic to unprotected biology, qualifies as an environment in the sense that it has a definable set of physical properties that a sufficiently robust piece of engineering could, in principle, be designed to survive within. The interstellar medium beyond the heliopause challenges even this expansive definition. It is not simply hostile in the way that planetary surfaces, deep space within the heliosphere are hostile. It is hostile in kind, a physically distinct region, governed by processes that have no meaningful analog within the solar system, presenting challenges that no spacecraft has yet been engineered to address, and that no biological organism has ever encountered and survived. To understand precisely why, the dramatic boundary crossings must give way to the actual measured physical properties of the environment the Voyager spacecraft entered, because the numbers are where the true hostility lies, not vague descriptions, not poetic language about the void, actual numbers, actual densities, actual radiation levels, actual magnetic field structures, because the numbers are where the true hostility lives, and the numbers are more extreme than most descriptions of interstellar space convey. Begin with the structure of where we are. Our solar system currently sits inside a specific, named region of the interstellar medium called the local interstellar cloud, sometimes referred to informally as the local fluff, a name that feels almost comically inadequate once you understand what it actually contains. The local interstellar cloud is a region of partially ionized interstellar gas, approximately 30 light-years in its longest dimension, and roughly 17 light-years across in the shorter direction. It is not spherical. It is irregular, with a somewhat elongated and lumpy shape reflecting the chaotic processes that created and continue to shape it. The solar system entered this cloud somewhere between 45,000 and approximately 150,000 years ago. The uncertainty in that estimate, reflecting how difficult it is to precisely reconstruct the solar system's trajectory through local interstellar structures over tens of thousands of years. The local interstellar cloud is itself embedded within a much larger structure called the local bubble. The local bubble is a cavity in the broader interstellar medium of the Milky Way, an irregularly shaped region of dramatically lower than average interstellar density that extends approximately 300 light-years in its shorter dimension, perhaps 1,000 light-years or more in its longest extent. The cavity is ancient. It was excavated by a series of supernova explosions from massive stars that passed through this region of the galaxy over the past approximately 10 to 20 million years. Current models suggest that somewhere between 14 and 20 individual supernova events contributed to carving the local bubble to its current dimensions, each explosion sweeping outward through the surrounding interstellar medium and driving the denser gas ahead of the blast wave. Over millions of years, these successive explosions cleared most of the denser, cold and warm neutral gas from the region, leaving behind a hot, diffuse cavity filled with plasma at temperatures of approximately 1 million Kelvin. The walls of the local bubble are where that swept-out material accumulated, compressed into shells and sheets of denser interstellar gas. The walls mark the transition back to more typical galactic interstellar medium densities. Several of the most prominent nearby star-forming regions, including portions of the Scorpius-Centaurus-OB association, the nearest region of recent massive star formation to the solar system, roughly 400 light-years, are located in or near the walls of the local bubble, where the compressed material has subsequently become dense enough to collapse gravitationally and form new stars. The supernova explosions that created the local bubble seeded future stellar generations in the same act that destroyed the prior interstellar structure. Within this cavity floats the local interstellar cloud, a denser patch of partially ionized gas that has survived within the local bubble interior without being entirely dispersed by the hot surrounding plasma. The cloud is warmer and less dense than the cold neutral medium that dominates galactic interstellar space in denser regions, but it is orders of magnitude denser than the hot million Kelvin plasma filling the broader local bubble. It occupies an intermediate position in the interstellar medium's temperature density phase structure, what astronomers classify as the warm, partially ionized medium, and it represents the immediate physical context of our solar system's journey through the galaxy. Now, the numbers. The particle density of the local interstellar cloud is approximately 0.3 hydrogen atoms per cubic centimeter. This is the density of the medium that Voyager 1 and Voyager 2 are currently moving through. The medium that presses against the heliopause from outside. The medium into which any future interstellar mission would be launched. 0.3 atoms per cubic centimeter. To translate this into something comprehensible, consider that the air surrounding you at sea level contains approximately 2.7 times 10 to the 19th molecules per cubic centimeter. That is 27 million trillion molecules in every cubic centimeter of the atmosphere you are breathing. The local interstellar cloud contains 0.3 of a single atom per cubic centimeter. The ratio between these two densities is approximately 9 times 10 to the 19th, roughly 100 billion. The interstellar medium is not merely thin or vacuous, in the way that the space between planets is thin and vacuous. It is so incomprehensibly empty that no everyday experience, no laboratory experiment, no engineering process available to current human technology can produce a comparable vacuum. The best laboratory ultra-high vacuum systems achieve approximately 10 to the 7th molecules per cubic centimeter, still tens of millions of times denser than the local interstellar cloud. When physicists and engineers speak of ultra-high vacuum as an extraordinary achievement requiring specialized chambers, ion pumps, and baking procedures to eliminate outgassed molecules from chamber walls, they are describing a density that remains fantastically crowded by comparison to the interstellar medium. The space between the stars is not a vacuum in any sense that the word carries within the context of human experience. It is something for which there is genuinely no terrestrial reference point, but the local interstellar cloud is not the least dense interstellar environment in our the hot plasma filling the broader local bubble interior, plasma left behind by those ancient supernova explosions, has a density of approximately 5 times 10 to the negative 3 particles per cubic centimeter. This is roughly 60 times less dense than the local interstellar cloud. The local bubble interior represents the most rarefied environment directly accessible to spacecraft launched from our solar system. Should any mission travel far enough to exit the local interstellar cloud before encountering the next distinct interstellar structure, an object moving through the local bubble interior beyond the local interstellar cloud would find itself in an environment with individual particle temperatures exceeding 1 million Kelvin, and a total particle density so low that the thermal energy content per unit volume, which depends on both temperature and density, remains extraordinarily small, hot but nearly empty, in the counterintuitive way that only extreme plasma physics can produce. The temperature structure of the local interstellar cloud itself is worth examining precisely because it defies intuitive expectations in its own right. The bulk gas temperature of the cloud is approximately 6,000 to 8,000 Kelvin, significantly hotter than the surface of many red dwarf stars, which have photospheric temperatures in the range of 3,000 to 4,000 Kelvin. Yet nothing in the local interstellar cloud burns or glows visibly in the way that a stellar surface does, because the density is so low that the total thermal energy content per unit volume is negligible. Temperature in a plasma is a measure of the average kinetic energy of individual particles. When there are only 0.3 of a particle per cubic centimeter, the aggregate thermal energy of those particles is essentially zero, even if each individual particle is 20 to 30% of the hydrogen in the local interstellar cloud is ionized, stripped of its single electron by ultraviolet radiation from nearby hot stars, including the hot white dwarf companion of Sirius, approximately 8.6 light-years away, whose ultraviolet output contributes significantly to the local interstellar radiation field. The remaining 70 to 80% consists of neutral hydrogen atoms. The cloud also contains helium at approximately cosmic abundance ratios, roughly 10 hydrogen atoms for every helium atom, along with trace quantities of heavier elements, including carbon, oxygen, nitrogen, neon, magnesium, silicon, sulfur, and iron. Many of these heavier elements are significantly depleted relative to solar photospheric abundances because a fraction of each element is condensed onto the surfaces of interstellar dust grains rather than remaining in the gas phase. Those dust grains constitute a physically important component of the interstellar medium that is easy to underestimate. Interstellar dust particles are extraordinarily small, ranging from a few nanometers to roughly a tenth of a micrometer in size, and extraordinarily sparse by terrestrial standards. But they have measurable effects on light propagation across light-year distances and contribute meaningfully to the interstellar medium's overall physical character. Dust grains in the warm, partially ionized medium of the local interstellar cloud are composed primarily of silicon minerals and carbonaceous materials, with compositions broadly similar to the mineral compositions of meteorites and rocky planets. Some grains carry ice mantles in colder interstellar regions, though in the warm local interstellar cloud, ice mantles are less stable. The significance of interstellar dust for any spacecraft operating in the interstellar medium is primarily mechanical rather than chemical. The dust grain, 1/10 of a micrometer, across traveling at the relative velocity between the solar system and the local interstellar cloud, approximately 52,000 miles per hour, carries kinetic energy proportional to its mass and velocity squared. Individual grains of this size have masses so small that the kinetic energy of any single impact is negligible. But a spacecraft traveling through the interstellar medium at a significant fraction of the speed of light as any mission designed to reach even the nearest stars within a human lifetime would need to encounter the dust. Grains at velocities millions of times higher than the current relative velocity between the solar system and the interstellar medium. At 20% of light speed, which is the target velocity for the breakthrough Starshot laser sail concept, even a grain, 1/100th of a micrometer across, carries enough kinetic energy to penetrate a thin sail material or damage a millimeter-scale electronic component. The dust density of the interstellar medium, negligible at solar system traversal speeds, becomes a significant engineering constraint at relativistic velocities. The galactic cosmic ray environment of the interstellar medium beyond the heliopause demands extended treatment because it represents the most biologically and electronically significant hazard facing any unprotected object in this people's environment. The basics of cosmic ray origin were established in the previous section. Galactic cosmic rays are atomic nuclei accelerated to near-light velocities by supernova remnants and other astrophysical accelerators distributed throughout the Milky Way, filling the galaxy with an approximately isotropic background of energetic particles. What deserves more precise characterization here is the specific nature of that background, its energy spectrum, its composition, its intensity, and its practical consequences. The galactic cosmic ray energy spectrum spans an enormous range, from approximately 100 million electron volts at the low end, through approximately 10 to the 20th power electron volts at the most extreme. This range covers a factor of 1 trillion volts of energy. The spectrum is not flat, it follows a power law, meaning there are vastly more lower energy cosmic rays than higher energy ones. For every factor of 10 increase in energy, the number of cosmic rays at that energy decreases by approximately a factor of 100 to 1000, depending on the energy range. This means that the overwhelming majority of galactic cosmic ray interactions with matter involve particles at energies between approximately 100 million and approximately 10 billion electron volts. These are the particles that the heliosphere most effectively modulates, and they represent the dominant radiation hazard for any unprotected object making the crossing. The composition of galactic cosmic rays mirrors the elemental composition of the galaxy in a modified form. Approximately 89% are protons, hydrogen nuclei. Approximately 10% are alpha particles, helium nuclei. The remaining approximately 1% consists of heavy nuclei, carbon, oxygen, nitrogen, neon, magnesium, silicon, iron, and every other element in the periodic table. There are also electrons and positrons at lower abundances. The relative abundances of different elements in cosmic rays carry information about both the source environments, the stellar interiors, and supernova ejecta, where the atoms originated, and the propagation history through the galactic magnetic field. Since different elements are produced at different rates in different types of nuclear burning and supernova explosions, for any biological organism exposed to the full interstellar cosmic ray flux, the consequences are severe. The most biologically damaging cosmic ray interactions are not the direct passages of primary cosmic ray nuclei through tissue. These are energetic enough that they typically pass through without depositing all of their energy, leaving a trail of ionization damage along their track, but not stopping entirely within the body. More damaging are the secondary particle showers produced when primary cosmic rays collide with atomic nuclei in tissue or shielding material. A high-energy cosmic ray proton striking an atomic nucleus in human tissue produces a spray of secondary particles, neutrons, pions, gamma rays, lighter nuclei that radiate outward from the interaction point in a cone of ionizing radiation. This secondary shower can deposit far more energy locally than the primary particle would have deposited on its own. The dose rate from galactic cosmic rays in the interstellar medium immediately beyond the heliopause is significantly higher than the dose rate experienced anywhere within the heliosphere. Mars-bound astronauts who must travel through space with only their spacecraft structure for shielding already face projected galactic cosmic ray doses that approach or exceed established lifetime career limits for NASA astronauts on missions of 2 to 3 years duration. The dose rate in interstellar space beyond the heliopause, where the heliospheric modulation that partially reduces the cosmic ray flux is absent, would be meaningfully higher still. For missions lasting years or decades in the interstellar medium, galactic cosmic rays represent a fundamental constraint on crew survival that cannot be addressed through any passive shielding approach that adds acceptable mass to a spacecraft. The only effective mitigation for the highest energy cosmic rays is active magnetic shielding, generating an artificial magnetic field around the spacecraft, large and strong enough to deflect incoming cosmic rays. The engineering requirements for such a system at scale sufficient to protect a crewed vehicle are currently far beyond available technology. For the Voyager spacecraft themselves, the cosmic ray environment beyond the heliopause creates challenges to electronics longevity through the single event effects mechanism. When a cosmic ray passes through an integrated circuit, it deposits ionizing energy along its track. If that track passes through a transistor gate or a memory cell, it can flip a stored bit, corrupt a processor register, or in extreme cases trigger a latch-up condition that permanently damages a circuit element. The Voyager spacecraft were designed in the early 1970s using semiconductor components with feature sizes measured in micrometers relatively large by modern standards, correspondingly more robust against single event effects, because the sensitive volumes within each transistor are larger and thus present a larger target. Modern integrated circuits, with transistors measured in nanometers, pack billions of transistors into areas where the Voyager chips contain thousands, making each individual transistor a far smaller and harder to hit target in absolute terms, but making the overall chip far more susceptible because any given cosmic ray track from the chip passes through many individual transistors. This presents a fundamental design challenge for any future interstellar probe. A spacecraft designed to operate for decades in the interstellar cosmic ray environment must use radiation-hardened electronics whose component feature sizes are large enough to resist single event effects but larger. Feature sizes mean lower performance, higher power consumption, and heavier components. Every gram of additional electronics mass is a gram that must be accelerated to the spacecraft's operating velocity, which at the extreme velocities required for meaningful interstellar transit demands enormous additional propulsive energy. The cosmic ray environment imposes a direct trade-off between electronics reliability and mission performance that has no satisfying resolution with current technology. The interstellar magnetic field adds further complexity to any operational picture of the environment beyond the heliopause. The interstellar magnetic field measured directly at the heliopore's crossing threads the entire local interstellar cloud on scales of tens of light years. This field did not form suddenly or locally. It is a remnant and amplification product of processes operating at galactic scales, the differential rotation of the Milky Way, which stretches and wins magnetic field lines over millions of years. The turbulent energy injection by supernova explosions, which randomizes and amplifies magnetic fields on intermediate scales, and smaller scale magnetohydrodynamic turbulence within individual interstellar clouds, which cascades magnetic energy from large scales to small scales, in a process analogous to turbulent energy cascades in ordinary fluids. The direction of the local interstellar magnetic field pointing approximately toward the galactic plane, as inferred from both the Voyager magnetometer data and the IBEX energetic neutral atom ribbon observations, reflects the large-scale organization imposed by the Milky Way's differential rotation. The galactic magnetic field has a preferred direction aligned roughly parallel to the galactic plane, following the spiral arm structure of the galaxy. Local perturbations from supernova explosions and the dynamics of individual interstellar clouds distort this preferred direction regionally, but over scales of hundreds of light years the field tends to return to its large-scale organized direction. For a spacecraft navigating through the interstellar medium, the magnetic field is relevant primarily through its effect on galactic cosmic ray trajectories. Charged particles moving through a magnetic field are deflected perpendicular to both their velocity and the field direction. The degree of deflection depends on the particle's charge, its momentum, and the field strength. For the weak interstellar magnetic field of the local interstellar cloud, the deflection radius, the radius of the curved path, the cosmic ray follows in the field for a typical 1 billion electron volt proton is approximately 1 astronomical unit. This means that typical interstellar cosmic rays are deflected by the local magnetic field on scales comparable to the size of planetary orbits. The cosmic ray background in interstellar space is not perfectly isotropic. It has directional structure imposed by the local magnetic field geometry and by the locations of nearby cosmic ray sources, and the anisotropy and the energies relevant for biological and electronic effects is small enough that it does not change the fundamental character of the radiation hazard. One of the most practically significant aspects of operating beyond the heliopause is not the particle environment, but the communication environment. Both Voyager spacecraft transmitted frequencies in the X-band of the radio spectrum, approximately 8 GHz for Voyager 1. At the spacecraft's current distance of approximately 160 astronomical units, the signal arrives at Earth with a power of approximately 10 to the negative 26th watts. This is a number so small that writing it out provides no intuitive sense of its magnitude. The Deep Space Network receiving dishes, the largest radio telescopes operated by NASA, with diameters up to 70 meters, must integrate signal for extended periods and use sophisticated noise reduction techniques to extract usable data from this power level. The one-way light travel time from Voyager 1 at 160 astronomical units is approximately 22 hours. Every command sent from Earth takes 22 hours to arrive at the spacecraft, and every response takes 22 hours to return. Total round-trip communication delay, 44 hours. For Voyager 2, at approximately 130 astronomical units, the one-way delay is approximately 18 hours. For a spacecraft at the distance of the heliopause approximately 120 astronomical units, the One-way light travel time is approximately 16.5 hours. For a spacecraft at 1,000 astronomical units still within the inner regions of the hypothetical Oort cloud, nowhere near the nearest stars, the one-way delay exceeds 5 days. Any meaningful interstellar probe designed to operate beyond the solar system would need to function autonomously for essentially its entire mission. Commands from Earth cannot arrive in time to respond to rapidly evolving situations. Fault protection, science operations, navigation corrections, instrument management, all of these must be handled by onboard systems without human intervention. This requires a level of spacecraft autonomy that exceeds anything currently deployed in operational deep space missions. The Voyager spacecraft carry relatively simple fault protection logic by modern standards, and they have experienced numerous anomalies over their 40-plus years of operation that have required rapid response from Earth-based teams. At interstellar distances, that response time becomes irrelevant. The spacecraft must solve its own problems or fail. Navigation in the interstellar medium presents a related challenge. Within the solar system, spacecraft are navigated using a combination of radio signal timing and Doppler measurements. The Deep Space Network transmits a signal to the spacecraft retransmits it. The round-trip time and frequency shift precisely determine the spacecraft's position and velocity relative to Earth. This technique works extremely well within the heliosphere, because the solar gravitational field provides a well-characterized dynamical background against which positions and velocities can be computed with high accuracy. Beyond the heliopause, the same technique continues to work. Both Voyager spacecraft are navigated this way, but it provides only the spacecraft's position relative to the solar system's center of mass. Navigating relative to a target star system, which any interstellar mission would eventually need to do, requires both extremely precise knowledge of the target star's position and proper motion over decades, and a navigation framework that accounts for the effects of the interstellar medium on the spacecraft's trajectory. The interstellar medium exerts very small but non-zero forces on a traveling spacecraft through the ram pressure of the interstellar gas and the magnetic pressure of the interstellar field. At Voyager speeds, these effects are negligible. The spacecraft is moving at approximately 38,000 miles per hour, which is slower than the thermal speed of the interstellar plasma particles and far below the velocities at which ram pressure effects become significant. At the relativistic velocities contemplated for rapid interstellar transit, however, the ram pressure of even the extraordinarily thin interstellar medium becomes a meaningful deceleration force. A spacecraft moving at 20% of light speed, approximately 134 million miles per hour, encounters the interstellar medium's 0.3 particles per cubic centimeter with a ram. Pressure sufficient to cause measurable deceleration over distances of light years. The cumulative physical picture of the interstellar medium beyond the heliopause can now be assembled from these individual characterizations to a coherent portrait of the environment. It is a near-perfect vacuum by any human engineering standard, containing the same warm, partially ionized gas of the local interstellar cloud, at its characteristic near-vacuum density, threaded by a magnetic field of approximately 0.4 nanotesla, pervaded by a continuous flux of galactic cosmic rays whose intensity is approximately double the value modulated to by the heliosphere, dusted with nanometer to submicrometer silicate and carbonaceous particles at densities that are negligible at low speeds, but potentially significant at relativistic velocities. Communication across it is subject to speed of light delays measured in years for the nearest stars and decades for even the closest stellar neighbors. Navigation within it requires autonomous onboard systems of a sophistication not yet demonstrated in operational spacecraft. Radiation shielding within it requires either accepting dose rates that exceed current human spaceflight limits, or developing active magnetic shielding technology of a mass and complexity not yet achievable. None of this is speculation. These are the measured properties of the specific interstellar environment into which our solar system is currently embedded, derived from spacecraft data, astronomical spectroscopy, and energetic particle observations that that have been peer-reviewed, replicated, and refined over decades. The interstellar medium is not the unknown. It is the measured, and the measurement reveals an environment that makes the inner solar system, even the surfaces of airless rocky bodies like the Moon and Mercury, look like sheltered, protected, survivable places by comparison. All of this characterization applies to the immediate vicinity of the heliosphere, the local interstellar cloud, and the inner regions of the local bubble within the first few tens of light years of our solar system's neighborhood. The distance of the nearest stellar systems at 4.24 light years from Proxima Centauri. The properties of the interstellar medium are broadly similar to those in our immediate vicinity, since we and the nearest stars share the same local interstellar cloud. But the stars themselves introduce new hazards, new dynamics, new environments within their own stellar systems that are distinct from the interstellar medium between them. Understanding those distances not just as numbers but as physical realities, as barriers, as measurements of the true scale of the isolation that the interstellar medium imposes on stellar systems, is the final and most important step in grasping what it means to leave the solar system behind, 4.24 light years. That is the distance to Proxima Centauri, the nearest known star to our solar system, 4.24 light years. The number is small enough to fit in a sentence, precise enough to feel scientific, and completely, utterly meaningless to any human brain, attempting to hold it as a physical reality rather than an abstract quantity. Every number used in astronomy suffers from this problem. To some degree, astronomical distances are so far outside the range of distances that human evolution equipped us to process that even the most careful attempts at translation fall short. The distance to the nearest star deserves a sustained attempt at translation, because it is the most important number in understanding what interstellar space actually is, and why the boundary we have spent 3 parts of this story characterizing represents something far more profound than a line on an astronomical chart. 1 light year is the distance light travels in 1 year. Light travels at approximately 186,000 miles per second. In 1 minute, light covers approximately 11 million miles. In 1 hour, approximately 670 million miles. In 1 day, approximately 16 billion miles. In 1 year, 365 days, approximately 315 million seconds, light covers approximately 5.88 trillion miles. 4.24 light years is therefore approximately 24.9 trillion miles. Written out in full, that number is 24 million miles. 24 followed by 12 zeros, expressed in miles. These kinds of number translations are common in astronomy writing, and they typically produce a brief cognitive jolt before the brain reasserts its inability to process the quantity and moves on. So instead of stopping at the number, follow it through to its practical consequences. Consider what it means for the only human-made objects that have actually entered interstellar space. Voyager 1 is currently traveling at approximately 38,000 miles per hour. This velocity was not achieved easily. It required the most powerful rockets of its era, combined with the gravity assist trajectory already described, and the resulting 38,000 miles per hour represents the absolute peak of human propulsive achievement. Across nearly 5 decades of spaceflight, the resulting velocity of approximately 38,000 miles per hour represents the fastest sustained speed ever achieved by a human-made object. At this velocity, Voyager 1 covers approximately 912,000 miles every 24 hours, roughly 3.8 times the distance from Earth to the Moon every single day, without stopping. At this speed, the absolute peak of human propulsive achievement, the fastest we have ever managed to send anything reaching Proxima Centauri, would require approximately 75,000 years, not 73,000 days, not 73,000 months, 73,000 years. Modern, anatomically modern humans have existed as a species for approximately 300,000 years. Recorded human history spans approximately 5,000 years. Agriculture was developed approximately 12,000 years ago. The earliest known permanent human settlements date to approximately 10,000 years ago. The time required for Voyager 1 to reach the nearest star if it were travelling in that direction, which it is not, is approximately 15 times the entire span of recorded human civilization, roughly 1/4 of the entire duration of our species' existence on Earth. To frame this from the other direction, when light left Proxima Centauri this morning and began its 4.24 light-year journey toward Earth, that light will arrive here in 4 years and approximately 3 months. If a human civilization sent a radio message to Proxima Centauri today and waited for a response, the minimum possible round-trip communication time, assuming an immediate reply, would be approximately 8.5 years. Any meaningful exchange of information with the nearest stellar system would unfold on timescales measured in human generations rather than human lifetimes. A scale model makes the spatial relationship concrete in a way that raw numbers cannot. If the distance from the Sun to the Earth, 1 astronomical unit, approximately 93 million miles, is represented as 1 single millimeter, then on this scale, the solar system takes on the following proportions. Neptune orbits at 30 millimeters from the Sun, 3 centimeters, fitting comfortably across 2 fingers. The termination shock at approximately 90 astronomical units sits at 90 millimeters, roughly the width of a hand. The heliopause at approximately 120 astronomical units sits at 120 millimeters, about the length of a standard ruler from its edge to the 12 centimeter mark. Proxima Centauri, the nearest star, sits at approximately 268,000 millimeters from the Sun. On this scale, 268 meters, roughly the height of the Eiffel Tower. On this scale, the entire solar system, out to the heliopause, fits within a region the size of a dinner plate. The nearest star is 268 meters away, nearly 3 football fields. The interstellar medium fills the space between. At that space, those 6 meters on the scale model representing 25 trillion actual miles, contains essentially nothing but the local interstellar clouds, 3/10 of an atom per cubic centimeter, the weak interstellar magnetic field, the continuous galactic cosmic ray flux, and the occasional interstellar dust ray, 6 meters of almost perfect vacuum, on a scale where the Sun is a single millimeter and the Earth is roughly 1/100th of a millimeter. But Proxima Centauri is not the only nearby star. The local stellar neighborhood, the volume of space within approximately 15 light-years of the Sun, contains a specific, mapped population of stellar systems whose properties are known with precision from decades of observational work. Understanding this neighborhood is not merely a cataloging exercise. The properties of these nearby stars define the particle radiation to the interstellar medium between them. Those properties reveal something important about what the local interstellar environment is actually like, across the full distance to the nearest stellar systems. Proxima Centauri is a red dwarf of spectral type M, 5.5 among the coolest, dimmest, smallest stars, classified as genuine hydrogen-burning main sequence stars. Its surface temperature is approximately 3040 Kelvin, roughly half the temperature of the Sun's photosphere. Its luminosity is approximately 0.17% of the Sun's output. It produces roughly 600 times less light than the Sun. If Proxima Centauri replaced the Sun at the center of our solar system, Earth would receive so little energy that the planet's surface would freeze solid within decades. Proxima Centauri's mass is approximately 12% of the Sun's mass, small enough that if it were significantly less massive, the pressure and temperature at its core would be insufficient to sustain hydrogen fusion, and it would be a brown dwarf rather than a star. Despite its feeble luminosity, Proxima Centauri is magnetically violent. It is a flare star, a category of red dwarf that produces sudden, intense releases of magnetic energy in the form of ultraviolet and X-ray flares that can briefly increase its total luminosity by factors of hundreds to thousands. In March of 2016, a superflare from Proxima Centauri temporarily increased its ultraviolet output by a factor of approximately 1,000 relative to its quiescent level, with the flare event lasting approximately 2 minutes of peak intensity for any planetary surface in the system. The ultraviolet dose range during such an event would be orders of magnitude above anything in the solar system's habitable zone on Earth's worst day of solar activity. Proxima Centauri b, the confirmed terrestrial mass planet, detected in 2016 through the radial velocity technique, which measures the tiny wobble a planet's gravity induces in its host. The star's motion orbits its star at approximately 0.048 astronomical units. For comparison, Mercury orbits the Sun at approximately 0.39 astronomical units. Proxima Centauri b is more than 8 times closer to its star than Mercury is to the Sun. It orbits once every 11.2 days. At this distance, it receives approximately 65% of the energy per unit area that Earth receives from the Sun, placing it within the nominal habitable zone defined by the stellar energy flux alone. But the habitable zone definition accounts only for the stellar luminosity's capacity to maintain liquid water at the surface. It says nothing about flare radiation, stellar wind particle flux, or the magnetic environment. The stellar wind from Proxima Centauri, the equivalent of our solar system's solar wind, is estimated to be significantly more intense than the Sun's solar wind in terms of particle flux per unit area at the planet's orbital distance, despite the star's low luminosity. The close orbital distance of Proxima Centauri b means it is immersed in a stellar wind that is substantially denser at its location than the solar wind is at Earth's orbit, even though the star itself is much less luminous. The resulting astrosphere, the Proxima Centauri equivalent of our heliosphere, may be smaller and weaker than ours relative to the surrounding interstellar medium. The planet itself, orbiting so close to the star within this compressed astrosphere, faces a particle radiation environment that may strip atmosphere from its surface over geological timescales. Whether Proxima Centauri b retains an atmosphere, whether it has liquid water, whether it has a magnetic field strong enough to deflect its star's particle wind, whether it is tidally locked, rotating synchronously with its orbit, so that one hemisphere permanently faces the star while the other is in eternal darkness, these questions remain entirely open. No instrument currently in operation can characterize the planet's atmosphere or surface. The nearest planetary system is simultaneously accessible to detection and inaccessible to characterization with our current capabilities. We know it exists. We know almost nothing else. The two brighter members of the Alpha Centauri system, Alpha Centauri A and Alpha Centauri b, orbit each other as a gravitationally bound binary pair, their separation varying between approximately 11 astronomical units at closest approach and approximately 36 astronomical units at their widest, completing one mutual orbit approximately every 79.9 years. Completing one mutual orbit approximately every 79.9 years. Alpha Centauri A is a Type G 2 main sequence star, essentially a solar twin, slightly larger and more luminous than the Sun, with a surface temperature of approximately 5,790 Kelvin and a luminosity approximately 1.5 times solar. Alpha Centauri b is a Type K 1 main sequence star, smaller and cooler than both the Sun and Alpha Centauri A, with a surface temperature of approximately 5,290 Kelvin and a luminosity approximately half of solar. The proximity and brightness of these two stars have made them targets for exoplanet searches. Though confirmed planets in the Alpha Centauri AB system have proved elusive, a candidate planet detection from 2012 was subsequently retracted, and the observational challenge of detecting planets around stars in a close binary system remains significant. Moving outward through the local stellar neighborhood, the population continues to be dominated by red dwarfs. Barnard's star, at approximately 5.96 light-years, the fourth nearest star system is a Type M4 red dwarf, notable for its extraordinary proper motion across the sky. It shifts its angular position relative to background stars by approximately 10.3 arcseconds per year, the fastest proper motion of any known star. This rapid motion reflects its relatively close distance combined with a significant velocity relative to the Sun. A candidate super-Earth in a potentially habitable orbit around Barnard's star was announced in 2018, but has not been confirmed with high confidence. Wolf 359, at approximately 7.78 light-years, is a Type M6 red dwarf of such extreme magnetic activity that it was the source of one of the most energetically intense stellar flares ever directly recorded. The census of stars within 15 light-years of the Sun contains approximately 56 stellar systems, hosting approximately 67 individual stars and brown dwarfs. Of these, approximately 45 are red dwarfs of type M, 5 are orange dwarfs of type K, 2 the Sun and Alpha Centauri A, are yellow dwarfs of type G. One Sirius A, at approximately 8.6 light-years, is a white main sequence star of type A, approximately twice the solar mass and approximately 25 times the solar luminosity. Sirius A's binary companion, Sirius B, is a white dwarf, the remnant core of a star that exhausted its fuel and shed its outer layers, leaving behind a hot, dense, cooling cinder approximately equal to Earth in size but to the Sun in mass. The statistical implication of this local census applies globally. Red dwarfs constitute approximately 70% of all stars in the Milky Way, the brilliant, luminous stars that dominate the night sky. Sirius, Vega, Rigel, Betelgeuse are spectacularly rare exceptions. The galaxy is overwhelmingly populated by dim, long-lived, magnetically volatile red dwarfs that produce so little light they are essentially invisible to the naked eye at even the modest distances in the nearest stellar systems. The nearest star bright enough to see without optical aid under dark sky conditions from Earth is Alpha Centauri A and B combined, which appear as a single point of light at magnitude -0.3 in the southern sky. Proxima Centauri, only slightly farther away, has a magnitude of approximately 11, roughly 100 times too faint to detect with the unaided eye. For the interstellar medium between the solar system and these nearby stars, the relevant physical context is that of the local interstellar cloud, as characterized in the previous section, approximately 0.2 cubic centimeter, temperatures of 6,000 to 8,000 Kelvin, weak interstellar magnetic field of approximately 0.3 to 0.5 nanotesla, full galactic cosmic ray flux. This environment extends approximately continuously from just beyond the heliocores to the astrospheres of the nearest stellar systems. There is no protective structure, no transition to a more benign environment, no region where the conditions become less hostile to an unprotected spacecraft or organism. The interstellar medium between here and Proxima Centauri is the same interstellar medium that the Voyager spacecraft are currently sampling at 160 astronomical units, just extending for an additional 4 light-years. Approximately 269,000 additional astronomical units in every direction. Serious proposals for reaching the nearest stars within human-relevant timescales exist and deserve honest examination. The Breakthrough Starshot Initiative, announced in April 2016 by a group including physicist Stephen Hawking and entrepreneur Yuri Milner, with backing of $100 million for research and development, proposes accelerating the ground-scale spacecraft to approximately 20% of the speed of light using a grid-based phased laser array. At 20% of light speed, approximately 134 million miles per hour, such a spacecraft would reach the Alpha Centauri system in approximately 20 to 22 years. The concept is grounded in known physics. Laser propulsion and light sails have been demonstrated at small scales. There is no fundamental physical law that prevents the approach from working. The engineering obstacles, however, are substantial, and none have been resolved as of current technology. The proposed laser array would need to deliver approximately 100 gigawatts of focused, coherent laser power to the sail, a power level roughly equivalent to the total electrical generating capacity of the United Kingdom, for a period of approximately 10 minutes during the acceleration phase. Maintaining the beam's diffraction-limited focus on a sail measuring perhaps several meters across, over an acceleration distance of roughly 10 million kilometers, requires adaptive optics systems of a precision not yet demonstrated at any comparable scale. The sail material must survive the initial laser pulse without vaporizing, distorting, or tearing a pulse that delivers more energy per unit area than any known material has survived intact. The gram-scale payload, carrying cameras, spectrometers, and a laser communication system capable of transmitting data across 4 light years, must be designed within mass constraints that make every component a challenge of miniaturization beyond current capability. Even if all of these obstacles were resolved, the interstellar medium itself imposes constraints on the mission. At that velocity, the spacecraft's collision cross-section with interstellar dust grains becomes significant in a way that is entirely negligible at Voyager speeds. An interstellar dust grain of approximately 1/10 of a micrometer diameter, typical of the grain size distribution in the local interstellar cloud, carries kinetic energy in the spacecraft's rest frame of approximately 1/10 of a millijoule at 20% of light speed. For a gram-scale sail material with a real density of grams per square meter, the cumulative erosion from thousands of such impacts over a 4-light-year transit would degrade the sail's reflectivity and potentially compromise its structural integrity. Larger, rarer grains approaching a micrometer in diameter could carry enough kinetic energy in a single impact to punch through the sail or destroy the payload entirely. Designing a sail that is simultaneously light enough to be accelerated efficiently, large enough to intercept the laser beam effectively, and robust enough to survive thousands of dust grain impacts at relativistic velocities is a design problem for which no current material solution exists. The galactic cosmic ray environment at 20% of light speed presents an additional complication. At relativistic velocities, the spacecraft's electronics are exposed to galactic cosmic rays arriving from the forward hemisphere at higher effective energies. Due to relativistic beaming, the same effect that causes rain to appear to fall at an angle toward you when you run through it. The single event effect rate in the spacecraft's electronics increases at relativistic velocities compared to stationary exposure, further stressing the already challenging requirement for radiation-hardened computing systems, the performance and miniaturization needed for a gram-scale payload. These are not objections intended to dismiss the concept. They are characterizations of real physical constraints imposed by the interstellar medium itself. The medium does not merely need to be traversed, it actively resists traversal at the velocities required to make the journey meaningful. Every property of the interstellar environment between here and Proxima Centauri, the dust density, the cosmic ray flux, the magnetic field becomes a mission design constraint for any spacecraft attempting to cross it at speeds that would make the crossing worth attempting. For missions at Voyager speeds, the only speeds currently demonstrated for interstellar transit, the constraints are different in character but no less definitive. 73,000 years to the nearest star. The entire span of human civilization has lasted approximately 5,000 years. No continuous human institution, no government, no religion, no scientific organization has maintained operational continuity for even 1,000 years in their current recognizable form. The idea of maintaining a spacecraft mission, maintaining the knowledge base to interpret its data, maintaining the communication infrastructure to receive its transmissions, and maintaining the organizational continuity to care what it finds for 73,000 years is not an engineering problem. It is a civilizational one, of a kind no civilization in recorded history has come close to demonstrating the capacity to solve. And yet the Voyager spacecraft are there, beyond the heliopause, in the interstellar medium, transmitting data from a place that no prior human technology had reached. Built in the 1970s with technology that any modern smartphone surpasses in computational power by many orders of magnitude, Designed for a mission expected to last approximately 4 years, now in their 48th year of operation, they are still functioning, still measuring, still returning data from an environment whose properties we would not otherwise know. This is the context in which the conclusion of this story belongs. Not in despair at what we cannot yet do, but in clarity about what the measurements actually reveal. The solar system is not the normal condition of space. It is an exception. The Sun, by continuously outputting the solar wind and maintaining the heliosphere, spent 4.5 billion years creating and defending a region of modified space, approximately 240 astronomical units, across roughly 0.004 light-years in diameter, within which the galactic cosmic ray flux is meaningfully reduced by the heliospheric magnetic field. The interstellar plasma is excluded. The magnetic environment is organized by stellar rather than galactic processes. The conditions are, in aggregate, substantially less hostile to complex chemistry and biology than the surrounding interstellar medium. This exception is not stable in the long term. The Sun will eventually evolve off the main sequence. The solar wind will change dramatically, and the heliosphere will no longer maintain its current form. But for the approximately 5 billion remaining years of the Sun's main sequence lifetime, the heliosphere will continue to hold. The nearest analogue to this protected environment is the astrosphere of Proxima Centauri, 4.24 light-years away across the full hostility of the local interstellar cloud. In between, there is no shelter, no reduction in cosmic ray flux, no stellar magnetic protection, no warm plasma environment. Only the interstellar medium as it actually is: diffuse, cold, magnetically threaded, radiation saturated, and indifferent to the survival of the galaxy contains somewhere between 200 billion and 400 billion stars. Each of those stars maintains its own version of the protected bubble our Sun maintains for us. But those bubbles are separated from each other by distances that, even at the speed of light, require years to cross, and at any speed currently achievable by human technology require tens of thousands to millions of years. The galaxy is not a connected environment. It is a collection of isolated stellar islands, each surrounded by its own modest sphere of modified space, each separated from its neighbors by vastly larger regions of unmodified interstellar medium. Our heliosphere, at approximately 240 astronomical units across, represents approximately 0.09% of the distance between the Sun and Proxima Centauri. If the distance to the nearest star were represented as the length of the standard football field, 100 yards in the diameter of our entire heliosphere, the full extent of the Sun's protected domain would represent approximately 3 inches, a small fraction of a single human hair's width on a football field. That is the fraction of interstellar space that our Sun has successfully modified into a habitable environment. Everything that has ever lived on Earth, every organism in the fossil record, every bacterium in the deep ocean, every human being who ever existed has lived within that hair's width fraction of the space between here and the nearest star. 4.5 billion years of biological evolution, the entire history of complex life on this planet, the entire span of human civilization, every scientific discovery ever made, every piece of music ever composed, every war ever fought, all of it occurred within a bubble so small that it occupies a negligible fraction of the distance to our nearest stellar neighbor. And the moment anything crosses the heliopause, the moment any spacecraft, any probe, any future human mission exits that protected domain, it enters an environment that has never been shaped by the Sun, that has never been modified to be less hostile, that does not care whether the objects passing through it survive the crossing. The interstellar medium does not become more hospitable farther out. It does not thin into something less threatening. It simply continues at the same density, the same radiation level, the same magnetic character, all the way to the next star's astrosphere, across 25 trillion miles of measured, quantified, instrument-confirmed hostility. Leaving the solar system is not traveling farther into space. Every spacecraft launched by humanity has traveled into space. The Apollo missions traveled into space. Mars rovers operate in space, the Voyager spacecraft traveled through space for decades before they reached the heliopause. Traveling into space, within the heliosphere, means traveling through an environment that is unusual by galactic standards. A stellar wind-filled, magnetically organized, partially shielded from cosmic radiation bubble that represents the Sun's continuous physical output. Leaving the solar system means exiting that environment entirely and entering the baseline condition of the interstellar medium, the condition that prevails across the vast majority of the galaxy's volume. The space between the stellar islands, where no star's wind reaches, no star's magnetic field provides any protection, the galactic cosmic ray background arrives at its full unmodulated intensity. It means crossing from one physical regime into a fundamentally different one, at a boundary that both Voyager spacecraft have now confirmed is sharp, measurable, and real. The heliosphere is small. By galactic standards, it is almost unimaginably small, a microscopic sphere of modified space embedded in a galaxy 100,000 light-years across. But from the perspective of every living thing that has ever existed on Earth, it is everything. It is the entire physical domain in which life emerged, evolved, and developed the capacity to measure the boundary of its own home. We now know where that boundary sits. We know what it is made of. We know what the instruments measure when they cross it. And we know what waits on the other side, not as speculation, not as inference from theory, but as direct measurement from the two most distant objects humanity has ever made. The solar system is protected, profoundly, specifically, physically protected by a star that has been spending its own mass at a rate of 1,000,000 tons per second for 4.5 billion years, holding the galaxy at arm's length. Beyond the heliopause, the galaxy stops being held back. It presses in from all directions, as it always has, as it will for billions of years to come, cold, ancient, radiation-bathed, vast, beyond any scale that feels real when you are standing on one small planet inside the exception. The Voyager spacecraft are in it now. They crossed the boundary and kept transmitting. What they found confirmed what the physics predicted. That the Sun's domain ends sharply, that the interstellar medium begins immediately, and that the distance between what we are and where the nearest star sits is not a journey, it is an ocean. We have, so far, managed to wade in only up to our ankles. boarding. Yourself to the bus. A spacecraft, traveling at 38,000 miles per hour, the fastest sustained speed any human-built object has ever maintained on an interstellar trajectory. You launch today. You aim straight for the opposite edge of the Milky Way. You will not arrive for nearly 2 billion years. Not 2,000, not 2 million, 2 billion. By the time your ship crosses the galaxy, our sun will have swollen enough to boil the oceans away and render Earth a scorched, lifeless rock. Every continent will have been rearranged. Every trace of human civilization will have been erased by geological forces many times over. And here is the part that should unsettle you most. The Milky Way is not even close to the largest galaxies in the universe. Some are 10 or 20 times wider. This is what it actually costs to cross your own home. If you enjoy having your sense of scale permanently broken, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives, and I appreciate every single one of you. Now, let's begin. You already have a picture of the Milky Way in your head. Everyone does. It is that elegant spiral you have seen 1,000 times on posters, documentaries, textbook diagrams. A pinwheel of white and blue light sitting against a black background, with a neat label pointing to a tiny dot somewhere along one of the outer arms that says, "You are here." The image is beautiful. It is comforting. It is also one of the most dangerously misleading pictures in all of science. Not because it is factually wrong. The Milky Way is indeed a spiral. We are indeed located in the outer arms. But the image creates an illusion so powerful that almost nobody recognizes it as an illusion. It makes the galaxy look like something you could hold, something you could cross, something you could wrap your mind around the way you wrap your mind around a country or a continent. You look at that spiral diagram and you think, I know where I live. I understand the shape of my cosmic neighborhood. The distance from one side to the other looks manageable. It looks like a map, and maps by definition are things you can traverse. That instinct is wrong. Not slightly wrong. Catastrophically wrong. The Milky Way is not a map you live inside. It is a physical object whose diameter would take light itself 100 millennia to cross. And the first step toward understanding why it would take so absurdly long to travel from one side to the other is understanding what this galaxy actually is, not as a diagram, not as a poster, but as a three-dimensional object made of matter, energy, gravity, and distances that break every intuitive tool your brain possesses. Let us start with the basics. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped structure of densely packed stars running through its core, with sweeping spiral arms curving outward from the ends of that bar. It contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number is itself staggering. We are not sure whether our galaxy contains 100 billion stars or 4 times that many. The difference between the low estimate and the high estimate is 300 billion stars, a margin of error larger than most galaxies in the universe. And we are not talking about distant, poorly observed galaxies here. We are talking about the galaxy we live in, the one we have been studying for centuries. We still cannot agree on how many stars it holds to within a factor of 4. The reason for this uncertainty is simple and humbling. We are trying to measure the galaxy from inside it. Picture standing in the middle of a dense forest and being asked to count every tree. You can see the ones nearby clearly. You can estimate the ones a little farther away, but beyond a certain distance, the trunks overlap, the canopy blocks your view. You cannot tell whether there are 1,000 trees ahead of you or 10,000. Dust clouds, gas lanes, and the sheer density of stars near the galactic center block our view of enormous sections of our own galaxy. We are embedded in the structure we are trying to measure, and that makes everything harder. The stellar disk of the Milky Way, the flat pancake-shaped region where the vast majority of stars reside, spans approximately 100,000 light-years from edge to edge. Some recent studies using chemical analysis of distant stars have argued that the disk may extend even farther, perhaps out to 160,000 or even 200,000 light-years when you include faint outer populations and warped edges. But the commonly cited figure, the one supported by the broadest range of measurements, remains approximately 100,000 light-years from the main visible disk. That is the number we will use as our baseline. That is what crossing the Milky Way means in this story, traveling from one edge of that stellar disk to the other, straight through the center, a journey of roughly 100,000 light-years. Now, 100,000 light-years is a phrase that rolls off the tongue so easily it almost sounds tame. Astronomy has a way of numbing you to enormous numbers. You hear billion, trillion, and light-years so often that they start to feel like wallpaper, background noise. So let us stop and actually unpack what 100,000 light-years means in physical terms. A single light-year is the distance that light travels in 1 year, moving at 186,000 miles per second. Not per hour, per second. In 1 second, a beam of light covers a distance that would take a commercial airplane roughly 14 days to fly. In 1 minute, light travels more than 11 million miles. In 1 hour, it crosses 670 million miles. By the end of a full year, light has traveled approximately 5,878,000,000,000 miles. That is 1 light year. If we multiply that by 100,000, the diameter of the Milky Way works out to roughly 588 quadrillion miles. Written numerically, that is an 18-digit number, a figure so long it would not fit on a standard calculator display. The number is so large that it ceases to function as information. Your brain receives it the same way it receives a random string of digits. It does not land, it does not connect to anything you have experienced. And that is precisely the problem. You cannot feel the size of the galaxy by hearing a number. You can only feel it by comparing it to things you already understand. We will do that shortly. But for now, the critical point is this. The Milky Way is not a picture on a wall. It is a physical object nearly 600 quadrillion miles across. And when we talk about crossing it, we are talking about traversing every single one of those miles. The disk itself is remarkably thin compared to its width. At the location of our Sun, the disk is roughly 1,000 light-years thick. That is a ratio of width to height of about 100 to 1. If you scaled the Milky Way down to the size of a dinner plate, the plate would be barely a tenth of an inch thick, thinner than a stack of 3 credit cards. The galaxy is extraordinarily flat. We live in a galaxy that is essentially flat, a vast cosmic frisbee spinning through space. The central bulge is thicker, roughly 10,000 light-years in diameter, swelling around the core like a slight bump at the center of the disk. And at the very heart of that bulge sits Sagittarius A star, a supermassive black hole with a mass of approximately 4 million suns compressed into a region smaller than the orbit of Mercury. Everything in the galaxy, all 400 billion stars if we accept the higher estimate, orbits around this gravitational anchor. Our own Sun completes one full orbit roughly every 230 million years. Astronomers call this period a galactic year. The entire history of Earth, our planet has completed only about 20 orbits around the galactic center. The dinosaurs went extinct less than 1 galactic year ago, but the disk and the bulge are only the visible portion of the galaxy. Beyond the bright spiral arm stretches an enormous spherical halo of old stars, globular clusters, and most importantly, dark matter. This halo extends far beyond the visible disk. Recent research using the orbits of satellite galaxies has placed the outer edge of the Milky Way's gravitational influence at approximately 950,000 light-years from the galactic center. That is a total diameter of roughly 1.9 million light-years when you include the full dark matter halo. The visible galaxy, the part you see in photographs and diagrams, represents a relatively small luminous core sitting inside a vastly larger invisible structure. The dark matter halo contains approximately 10 times more mass than all the visible stars, gas and dust combined. This invisible scaffolding holds everything together. Without it, the galaxy would fly apart. Stars in the outer disk orbit far too quickly to be held by the gravity of visible matter alone. Something massive and unseen provides the additional gravitational pull. That something is dark matter, and it extends the true boundary of the Milky Way far beyond the edges of any poster you have ever seen. For the purposes of this script, however, we are focused on the stellar disk. 100,000 light-years. That is the journey. That is the crossing. And understanding what that crossing actually entails requires looking at what fills the space between one edge of the galaxy and the other. The Milky Way is not a uniform slab of stars. It has structure. Complex, layered, dynamic structure. The spiral arms are the most obvious feature. Our galaxy has 4 major spiral arms: the Scutum Centaurus arm, the Perseus arm, the Sagittarius arm, and the Norma arm, along with several smaller spurs and branches. Our solar system sits on the inner edge of a minor structure called the Orion arm, sometimes called the Orion spur, which branches off between the Sagittarius and Perseus arms. The spiral arms are not solid walls of stars. They are density waves, regions where gas and dust are compressed by gravitational interactions, triggering intense bursts of star formation. The bright blue stars that make the arms visible are young, massive, and short-lived. They are born in the arms, burn fiercely for a few million years, die before they ever leave. The arms glow because they are factories, constantly producing.
Why, I wholeheartedly agree with you, my friend. I find you so good, so clever, so nice things. Ah, well, I couldn't agree with more of you, because of course. Why, you have the best opinions, and I think so. Could be, you never know. Absolutely, well, yes. Oh, I heard about that. Absolutely delectable. I highly approve of this course. I completely understand it.
factories, constantly producing new stars from raw material. Between the spiral arms lie interarm regions. These are not empty. They contain older, dimmer stars, scattered gas clouds, and vast stretches of relatively quiet space. Crossing the galaxy would mean passing through multiple arm and interarm transitions, each spanning thousands of light years. You would traverse regions of intense star formation where radiation and stellar winds create hostile environments, and you would pass through calmer stretches where stars drift in relative isolation. As you approach the galactic center, conditions would change dramatically. The density of stars increases sharply. Within the central few thousand light years, stars are packed hundreds or thousands of times more tightly than they are in our neighborhood. The gravitational environment becomes chaotic. Stars swing around the supermassive black hole on tight, fast orbits. Some stars in the galactic center region move at speeds exceeding 10 million miles per hour, whipping around Sagittarius A star in orbits that take only a few years to complete. The radiation environment is extreme. X-ray emissions, gamma-ray bursts from high-energy processes, and intense magnetic fields make the galactic center one of the most energetic and violent regions in the entire galaxy. Crossing through it would not be a gentle flyby. It would be a passage through a gravitational and radiological storm. Beyond the center, you would enter the far side of the galaxy, a region we know even less about than our own neighborhood. Dust lanes near the galactic plane block visible light from reaching us, making it extremely difficult to study stars and structures on the opposite side. Infrared and radio telescopes can peer through some of this obscuration, and the Gaia Space Observatory has mapped the positions and motions of nearly 2 billion stars with unprecedented precision. But even with Gaia's extraordinary data set, our knowledge of the far side remains fragmentary. There are entire spiral arm segments on the opposite half of the galaxy that we can barely resolve. Crossing the Milky Way would mean traversing regions that are not just distant but genuinely unknown. Unmapped territories that no human instrument has fully characterized. This is the physical reality of what crossing the galaxy means. It is not drawing a line on a diagram. It is traveling through a three-dimensional structure containing hundreds of billions of stars, trillions of planets, vast clouds of molecular hydrogen, lanes of interstellar dust, regions of scorching radiation, gravitational wells that can warp space-time, and stretches of near-perfect vacuum where the nearest star might be several light years away. And all of this is spinning. The entire disk rotates. Different parts rotate at different speeds. Stars closer to the center orbit faster than stars farther out. The galaxy is not a static object you can simply fly across in a straight line. It is a dynamic, rotating, evolving system, and any journey through it would need to account for the fact that the destination is moving while you travel toward it. Now, here is where the first crack in human intuition appears. Most people, when they hear that the Milky Way is 100,000 light years across, process that fact in roughly the same mental category as hearing that the Pacific Ocean is 12,000 miles wide, or that the distance from Earth to Mars averages about 140 million miles. Large numbers, impressive numbers, but numbers that feel like they belong on the same scale, just at different magnitudes. Your brain files them all under really far and moves on. This is a mistake. These distances do not belong on the same scale. They do not belong on adjacent scales. They do not even belong in the same conversation. The distance across the Milky Way is not merely bigger than the distance from Earth to Mars, the way a skyscraper is bigger than a house. The relationship is more like the difference between a single drop of water and the entire Atlantic Ocean. The Pacific Ocean is large by human standards, but a beam of light crosses it in about 1/15 of a second. The distance from Earth to Mars takes light between 3 and 22 minutes depending on orbital positions. The distance across the Milky Way takes light 100,000 years. 100,000 years. You go from fractions of a second, minutes, to a span of time longer than all of recorded human civilization, and you are still inside the same galaxy. The jumps between these scales are so enormous that your brain's instinct to group them together as big distances actively prevents you from comprehending the true situation. They are not points on a single ruler. They are completely different categories of reality. This categorical confusion is the single biggest obstacle to understanding galactic travel times. When people hear that it would take an extraordinarily long time to cross the Milky Way, they nod and think, well, yes, space is big, but they do not feel the actual magnitude because their brains are quietly sorting 100,000 light years into the same mental drawer as 140 million miles to Mars. Those two distances have almost nothing in common, and until you forcibly separate them in your mind, until you build a ladder of comparisons that shows you exactly how each step dwarfs the one before it, you cannot begin to grasp what galactic distance truly means. Here is one way to begin separating them. Light travels from the Earth to the Moon in about 1.25 seconds. That is a distance of roughly 239,000 miles. A manned spacecraft can cover that gap in about 3 days. Humanity has actually done this. We sent people to the Moon and brought them back alive. It is an achievable distance. Now step outward. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. That is 93 million miles. We have sent robotic probes to the Sun's vicinity. The Parker Solar Probe, the fastest human-made object ever, at its peak velocity of 430,000 miles per hour, dives close to the solar surface regularly. The inner solar system is within our technological reach. Step outward again. Light from the Sun takes about 5.5 hours to reach Pluto. The New Horizons spacecraft, traveling at roughly 36,000 miles per hour, took 9.5 years to make that journey. Pluto represents the outer boundary of what humanity has explored with dedicated flyby missions. We have reached the edge of our solar neighborhood. Now here is the jump that breaks everything. The nearest star system, Alpha Centauri, sits 4.25 light years away. That is roughly 25 trillion miles. Compared to the distance from the Sun to Pluto, which is about 3.5 billion miles, the jump to Alpha Centauri does not merely add more distance. It multiplies the distance by a factor so large that the entire solar system, everything humanity has ever visited or studied up close, shrinks to a rounding error. The gulf between the outermost planet and the nearest star is not a gap you cross by going a bit farther. It is a gap that belongs to an entirely different category of distance, one that makes the solar system look like a puddle next to an ocean. That single jump from the edge of our solar system to the closest neighboring star is already beyond anything human engineering has attempted or seriously planned for. At Voyager 1's speed of 38,000 miles per hour, the trip to Alpha Centauri would take approximately 75,000 years, and Alpha Centauri is the closest star. It is the nearest front porch. It is the house next door. Crossing the Milky Way is not reaching the house next door. Crossing the Milky Way is reaching a point roughly 23,500 times farther away than Alpha Centauri. If the jump from Pluto to Alpha Centauri multiplied the distance by 7,000, the jump from Alpha Centauri to the far edge of the galaxy multiplies it again by more than 23,000. You are stacking multiplication on top of multiplication, each factor so large that the previous distance becomes a rounding error. This is why the galaxy does not work like a map. A map implies traversability. It implies that the space between 2 points is something you can move through in a reasonable period of time, given sufficient speed or technology. The Milky Way is not that kind of space. The distances within it are so large that they transform the concept of travel from a practical question into something closer to a thought experiment. You can talk about crossing the galaxy, you can calculate the time it would take, but the numbers that come out of those calculations are so far beyond any meaningful human reference frame that the journey stops being a journey and starts being an abstraction. And yet the numbers are real. The galaxy is real. The distances are real. They exist whether we can comprehend them or not. 100,000 light years of stars, gas, dust, radiation, gravity, and innumerable, every mile of it waiting to be crossed by anything brave or foolish enough to try. But how long would that crossing actually take? That depends entirely on how fast you go. And what comes next reveals something deeply unsettling about speed, distance, the geometry of the galaxy we call home. Because the Milky Way does not merely punish slow travelers, it punishes fast ones too. It punishes every speed humans have ever achieved, or even imagined achieving. And it does so with a kind of mathematical brutality that makes the problem feel less like an engineering challenge, and more like a fundamental law of cosmic architecture, designed specifically to keep us exactly where we are. Those numbers sit in your mind right now as abstractions. 100,000 light years, 588 quadrillion miles, 23,500 times the distance to Alpha Centauri. You heard them. You may have even tried to process them, but you did not feel them. Your brain acknowledged the figures the way it acknowledges the national debt, or the number of grains of sand on a beach. It filed them under incomprehensibly large and moved on, because that is what human brains do with numbers that exceed lived experience. They round them all down to the same emotional category, big. But big is not good enough here. The distance across the Milky Way is not just big. It is big in a way that is qualitatively different from every other distance you have ever encountered. And the only way to force your intuition to register that difference is to build a ladder of concrete comparisons, rung by rung, starting from things you can actually picture, and then watch as the ladder snaps under the weight of galactic reality. Let us begin with something you can hold in your hand. Take a standard 12-inch classroom globe. On that globe, the distance from New York to London spans roughly 3 inches. The highest mountain on Earth, Everest, would be a bump so tiny you could not feel it with your fingertip. The deepest ocean trench would be an equally invisible scratch. The entire atmosphere, every molecule of air you have ever breathed, would form a film thinner than a coat of varnish. This is your world reduced to something you can spin on a desk. Now, on that same scale, where would the moon be? About 30 feet away, roughly the length of a school bus. You could walk there in 10 seconds. That is the Earth-Moon distance, the farthest any human being has ever physically travelled, reduced to a casual stroll across a classroom. The moon feels close on a globe. It feels achievable, and it was achievable. We went there 6 times. Now, where would the sun be on this scale? Over 2 miles away, a solid 40-minute walk. And the sun itself, at this scale, would be a glowing sphere roughly 100 feet across, about the length of a full-grown blue whale, sitting in a parking lot several neighborhoods from your classroom. The inner solar system, Mercury through Mars, would all fit within that 2-mile radius. Still walkable, still human, still something your body understands. But here is where the first crack opens. Where is Pluto on this scale? Pluto orbits at an average distance of about 3.7 billion miles from the Sun. On our 12-inch globe scale, that places Pluto roughly 88 miles away. Not 88 feet, 88 miles. You have gone from a 40-minute walk to the Sun to roughly the driving distance from New York City to Philadelphia. The solar system, which felt so compact at its inner edge, is suddenly stretched to the size of a small state. The New Horizons, the spacecraft that actually made this journey, needed 9.5 years to cover that distance. That 88-mile hike to Pluto represents the absolute frontier of human exploration. No spacecraft has been sent to a specific destination beyond Pluto. Voyager 1 and 2 have traveled farther, but they were not aimed at any target past the outer planets. They are simply coasting, drifting outward through interstellar space, with no destination and no way to stop. The 88-mile mark on our scale model is the edge of everything humanity has deliberately reached out and touched. Beyond that point, we have only drifters and silence. Now comes the rung that shatters the ladder. Where is Alpha Centauri, the nearest star system on this scale? Remember, on our 12-inch globe, The Sun is just over 2 miles away and Pluto is 88 miles out. Alpha Centauri, at 4.25 light years distant, would sit approximately 600,000 miles from your classroom. That is more than twice the real distance from the Earth to the Moon. To visit the nearest star on your scale model, you would need to travel a distance equivalent to 2.5 real trips to the actual Moon. You just went from an 88-mile drive to a 600,000-mile odyssey. You have not even left the Sun's closest stellar neighborhood. The nearest front porch in the galaxy requires a journey that, even on a shrunken model, dwarfs the greatest voyage humanity has ever accomplished. Sit with that comparison for a moment, because it is the single most important ratio in this entire story. The jump from the edge of the solar system to the nearest star is not a step, it is a chasm. On the scale model, Pluto is 88 miles away. Alpha Centauri is 600,000 miles away. That is a multiplication factor of nearly 7,000. Everything humanity has ever explored, every moon landing, every Mars rover, every Pluto flyby, occupies a zone so tiny compared to the interstellar gulf that it barely registers. If the solar system were a single footstep, the gap to Alpha Centauri would be a 3-mile walk. We have taken the step. We have not even begun the walk. Now we reach the rung where the ladder does not just crack, it disintegrates entirely, because Alpha Centauri is not the destination. Alpha Centauri is the very first star beyond our own. The nearest neighbor in a galaxy containing hundreds of billions of stars spread across 100,000 light years. On our 12-inch globe scale, we established that Alpha Centauri sits 600,000 miles away, the far edge of the Milky Way. The point you would need to reach to complete the crossing sits approximately 14 billion miles away on this same scale. Let that register. On a model where the Earth is 12 inches wide and you can hold it in your lap, the opposite edge of the galaxy is 14 billion miles from your classroom. That is nearly 4 times the real-world distance from the Sun to Pluto. Your scale model of the galaxy would stretch from the real Earth past the real orbits of Jupiter, Saturn, Uranus, Neptune, and Pluto, and keep going deep into interstellar space. This is the comparison that breaks human intuition permanently. On a model where the entire Earth shrinks to the size of a globe you can carry under your arm, the galaxy remains so vast that it would engulf most of the inner solar system. You cannot shrink the galaxy down to human scale. You can shrink mountains, you can shrink oceans, you can shrink the solar system to something that fits inside a small town. But the Milky Way resists compression. No matter how tiny you make the Earth, the galaxy stays enormous. It is too large to model at any scale that a human being can physically interact with. The ratio between human accessible distances and galactic distances is simply too extreme. This is not a failure of imagination. It is a mathematical rule. The distances involved span too many orders of magnitude for any single analogy to bridge them. When scientists talk about the Milky Way being 100,000 light years across, they are describing something that exceeds human spatial intuition by roughly 16 orders of magnitude, compared to the distances we navigate in daily life. For context, the difference between a single grain of sand and the entire diameter of Earth is only 10 orders of magnitude. The galaxy exceeds even that enormous ratio by another factor of 1,000,000. The gap between your commute to work and a trip across the galaxy occupies the same mathematical territory as the gap between a virus and a mountain range. Your brain is not equipped to hold both of those realities simultaneously. Nobody's brain is. The limitation is not intellectual laziness, it is architecture. Human spatial reasoning evolved to track predators across a savanna, to estimate the distance to a water source, and to navigate a few dozen miles of terrain on foot. It did not evolve to process 588 quadrillion miles. Nothing in evolutionary history required that capacity, so it does not exist. This is why analogies matter here more than raw numbers. Numbers fail at this scale, they become noise. But analogies that walk you through the jumps, rung by rung, and force you to notice the moment when each previous step becomes invisible, Those can at least approximate the feeling of galactic distance, even if they cannot truly replicate it. And the most devastating analogy of all requires no globe, no football field, no walk around the Earth. It requires only a trip to the beach. Pick up a single grain of sand. Hold it between your thumb and forefinger. This grain, roughly 0.5 millimeter across, represents the entire solar system. Everything humanity has ever known. Every planet, every moon, every asteroid, every comet, every spacecraft we have launched, every photon of sunlight that has ever warmed your skin, all of it, compressed into a single grain of sand. Now set that grain down on the beach and look around. The Milky Way, at this scale, is the entire beach, not a small beach. A beach stretching dozens of miles in each direction. The sand beneath your feet, the dunes behind you, the coastline extending to the horizon. Every grain on that beach represents a volume of space comparable to our solar system, and there are hundreds of billions of grains. Your grain, the one containing everything you have ever experienced, sits somewhere along one of the outer curves of the shoreline, unremarkable, indistinguishable from its neighbors, surrounded by an unimaginable number of other grains that you will never visit, never see up close, never even confirm contain what you think they contain. Crossing the Milky Way means crossing that entire beach. From your grain of sand to the most distant grain on the opposite shore, miles away, passing over billions of other grains in between. And you are not walking. You are crawling. You are crawling at a pace so slow relative to the beach that you would need millions of years to cover a single stretch of wet sand. That is the scale. That is the reality. That is what the diagram on the poster does not show you. But even the beach analogy, powerful as it is, understates the emptiness of the galaxy. Beaches are packed tight. Grain touches grain. The Milky Way is nothing like that. The space between stars is overwhelmingly, oppressively empty. If you placed the sun at the center of a room the size of a basketball court, and shrank it down to the size of a peppercorn, a tiny speck sitting at half court, the nearest star would be another peppercorn sitting in a different city. Not a different neighborhood, a different city, roughly 36 miles away. Everything between those two peppercorns would be void. Blackness, vacuum, a few stray atoms of hydrogen per cubic centimeter, which is a density so low it qualifies as a better vacuum than anything ever produced in a laboratory on Earth. The interstellar medium is not merely empty by human standards, it is empty by the standards of the best vacuum chambers we can build. And this is typical. This is what most of the galaxy consists of. Stars separated by light years of functionally perfect nothingness. But calling it empty does not capture the experience. Empty implies an absence, a blank space waiting to be filled. The interstellar medium is not waiting for anything. It is a positive, hostile, aggressively barren environment with physical characteristics that would destroy any intuitive sense of location and progress, or direction that a human traveler might cling to. The temperature of interstellar space averages roughly 3 degrees above absolute zero, about minus 454 degrees Fahrenheit. That is colder than any natural surface in our solar system, colder than the night side of Pluto, colder than the shadowed craters at the lunar poles. The cosmic microwave background radiation, the afterglow of the Big Bang itself, bathes the entire universe in a faint thermal whisper at 2.7 Kelvin. And in most regions of interstellar space, that whisper is the dominant source of warmth. There is so little matter between the stars that temperature almost ceases to be a meaningful concept. Individual atoms may carry kinetic energy equivalent to thousands of degrees, but they are so sparse that they transfer essentially no heat to anything they touch. A human body exposed to interstellar space would not freeze the way it freezes on a cold night on Earth. It would radiate its thermal energy outward into the void, slowly cooling toward equilibrium with the background radiation. Losing heat, not because something cold is touching it, but because nothing is touching it at all. The emptiness itself is the cold. The density of this medium is almost impossible to convey in human terms. In the air you are breathing right now, there are roughly 25 quintillion molecules per cubic centimeter. That is a 2 and a 5 followed by 19 zeros. In a typical region of interstellar space between the spiral arms, the density drops to approximately 1 atom per cubic centimeter. Not one molecule, one atom. Usually hydrogen, sometimes helium, occasionally a stray particle of dust smaller than a wavelength of visible light. The ratio between the density of the air in your lungs and the density of interstellar space is comparable to the ratio between the mass of the Earth and the mass of a single grain of table salt. You would need to sweep up the atoms scattered across roughly 27 million cubic kilometers of interstellar medium, a volume comparable to all the glacial ice on the surface of the Earth, just to gather enough matter for a single human breath. The void between stars is not just empty compared to Earth, it is empty compared to emptiness. Laboratory vacuum chambers on Earth, the most sophisticated ones built for semiconductor fabrication and particle physics experiments, achieve pressures of roughly 100 particles per cubic centimeter. The interstellar medium is 100 times emptier than the best artificial vacuum humanity has ever produced. What this means for a traveler is a condition that no human being has ever remotely experienced. There would be no landmarks, no visible features in any direction for years or decades at a time. If your ship was somehow silent, with no internal hum of machinery, no vibration of engines, the external environment would be as close to absolute silence and absolute darkness as the universe can produce. The nearest star behind you would have long since faded to a point indistinguishable from the background star field. The nearest star ahead of you would not yet have grown noticeably brighter. You would drift in a featureless black void, surrounded by a panorama of stars that change so slowly over decades and centuries that no human eye could detect the movement. There would be no sense of motion, no wind, no resistance, no evidence that you were going anywhere at all, except the steadily climbing number on a navigation readout ticking off miles in the trillions. Interstellar dust would present the only tangible physical feature. Tangible is a generous word. Dust grains in interstellar space are measured in fractions of a micrometer, smaller than the wavelength of visible light, smaller than bacteria, smaller than anything you can see or feel. But they are not harmless. At any significant fraction of the speed of light, a collision with a dust grain delivers energy far out of proportion to its mass. A grain weighing a millionth of a gram, striking a spacecraft at 10% light speed, would release kinetic energy comparable to a hand grenade. At 50% light speed, the same grain hits with the energy of several kilograms of high explosive. At 99% light speed, a dust grain carries the energy of more than 100 kilograms of TNT. The void is not just empty, it is empty and armed. The faster you cross it, the more dangerous its near-nothingness becomes. This is the texture of galactic distance. It is not merely a large number printed in a textbook. It is trillions upon trillions of miles of frigid, silent, radiation-bathed vacuum, where matter is so scarce it barely qualifies as existing, where temperatures hover just above the theoretical basement of thermodynamics, and where the only physical features you encounter are particles so small they are invisible and so fast-moving relative to your ship that they can punch through metal. This is what fills the spaces between the stars. This is what you would need to endure, mile after mile, year after year, century after century, for timescales longer than civilizations last. The galaxy is not just wide, it is wide and merciless. Every mile of the crossing is a mile of this. This emptiness is crucial to understanding galactic travel times. It is not just that the galaxy is wide, it is that the galaxy is wide and almost entirely vacant. There are no waypoints, no refueling stations, no gravitational assists from conveniently placed objects. Once you leave the immediate gravitational neighborhood of the star, you enter a desert that stretches for trillions of miles before the next star's gravity becomes relevant. The journey across the galaxy is not a highway dotted with rest stops. It is an ocean crossing in a universe where islands are separated by distances that would take centuries to traverse, even at speeds humanity has never achieved. Consider what Voyager 1 has accomplished. It launched in 1977. It has been traveling through space for nearly 48 years. It is currently more than 15 billion miles from Earth, moving at approximately 38,000 miles per hour. It has crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar space. By any human standard, Voyager 1 has traveled an extraordinary distance. It is the farthest human-made object in existence, and in galactic terms, it has gone essentially nowhere. 15 billion miles is approximately 0.0026 light-years. The galaxy is 100,000 light-years across. Voyager 1 has covered roughly 1/40,000,000th of the distance needed to cross the Milky Way. If the galactic crossing were a marathon, 26.2 miles, Voyager 1 has traveled less than 1/16th of an inch, after nearly half a century of continuous flight. You would need a magnifying glass to find its progress on a marathon course map. You would need a microscope to measure it. This is not a reflection of Voyager's inadequacy. Voyager 1 is a triumph of human engineering. It was designed to explore the outer planets, and it did so brilliantly, returning some of the most iconic images in the history of science. But its journey reveals with merciless clarity the mismatch between human capability and galactic geometry. We built the fastest sustained interstellar traveler in human history, and after nearly 5 decades of flight, its contribution to crossing the galaxy would be invisible on any map drawn at galactic scale. There is a tendency, when confronted with these comparisons, to retreat into optimism. Surely future technology will close the gap. Surely faster engines, better propulsion, more advanced spacecraft will make interstellar distances manageable. And that instinct is not entirely wrong. Humanity will almost certainly build faster spacecraft. Ion drives, solar sails, nuclear pulse propulsion, laser-driven light sails. These are all concepts under active development or serious theoretical study. Some of them could plausibly accelerate a small probe to a few percent of the speed of light. Projects like Breakthrough Starshot have proposed sending gram-scale probes to Alpha Centauri at 20% light speed, arriving in roughly 20 years. That would be an extraordinary achievement, a genuine leap beyond anything we have done before. But here is the critical distinction that optimism tends to blur. Reaching Alpha Centauri and crossing the galaxy are not the same problems scaled up. They are different problems separated by a factor of more than 23,000. If Breakthrough Starshot succeeds and sends a probe to Alpha Centauri at 20% the speed of light, arriving in roughly 20 years, the same technology aimed at the far edge of the Milky Way would require approximately 500,000 years to complete the journey. 500,000 years. At 20% the speed of light, a speed that no macroscopic spacecraft has ever approached, and that would require energy investments beyond anything currently possible. Even that extraordinary technological leap, which has not yet been achieved, would produce a travel time so long that the entirety of human civilization, from the first Sumerian city-states to the present day, represents barely 1% of the journey duration. This is the trap that galactic distance sets for human ambition. Every improvement in speed that feels revolutionary, every breakthrough that seems to bring the stars within reach, gets crushed by the sheer multiplication factor that separates nearby stars from the galactic far side. You can double your speed. You can multiply it by 10. You can multiply it by 100. And the galaxy absorbs each improvement without flinching, returning travel times that remain measured in hundreds of thousands or millions of years. The distance is not just large. It is large in a way that resists technological rescue. It is large enough that even technologies we have not yet invented, technologies that might seem like magic to us today, would still produce journey times longer than the lifespan of most species that have ever existed on Earth. To appreciate just how stubbornly the galaxy resists compression, consider the following thought experiment. Imagine you could magically accelerate a spacecraft to the speed of the fastest human-made object ever, the Parker Solar Probe, at its peak velocity of 430,000 miles per hour. That speed, which close solar passes in late 2024, is roughly 0.064%, the speed of light. It is 11 times faster than Voyager 1. At that velocity, you could fly from New York to Los Angeles in about 20 seconds. You could reach the moon in roughly 33 minutes. You could arrive at Mars in just a few days at closest approach. These are dizzying speeds by any terrestrial standard. Now point that spacecraft on the far edge of the galaxy. At 430,000 miles per hour sustained, the crossing would take approximately 156 million years. 156 million years ago, the dinosaurs had not yet gone extinct. The Atlantic Ocean was narrower than it is today. India was an island drifting northward toward a collision with Asia that would eventually raise the Himalayas. The Earth itself was fundamentally different. Not just culturally or technologically different in the way it has changed during human history, but geologically, biologically, climatically different at a planetary level. The continents had different shapes. The atmosphere had different composition. The dominant life forms bore no resemblance to modern animals. That is the timescale. The fastest sprint humanity has ever achieved, applied to the width of the galaxy, produces a journey longer than the age of flowering plants. And this is the moment where the ladder truly breaks. Because you have now exhausted every rung. You started with the Earth and Moon, a distance humanity has actually covered. You climb to the Sun, to Mars, to Pluto, distances our probes have reached. You leap to Alpha Centauri, a distance no probe has crossed, but that near-future technology might theoretically bridge within decades. And now you are staring at the far edge of the galaxy, 100,000 light-years away, and there are no more rungs. There is no technology in development, no propulsion system under study, no theoretical framework in mainstream physics that offers a plausible path to crossing the galaxy within any time frame that a human civilization could survive, let alone a human life. The ladder does not just fail to reach the top, it reveals that there is no top. The galaxy is not the final rung of a very tall ladder. It is the point where the concept of a ladder stops making sense. Ladders are for distances that can be bridged incrementally. The Milky Way is a distance that defeats incrementalism. Each step you take, no matter how large, leaves you facing a remaining distance so enormous that your step is undetectable. You cannot inch your way across a galaxy. The math does not allow it. The timescales do not permit it. The distance absorbs every effort and returns a number that makes the effort feel meaningless. And yet the galaxy is right there. You can see it tonight. Step outside on a clear night, far from city lights, and that luminous band of stars stretching across the sky. That is it. That is the structure we have been discussing. 100,000 light-years of stars and gas and dust and emptiness spread across the sky so close it feels like you could reach up and run your fingers through it. The Milky Way does not look 100,000 light-years wide when you see it with your eyes. It looks intimate. It looks close. It looks like home. And that is perhaps the cruelest trick of galactic distance. The galaxy presents itself to your senses as a neighborhood, a familiar glow above your head, a comforting presence on a dark night. It hides its true nature behind the limitations of human perception. You see the glow, but not the gulf. You see the light, but not the void between the sources. The Milky Way shows you its beauty and conceals its brutality. What comes next will take the comparison further than comfort allows. We are going to ask a simple question. What if we actually tried? What if we launched a spacecraft today, or 100 years from now, or 1,000 years from now? At every speed from the merely ambitious to the physically impossible, how long would each attempt take? And the answers will reveal something that goes beyond impressive, or challenging, or even daunting. They will reveal that the galaxy does not merely resist crossing, it renders the concept almost meaningless. built the ladder and watched it collapse. You saw the distances stack up from the Moon to Mars to Pluto to Alpha Centauri to the galactic edge, each rung multiplying the last by factors so large that every previous step shrank to invisibility. But that collapse was a collapse of spatial intuition. You understood that the galaxy is wider than your brain can picture. You understood that no analogy fully captures 588 quadrillion miles. What you may not yet understand is something far more disturbing. The galaxy does not just defeat your sense of distance, it defeats speed itself. Every speed. All of them. From the slowest crawl humanity has achieved to the fastest velocity permitted by the laws of physics. The Milky Way takes each one, processes it through simple division, and returns a travel time so long it makes the effort feel like a cruel joke. This is about that joke. It is about what happens when you actually try to cross the galaxy, not with optimism, not with speculation, but with mathematics. It is about the moment you realize that the problem is not a lack of engineering. The problem is the universe itself. Let us start where humanity actually stands. Our fastest interstellar traveler, Voyager 1, moves at approximately 38,000 miles per hour. That is roughly 17 kilometers per second. In everyday terms, that speed would carry you from Los Angeles to New York in about 4 minutes. It would get you to the moon in roughly 6 hours. It is a speed that would be nearly incomprehensible to anyone born before the 20th century. And it is laughably, tragically, almost insultingly slow compared to the Milky Way. At Voyager 1's speed, crossing the galaxy would require approximately 1.77 billion years. Say that number out loud. 1.77 billion years. Not million, billion. To give that duration a concrete anchor, consider what Earth looked like 1.77 billion years ago. There were no animals. There were no plants. There were no fungi. The most complex life forms on the entire planet were single-celled organisms, some of which had only recently figured out how to bundle together into rudimentary colonies. Multicellular life as we know it did not exist. The atmosphere contained only a fraction of the free oxygen it holds today. The continents were barren slabs of rock baking under a sun that was dimmer than it is today. If you had stood on the shore of that ancient Earth and launched a spacecraft at Voyager 1's speed toward the far edge of the galaxy, and if that spacecraft somehow survived every hazard of interstellar space for nearly 2 billion years, it would be arriving right about now. The entire history of complex life on Earth, every organism more sophisticated than a blob of cells, fits inside the travel time. Every fish, every dinosaur, every mammal, every primate, every human being who has ever drawn breath occupies a sliver of the timeline, so thin it would not show up on a graph. That result should stop you cold. But the natural human response is to think about going faster. Fine, Voyager is slow. What about something quicker? And this is where the trap reveals its teeth, because the galaxy punishes faster speeds with the same impersonal brutality. You can climb the speed ladder as high as you want. The galaxy adjusts the travel time, hands it back to you, and the number is still devastating. Take the Parker Solar Probe, the fastest human-made object ever constructed. During its closest approaches to the Sun in 2024 and 2025, it reached a peak velocity of approximately 430,000 miles per hour. That is 0.064% the speed of light. It is roughly 11 times faster than Voyager 1. At that blistering pace, you could fly from Earth to Mars in a matter of days rather than months. You could reach Jupiter in a few weeks. It feels fast because it is fast, at least by the standards of anything humans have ever built. Crossing the Milky Way at 430,000 miles per hour would take approximately 156 million years. You have multiplied your speed by 11, and you have shaved off roughly 91% of the travel time. That sounds like progress until you examine what 156 million years actually means. That is more than twice the span since the asteroid that killed the non-avian dinosaurs struck the Yucatan Peninsula. It is older than the Rocky Mountains. It is older than the modern Atlantic Ocean at its current width. The continents of Earth would rearrange themselves multiple times during the journey. Species would arise, dominate the planet, and go extinct in cycles that repeat dozens of times before the spacecraft reach the halfway mark. The fastest object humanity has ever created reduces the galactic crossing from 1.75 billion years to 156 million years. Both of those numbers land so far outside human experience that the improvement is emotion and meaningless. You have traded one incomprehensible number for a slightly smaller incomprehensible number. So let us push harder. Forget about current technology. Forget about rockets and gravity assists and solar sails. Imagine a spacecraft traveling at 1% the speed of light. That is roughly 6.7 million miles per hour. No spacecraft, no bullet, no explosion, no particle accelerator product on Earth moves at this speed in any sustained way. Achieving 1% light speed with a macroscopic payload would require energy budgets so far beyond current capability that the engineering challenges alone could occupy physicists for centuries. But let us assume we solve those challenges. Let us assume we build the engine, generate the fuel, and accelerate a ship to 1% the speed of light. How long does the crossing take? 10 million years. At 1% of the absolute cosmic speed limit, the journey across our own galaxy requires 10 million years. The human species, Homo sapiens, has existed for roughly 300,000 years. 10 million years is more than 33 times the entire duration of our species. Every stone tool, every cave painting, every empire, every war, every scientific discovery, every love story and funeral and sunrise that any human being has ever experienced fits inside less than 3% of the travel time. At 1% light speed, you would cross the Milky Way and arrive at the other side to find that the species that launched you had, in all probability, either evolved into something unrecognizable or ceased to exist entirely. The Earth that sent you off would be a different planet, not metaphorically different. Geologically, climatically, biologically different. Coastlines shifted, ice ages come and gone multiple times. Entire branches of the evolutionary tree grown, flourished, and vanished. The journey would outlast not just your civilization, but your entire biological lineage. Perhaps 1% is too modest. Let us try 10% the speed of light. 67 million miles per hour. This is the realm of serious speculative propulsion. Nuclear pulse drives, antimatter engines, concepts that live on the boundary between ambitious physics and outright science fiction. 10% light speed is a velocity at which relativistic effects begin to become noticeable, though they are still modest at this fraction. The kinetic energy of a ship mass object at 10% light speed would be staggering, equivalent to multiple nuclear arsenals packed into the motion of a single vessel. But assume it is done. Assume the impossible engine is built, the impossible fuel is loaded, and the ship is hurled across the galactic disk at 10% the speed of light. Before we look at that travel time, it is worth pausing to understand just how staggering the energy requirement actually is, because the numbers reveal a barrier almost as impassable as the distance itself. The kinetic energy of a moving object scales with the square of its velocity at everyday speeds, and climbs even more steeply as you approach light speed, due to relativistic mass increase. At low speeds, doubling your velocity quadruples the energy needed. At high fractions of light speed, the relationship becomes far more punishing. Let us make it concrete. Consider a spacecraft with a mass of 10,000 metric tons. That is roughly 25 times the mass of the International Space Station. Still modest for any vessel expected to sustain a crew across interstellar distances, but useful as a benchmark. Accelerating 1,000 metric tons to 1% of the speed of light requires approximately 4.5 times 10 to the 19th joules of energy. For comparison, the total energy consumption of the entire human civilization in a year is roughly 5.8 times 10 to the 20th joules. So accelerating a single 10,000-ton spacecraft to 1% light speed would would consume roughly 8% of the world's total annual energy output. That is the energy produced by every power plant, every engine, every furnace, every battery on the planet over an entire year, and you would need to focus nearly a tenth of it into a single spacecraft. And 1% light speed, as we have seen, still produces a crossing time of 10 million years. The speed is not fast enough, and the energy cost is already civilizational in scale. Now raise the speed to 10% light speed. Energy scales roughly with the square of velocity at these subrelativistic speeds. So you need approximately 100 times more energy. That is roughly 4.5 times 10 to the 21st joules. This exceeds the total annual energy output of human civilization by a factor of almost 8. You would need to harness approximately 8 years of total global energy production and channel it entirely into accelerating a single ship mass object. No heating, no lighting, no transportation, no industry. Every watt produced on Earth for 8 straight years poured into one spacecraft. And even if you could do it, the trip still takes 1 million years. At 50% light speed, the relativistic effects become significant and the energy climbs dramatically. The Lorentz factor at half light speed is approximately 1.15, which increases the effective mass of the spacecraft by 15%. The kinetic energy required reaches approximately 1.4 times 10 to the 23rd joules. That is roughly 240 years of total global energy production. The entirety of human industrial civilization since the steam engine, every kilowatt hour ever generated by coal, oil, nuclear, solar, wind, and hydro combined, would not be enough. You would need to multiply that total by roughly 9. At 99% light speed, the Lorentz factor climbs to approximately 7.1, meaning the relativistic mass of the spacecraft has increased 7-fold. The energy required approaches 5.5 times 10 to the 24th joules. This is roughly 9,500 years of total human energy production. But even this incomprehensible figure understates the problem, because we have been talking about acceleration only. We have not discussed deceleration. A spacecraft arriving at its destination at 99% light speed needs to slow down, or it will flash past in a fraction of a second after a journey of 100 millennia. Decelerating from 99% light speed requires the same energy as accelerating to it. The total energy budget for a round-trip speed profile, accelerate and decelerate, doubles to roughly 19,000 years of global energy output for a single ship. And here is the factor that makes all of this truly impossible. These calculations assume 100% efficiency. Every joule of energy produced goes directly into accelerating the spacecraft with zero waste, zero heat loss, zero inefficiency of any kind. No real propulsion system achieves anything close to this. Chemical rockets operate at efficiencies measured in fractions of a percent when you account for the mass of fuel they must carry. Even theoretical antimatter drives, which convert mass directly into energy via matter-antimatter annihilation, face enormous practical losses. The real energy requirements for any physically plausible propulsion system would be orders of magnitude higher than the theoretical minimums described above. The energy barrier does not merely complement the distance barrier, it reinforces it from a completely different direction. Even if the travel times were acceptable, even if you were willing to spend 1 million years crossing the galaxy, you would still face the problem of generating and focusing more energy than your entire civilization produces in centuries, possibly millennia, into a single vehicle. The galaxy demands not just time you cannot spare, but energy you cannot produce. It attacks the problem from both flanks simultaneously, and neither flank shows any sign of yielding. The crossing takes 1 million years. 1 million years. A number that finally begins to feel approachable, perhaps, compared to the billions and hundreds of millions that preceded it. But do not let the relative modesty of 1 million years fool you into thinking it is manageable. 1 million years ago, Homo sapiens did not exist. Our ancestors were Homo erectus, a species that had mastered fire and basic stone tools but had not developed complex language, symbolic art, agriculture, or any of the higher cognitive capacities that define modern humanity. The entire arc of human cultural evolution, from the first controlled fires to the International Space Station, occupies less than a third of 1 million years. The species itself has changed physically and cognitively over far shorter spans, meaning the beings who arrive would bear little resemblance to the beings who departed. The oldest known human structures are roughly 12,000 years old. The oldest continuously spoken language lineages may be 10,000 years old, and even that has changed beyond recognition from its original form. 1 million years is not a long time on an astronomical scale, but it is an eternity on a human one. It dwarfs every social structure, every political system, every cultural tradition humanity has ever produced, by factors of 100. This is the point where the concept of a generation ship usually enters the conversation. If the journey takes 1 million years, perhaps you do not send individuals. Perhaps you send a self-sustaining colony, a ship large enough to house thousands of people who live, reproduce, die aboard the vessel, while their descendants continue the journey. Generation after generation, the ship crawls toward its destination, a civilization unto itself hurtling through interstellar space. The idea is romantic. It is also, at galactic scales, absurd. Consider the engineering. A generation ship capable of sustaining a human population for 1 million years would need to maintain its hull integrity, its life support systems, its food production, its social structures, and its navigational accuracy across roughly 40,000 human generations. 40,000 successive generations of human beings, each born, raised, and buried inside the same vessel, each inheriting the mission from the previous generation, passing it to the next. For context, the entirety of recorded human history spans roughly 250 generations. The total span from the first anatomically modern humans to the present is roughly 12,000 generations. A million-year generation ship would need to sustain coherent purpose and functional systems for more than 3 times the number of generations that separate us from the emergence of our species. No material we know of lasts that long without degradation. No sealed ecosystem has maintained balance for more than a few years in laboratory settings. The engineering requirements alone span timescales that mock every structure humanity has ever built. The generation ship is a concept that works beautifully for journeys of a few centuries. At galactic timescales, it becomes a fantasy dressed in engineering language, but the generation ship problem exposes something even deeper than engineering failure. It exposes the certainty that you are not just leaving a place, you are leaving a time, and the time you leave will not wait for you. Consider what Earth looks like after each of the timescales we have discussed. At 10 million years, the duration of a crossing at 1% light speed, the continents will have shifted noticeably. The Atlantic Ocean will be over 100 miles wider. The Mediterranean Sea will have narrowed dramatically, squeezed by the slow northward drift of Africa into Europe. Mountain ranges that do not currently exist will have risen and begun to erode. Rivers will have carved new valleys. Coastlines will bear no resemblance to modern maps. Tens of thousands of species currently alive will have gone extinct, replaced by descendants adapted to environments that do not yet exist. If any trace of human civilization survives, it will be geological, faint chemical signatures in sedimentary rock, a thin stratum of unusual isotopic ratios in microplastics, marking the era when one species briefly reshaped the planet's surface. No building will remain, no road, no city, no dam. Erosion, tectonic recycling, and biological decomposition will have reclaimed everything. The species that launched your ship will be as distant to whatever inhabits the Earth as the first fish are to you. At 1 million years, the timescale of a 10% lightspeed crossing, the changes are less dramatic but no less total from a human perspective. Languages will have transformed beyond all recognition. Linguistic studies suggest that languages become mutually unintelligible within roughly 500 to 1,000 years of separation. After 1,000,000 years, the descendants of every language currently spoken on Earth would share no recognizable vocabulary, grammar, or phonetic system with their ancestors. Every word you know will be extinct. Every story, every song, every joke, every prayer will have been forgotten, reinvented, forgotten again, and reinvented in forms you would not recognize as related to the originals. Political and social structures will have cycled through thousands of iterations, the longest-lasting human institutions that have ever existed. Certain religious traditions, certain monarchies, lasted roughly 2,000 to 3,000 years. 1,000,000 years contains 300 to 500 complete cycles of rise, dominance, decline, and collapse of the most durable institutions humanity has ever built. Whatever exists on Earth after 1,000,000 years will be as foreign to you as the culture of Homo erectus is to a modern human. Because at least Homo erectus was the same genus. After 1,000,000 years of evolution, your descendants may not be. Even at the light speed minimum of 100,000 years, the erasure is nearly complete. 100,000 years ago, anatomically modern humans existed, but behavioral modernity, art, complex language, symbolic thought was only beginning to emerge. The entire arc of human cognitive and cultural development fits inside 100,000 years. If you launched a lightspeed ship today and arrived at the far edge of the galaxy, you would step out into a universe where Earth has undergone as much change as separates the first cave paintings from the smartphone in your pocket. Everything you knew, everyone you loved, every institution you served, every nation you belonged to, will be not just gone, but archaeologically unrecoverable. You will have arrived somewhere, but you will have come from nowhere, because the place you left will have ceased to exist in every sense that matters to a conscious being. This is the dimension of galactic crossing that pure mathematics obscures. The numbers tell you how long the trip takes. They do not tell you what the trip costs in human terms, and the cost is total. It is the complete severance of every connection to everything you have ever known. It is not a journey you return from, because there is nothing to return to. The galaxy does not just demand your time, it demands your past. It demands the world that sent you. It demands the erasure of your origin as the price of your arrival. And no speed fast enough to be interesting is fast enough to avoid paying that price. So let us abandon realism entirely. Let us go to the absolute limit, the speed of light, 186,000 miles per second, 670 million miles per hour, the fastest anything can move through the fabric of space-time according to every confirmed experiment in physics. Nothing with mass can actually reach light speed. Einstein's special relativity demonstrates that as an object with mass accelerates toward the speed of light, the energy required to continue accelerating increases without bound. Approaching infinity as you approach light speed, you would need infinite energy to push a physical object to the speed of light. It cannot be done. But let us pretend. Let us wave away physics and ask the simplest possible question. If you could travel at the speed of light itself, how long would it take to cross the Milky Way? 100,000 years. That is not a calculation. That is a definition. The galaxy is 100,000 light years wide. Light takes 100,000 years to cross it. That is what the unit means. And 100,000 years is the most optimistic possible answer the universe will ever give to this question. Because nothing can go faster. Light speed is not a speed limit in the way that a highway speed limit is a speed limit. It is not an arbitrary rule imposed by an authority that could choose a different number. It is woven into the geometry of space-time itself. The speed of light is the rate at which causality propagates through the universe. Exceeding it does not just require better technology. It requires a different universe operating under different physical laws. In this universe, with these laws, 100,000 years is the basement. It is the minimum possible crossing time. and it is a duration that stretches roughly 10 to 20 times longer than the entire history of human civilization. Now, there is a subtlety here that demands attention, because it is often misunderstood and sometimes offered as a kind of escape hatch from the problem of galactic distance. Special relativity contains a phenomenon called time dilation. When an object moves at a significant fraction of the speed of light relative to another observer, time passes more slowly for the moving object than for the stationary one. This is not a thought experiment or a theoretical curiosity. It is confirmed physics, measured in particle accelerators, and observed in the behavior of cosmic rays. Time dilation means that a traveler moving at very high speed would experience less elapsed time than an observer watching from Earth. At modest fractions of light speed, the effect is negligible. At 10% light speed, time on the ship would pass roughly 0.5% more slowly than time on Earth, barely noticeable. But at extreme fractions, the dilation becomes dramatic. At 90% light speed, time on the ship passes about 2.3 times slower than on Earth. At 99% light speed, the factor jumps to roughly 7. At 99.99%, the factor reaches about 70. And at 99.9999%, the dilation factor reaches roughly 700. This means that, in principle, a traveler moving at 99.99% of light speed could cross the galaxy in what feels to them like roughly 1,400 years of onboard time, while 100,000 years pass in the outside universe. Push the speed even closer to light speed, piling nines onto the decimal, you can compress the subjective experience further. At 99.9999%, the traveler might experience roughly a century and a half while the galaxy ages 100 millennia around them. This sounds like a solution. It is not. Time dilation is real, but it does not shrink the galaxy. It shrinks the experience of the traveler. The universe outside the ship still ages at full speed. 100,000 years still pass for everyone and everything not aboard the vessel. The Earth the travelers left behind undergoes 100,000 years of geological change, biological evolution, and civilizational transformation. By the time the ship arrives at the far edge of the galaxy, the civilization that launched it has been gone for thousands of centuries. Any message sent back would take another 100,000 years to arrive. There is no one to receive it. Time dilation allows you to survive the crossing in a personal sense, but it does so by detaching you from everything and everyone you have ever known by a temporal gulf so vast that the word return loses its meaning. You are not crossing the galaxy and coming home. You are crossing the galaxy and arriving in a future so distant that it constitutes a different world. There is also the energy problem, which time dilation does nothing to solve. Accelerating a spacecraft at 99.99% of light speed requires energy inputs that dwarf anything humanity has produced in its entire history. The kinetic energy of even a modest ship at that velocity would exceed the total energy output of the sun over several days. Sustaining that speed, navigating around interstellar debris at a velocity where a collision with a grain of dust would release energy comparable to a bomb, decelerating at the other end so you do not simply fly past your destination at nearly the speed of light. These are problems so far beyond current engineering that calling them challenges understates the gulf by orders of magnitude. Here is the deepest cut of all. Everything discussed so far assumes travel in a straight line, unimpeded, through empty space. The actual galaxy is not empty. It contains gas clouds, dust lanes, star systems, gravitational fields, radiation zones, and the dense, chaotic environment near the galactic center. Any real crossing would need to navigate these hazards or account for the drag and deflection they impose. The straight-line distance of 100,000 light-years is a theoretical minimum. A practical crossing, if such a thing could ever exist, would be longer. Let us assemble the results into a single unflinching summary. At Voyager 1 speed, the crossing takes 1.77 billion years. At the Parker Solar Probe's peak speed, 156 million years. At At 1% light speed, 10 million years. At 10% light speed, 1 million years. At 50% light speed, 200,000 years. At 90% light speed, roughly 111,000 years. At 99%, approximately 101,000 years. At light speed itself, 100,000 years flat. The progression is revealing. You gain enormous reductions at the lower end of the speed range. Going from Voyager speed to 1% light speed cuts the travel time by a factor of nearly 200. But as you climb into the high fractions of light speed, the returns diminish savagely. Going from 50% to 90% light speed saves you less than 90,000 years. Going from 90% to 99% saves barely 10,000. Going from 99% to 100%, crossing a boundary that physics says cannot actually be crossed, saves you only about 1,000 years. The galaxy gives back less and less for each increase in speed, guarding the final 100,000 years with the stubbornness of a physical law, because that is exactly what it is. The speed of light is the floor. You cannot dig beneath it. 100,000 years is the absolute minimum, and it is a duration that exceeds the entire history of human agriculture, human cities, human writing, human science, and human art combined, multiplied by 10. This is what it means to brace yourself. The Milky Way does not merely resist being crossed at slow speeds, which would be understandable and even expected. It resists being crossed at fast speeds. It resists being crossed at the fastest speed the universe allows. The galaxy is not a container that technology can shrink. It is a geometrical fact built into the structure of space-time. 100,000 light years is not a challenge to be overcome. It is a feature of reality, as fixed and non-negotiable as the charge of an electron or the mass of a proton. You can resent it, you can admire it, but you cannot change it. The numbers we have walked through are not speculative, they are arithmetic. Distance divided by speed equals time. The distance is confirmed by decades of astronomical observation. The speeds are either measured directly or derived from well-understood physics. The travel times follow inescapably. There is no hidden variable, no secret shortcut, no wormhole conveniently placed at the galactic center that rescues the journey from its mathematical verdict. There is only the galaxy, vast beyond intuition, and the speed of light, fast beyond experience, and the division of the former by the latter, which produces a number that should permanently alter how you think about the place you live. Because you do live here. You live inside this structure. You were born in it. You will die in it. And every human being who has ever existed or ever will exist will share that fate. The Milky Way is your home in the most literal sense possible. And it is a home you cannot cross. Not because you lack the will, not because you lack the imagination, not because you lack some future technology that a smarter species might invent, but because the galaxy is built on a scale where crossing it requires more time than more species has existed, more time than complex life has existed, more time than the journey has any right to demand of a living thing. What that means for humanity's place inside this uncrossable home, what it means for how we think about distance, ambition, and the boundaries of the possible, is where this story ends, and where a much harder truth begins. You now hold the numbers. You have seen the ladder built and broken. You have watched speed after speed thrown against the width of the galaxy and returned as a travel time measured in epochs. 100,000 years at light speed, 1 million years at 10%, 10 million years at 1%, 156 million years at the fastest velocity any human-made object has ever achieved, 1.77 billion years at the speed of Voyager 1, the farthest thing we have ever sent into the dark. These are not estimates. They are not guesses. They are the results of dividing a confirmed distance by confirmed or hypothetical speeds, and every result lands so far outside the boundaries of human experience that the question this script was built around, how long would it really take to cross the Milky Way, stops being a question about engineering or technology or ambition, It becomes a question about what kind of universe we actually live in. And the answer to that question is one that most people have never been forced to sit with. You live in a galaxy you cannot cross, not because crossing it is hard. Hard implies difficulty that effort can overcome. Climbing Everest is hard. Building a particle accelerator is hard. Landing on the moon was hard. Crossing the Milky Way is not hard. It is structurally excluded from the category of things that effort, ingenuity, or time can accomplish within any framework that connects to human existence. The galaxy is not presenting you with a challenge. It is presenting you with a boundary as fundamental and impassable as the speed of light itself, because it is the speed of light itself multiplied by a distance so large that even the cosmic speed limit cannot redeem it. This is a strange thing to realize about your own home. We call the Milky Way home. Every astronomy textbook, every documentary, every planetarium show invites you to think of the galaxy as your cosmic address. You live on Earth, in the solar system, in the Orion Arm, in the Milky Way galaxy. The language implies belonging. It implies residence. It implies the kind of relationship a person has with a house or a neighborhood or a city, the kind of place you can explore, learn the shape of, move through. But the relationship between a human being and the Milky Way is nothing like the relationship between a person and a house. It is more like the relationship between a bacterium and the ocean it floats in. The bacterium exists within the ocean. It is surrounded by it on all sides. It is made of materials drawn from it. In some technical sense, the ocean is its home, but the bacterium will never cross the ocean. It will never see more than an infinitesimal fraction of its volume. It will be born, live, and die in one negligibly small region, while the overwhelming majority of its home remains permanently beyond its reach. The ocean does not care about the bacterium. The ocean does not even know the bacterium is there. That is your relationship with the Milky Way. You live in it the way a microbe lives in the Pacific. The galaxy surrounds you. It defines the cosmic structure you inhabit. Its gravity holds your star in orbit. Its heavy elements, forged in ancient supernovae, compose your bones and blood. In every physical sense, you belong to this galaxy. And in every practical sense, the galaxy is closed to you. Not most of it, virtually all of it. Consider the numbers carefully. The solar system, the region humanity has actually explored with spacecraft, extends out to roughly 100 astronomical units, if you include the scattered disk objects beyond Pluto, perhaps 2,000 astronomical units, if you include the inner edge of the hypothesized Oort cloud. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. 2,000 astronomical units is roughly 3/100ths of a light year. The Milky Way is 100,000 light years across. The volume of space that humanity has even remotely explored represents less than 1/1,000,000,000th of 1% of the galaxy's volume. You could replicate the explored solar system trillions of times and still not fill a single spiral arm. Everything humanity has seen, touched, photographed, sampled, or studied with a physical instrument exists within a cocoon of space, so tiny compared to the galaxy that no visual representation can accurately depict both at the same scale. If the Milky Way were the size of the continental United States, the entire volume of space that humanity has explored with spacecraft would fit inside a single basketball. Now extend the boundary outward to include the nearest stars. Alpha Centauri sits 4¼ light years away. Barnard's star is about 6 light years. Wolf, 359, is roughly 8. Sirius, the brightest star in the night sky, lies 8½ light years from Earth. Within 20 light years, there are roughly 130 known star systems. This is the realistic frontier of human ambition for the next few centuries. Projects like Breakthrough Starshot aspire to send tiny probes to Alpha Centauri within a generation. Larger, crewed missions to nearby stars remain firmly in the domain of speculation, but they are at least conceivable within the laws of physics using technologies that could plausibly be developed in the coming centuries. The nearby stellar neighborhood, a sphere of perhaps 50 light-years centered on the Sun, represents the outermost boundary of what humanity might meaningfully explore within the next millennium if everything goes extraordinarily well. 50 light-years out of 100,000. That is 1/20th of 1% of the galactic diameter. A sphere 50 light-years in radius, encompassing every star system humanity might ever physically visit in the next 1,000 years of optimistic technological development, contains less than 1/1,000,000th of the galaxy's total volume. This is not pessimism. This is geometry. The galaxy is so large that even an aggressive multi-century expansion program that pushes humanity to dozens of nearby star systems would leave 99.9999% of the Milky Way untouched. We would spread across a small cluster of stellar neighbors and call it an interstellar civilization, and the galaxy would not notice. There is a word for this situation that nobody likes to use in the context of space exploration. The word is confinement. Humanity is confined, not by walls, not by a lack of vision, not by any technological barrier that ingenuity can dismantle. Confined by the raw, brute, inarguable width of the galaxy and the fixed speed at which information and matter can move through it, you are free to go anywhere you want within the Milky Way. The galaxy imposes no gatekeepers, no barriers, no permissions. It simply demands that you spend 100,000 years to reach the far side, even if you somehow achieve light speed, and it knows that this price is one no human being, no human society, no human species can afford to pay. The confinement is enforced not by restriction, but by cost. You are free to cross the ocean. You simply cannot survive the swim. This confinement has consequences that ripple outward in every direction. Consider communication. Even if a civilization exists on the far side of the Milky Way right now, broadcasting radio signals in every direction, the signals arriving at Earth tonight left their source 100,000 years ago. They carry news of events that occurred before the last ice age, before the first human city, before the domestication of the first animal. If we detected such a signal and immediately replied, our response would arrive at their location 100,000 years from now, carrying information about a civilization that has, in all likelihood, transformed beyond recognition or ceased to exist entirely in the interim. The round-trip communication time with the far side of the galaxy is 200,000 years. The concept of a conversation, of back and forth exchange, of dialogue, becomes meaningless at this timescale. You are not communicating. You are launching messages into a future so distant that the word reply no longer applies. This temporal abyss applies not just to the far side of the galaxy, but to most of it. A star system 30,000 light-years away, which is not even on the opposite side, but really on the other side of the galactic center, would require 60,000 years for a round-trip message at light speed. That is longer than the entire span of modern human civilization multiplied many times over. The galaxy is not just too wide to cross. It is too wide to talk across. Every region beyond a few thousand light-years exists in a state of communicative isolation, so profound that the concept of a galactic community, a galaxy-spanning network of civilizations sharing information and culture, is not merely difficult, it is physically precluded by the geometry of space-time. This realization carries a weight that is easy to intellectualize, difficult to feel. We are accustomed to thinking of isolation as something that can be overcome. Throughout human history, every barrier to communication and travel has eventually fallen. Oceans were crossed, continents were connected by telegraph, then telephone, then fiber optic cable. The moon was reached. Mars was photographed up close. The pattern of human progress has been a steady, triumphant expansion of reach, and it has conditioned us to expect that the trend will continue indefinitely. Galactic distance breaks this expectation. It does not bend to technological progress. It does not yield to determination. It sits at the intersection of distance and the speed of light. two quantities that are not subject to engineering. It produces timescales that no amount of cleverness can compress below a floor of 100,000 years. There is a temptation here to invoke exotic physics. Wormholes, warp drives, Alcubierre metrics, shortcuts through higher dimensional space. These concepts exist in theoretical physics, and they make for thrilling science fiction, but they remain, as of today, entirely speculative. No wormhole has ever been observed. No warp drive has ever been built or tested. The Alcubierre metric, while mathematically valid within general relativity, requires forms of energy, specifically negative energy density, that have never been produced in any quantity and may not be producible at all. Invoking these concepts to solve the problem of galactic distance is like invoking magic to solve the problem of mortality. It is not wrong to hope, it is not wrong to theorize, but it is wrong to treat unverified speculation as a counterargument to confirmed physics. The speed of light is confirmed. The width of the galaxy is confirmed. The resulting travel times are confirmed. Everything else is hope, and hope is fine. Hope is human. But this script is not about hope. It is about reality. The reality is this. You live inside a structure 100,000 light years wide. You are located roughly 26,000 light years from its center. The nearest edge of the disk is tens of thousands of light years away. The far edge is about 76,000 light years from your position. Even the center of your own galaxy, the supermassive black hole around which your star has been orbiting for 4.5 billion years, is so far away that light from it takes 26,000 years to reach you. You have never seen the galactic center as it exists now. You have only ever seen it as it existed 26,000 years ago, when humans were painting animals on cave walls and tracking mammoth herds across frozen tundra. The center of your own galaxy is hidden from you not just by dust and distance, but by time. Now expand the frame one final devastating step. The Milky Way is one galaxy. Current estimates place the total number of galaxies in the observable universe at approximately 2 trillion. 2 trillion galaxies, each containing billions or hundreds of billions of stars, each separated from its neighbors by millions of light years of intergalactic void. The nearest major galaxy, Andromeda, sits 2.5 million light years away. At light speed, reaching Andromeda would take 2.5 million years. The most distant observable galaxies lie more than 13 billion light years away. The space between us and them is expanding so rapidly that their light will eventually stop reaching us altogether. If crossing the Milky Way is structurally impossible on human timescales, crossing the intergalactic void is structurally impossible on civilizational timescales, on species timescales, on geological timescales. The gaps between galaxies dwarf the gaps between stars the same way the gaps between stars dwarf the gaps between planets. Each level of cosmic organization introduces another multiplication of distance that pushes travel times from the merely absurd to the genuinely infinite. You cannot cross your own galaxy. You certainly cannot cross the space between galaxies, and you absolutely cannot cross the observable universe, whose edges are already receding from us faster than light due to the expansion of space, placing them permanently and irrevocably beyond reach. The universe is structured in layers of inaccessibility. The solar system is accessible. The nearest stars are theoretically accessible at great cost and over long timescales. The galaxy is inaccessible. Other galaxies are profoundly inaccessible. The far reaches of the observable universe are absolutely inaccessible. And beyond the observable universe, in the regions from which light has not yet had time to reach us, lies a cosmos that is not merely inaccessible but fundamentally unknowable. Each layer contains more space, more stars, more potential worlds, and more distance than the layer before it, and each layer erects a barrier higher than the last. You do not just live in a big universe. You live in a universe that is architecturally designed, at every scale, to keep its contents separated from one another. This is not an accident. It is a consequence of fundamental physics. The The universe expanded from a hot, dense state roughly 13.8 billion years ago. That expansion created the distances that now separate galaxies, stars, and star systems. The speed of light, which governs the maximum rate of information transfer and physical travel, was set during the first moments of cosmic history and has remained constant ever since. The combination of cosmic expansion and the light speed limit reduces the isolation we observe at every scale. It is not a flaw in the design, it is the design. The universe is not a place built for crossing, it is a place built for containing. Every galaxy, every star system, every planet exists within its own pocket of space-time, connected to its neighbors by distances that function as barriers as effectively as any wall. What does this mean for you? Not for humanity in the abstract, not for hypothetical future civilizations. For you, the person listening to this, the person who looked up at the Milky Way on some clear night and felt a sense of belonging, a sense that this glowing band of stars was somehow yours. It means the galaxy is yours in the way the ocean belongs to a single fish. You can swim in your corner, you can feel the currents, you can sense the vastness extending in every direction, but you will never reach the far shore. You will never see more than an infinitesimal fraction of what the ocean contains. You belong to something enormous and beautiful, and overwhelmingly indifferent to your existence. Something that gave you the atoms in your body and the ground beneath your feet, and has no mechanism by which it can ever show you more than the tiniest glimpse of itself. There is a final image that brings this home. On a clear, dark night, far from city lights, the Milky Way stretches across the sky as a luminous river of soft white light. It arches overhead from horizon to horizon, dense near Sagittarius where the galactic center hides behind curtains of dust, fainter toward the outer edges where the spiral arms thin into scattered star fields. It is one of the most ancient and beautiful sights available to human eyes. Every civilization that has ever existed on Earth has looked up at this same band of light. They named it after milk, after rivers, after roads walked by gods and spirits. They built mythologies around it. They used it to navigate. They painted it on cave walls and wove it into creation stories. It feels close. It feels intimate. It feels, in some profound and wordless way, like it belongs to us. It does not. The light you see when you look at the Milky Way left its sources years, centuries, millennia ago. Some of the photons entering your eyes tonight have been travelling since before the Roman Empire. Some have been travelling since before the pyramids were built. Some of the faintest glow in the galactic band is the blended light of stars, so distant and so numerous that no single one is visible alone. Light that left its sources tens of thousands of years ago, when ice sheets covered half of Europe and our ancestors had not yet planted a single seed. You are not seeing the galaxy. You are seeing a composite of its past, a patchwork of moments stretching back thousands and tens of thousands of years, arriving simultaneously at your retina and creating the illusion of a single, unified, present-tense structure. The Milky Way you see tonight does not exist. It is a ghost image assembled from photons of different ages, a time-lapse exposed across millennia and projected onto the dome of your sky. The real Milky Way, the one that exists right now, is different. It's something no human being has ever seen, no human being ever will. Light does not travel fast enough to show it to you in real time. The galaxy is too wide for its own light to unify it into a single present. This is the
Good morning.
collapse, not just of distance, not just of speed, but of the assumption that the galaxy is a place at all, in the way that a city or a country is a place. A place is somewhere you can be present, somewhere that exists in a unified now. The Milky Way does not have a unified now. Its present is fragmented across 100,000 years of light travel time. Events happening right now on the far side of the galaxy will eventually be visible for 1,000 centuries. The galaxy is not a snapshot. It is a time-smeared ribbon of causally disconnected regions, each evolving independently.
Emerson Atkins. Ah, well.
So what do you think is the secret to happiness? I believe it is
I wholeheartedly agree with you, my friend. I find you so good, so clever, so nice things. Ah, well, I couldn't agree with more of you on this one. Well, you know, let's take it to the side. Could be, you never know. Absolutely, anyway. Yes. Oh, Arnold, that is absolutely delectable. I highly agree, approve of Kiss of Toast. Come, do you think I'm a nice guy, don't you? Come on, wait a minute. What? I mean, we think about it in a way. You never know. Could be. In a way. Didn't matter. When you think about it, when you think about it. When you think chicken, so chicken music, so chicken song. Come on, everyone, sing along, so chicken music, so chicken song. Follow me. For more hits like that, absolutely.
Good morning, ladies and gentlemen. I'd like to show you something about how full of it people are and how fickle and disingenuous they are. Right, watch this. Look. Right, at the end of this, I say, follow me, why not? I'd rather block. Oh, but you didn't block. You've commented here. Let's have a look. So you haven't blocked me, but you'd rather block. So how about I block you instead and absolutely get wrecked? Be true to your word. Do what you say and say what you do. Adibi, follow me. Why not?
At the end of this, I say, follow me, why not? I'd rather block. Oh, but you didn't block. You've commented here. Let's have a look. So you haven't blocked me, but you'd rather block. So how about I block you instead and absolutely get wrecked? Be true to your word. Do what you say and say what you do. Adibi, follow me.
Hello. Good morning. Okay. I don't know. Ace, are you okay? I don't know. When you think about it, in a wee. Okay. Hmm.
I'm not inside of it. One second, mate, right? It's you are under arrest. Yeah. Okay, but I'm literally come out the side, step away. Okay. I'm just going to check this. I've been running, I'm sweating. Well, your wife, no. We'll sort those things out. I'm based at Maidstone.
Oh, yeah?
What was your name, sir? Simon. So I said, essentially, there was an allegation that yesterday there was a male seen here naked that ran away. Obviously, given the location, you understand the concerns, etc. I'm not going to patronise you, I'm certainly speaking for reasons. Obviously, today, the same thing's been alleged. When we've turned up, you matched the description from yesterday.
So what, he's been running around naked?
Yeah, no worries. When I ran, I didn't know your place. I just saw someone. That's right. When I saw you through, you were going to the car and I was go from there.
Was he running around naked?
Yeah, how complicated things, isn't it? I'm not inside of it.
Was he running around naked? What's he doing running around naked? What a fucking dirty cunt. What a dirty cunt. He's in Kent. What a dirty cunt. What a dirty cunt. What a dirty cunt. What's he running around naked? What's he doing? Running around naked like a pixie. Hiding in the bushes. It doesn't get more dodgy than that, does it? Running around naked. Hiding in the bushes. Oh, hey, what's going on here, lads? Hey! Fucking freak. What a skank. Was he going around naked showing himself to ladies? Making out he was doing a wee in the middle of a marsh somewhere. What a fucking dirty cunt. That's what they do. Obviously, I'm not saying all of them, but so many of them are so fucking corrupt. It attracts people. If you want to... Oh, several women reported him. What a fucking loser. What a fucking sight that must have been. Some fucking middle-aged man running about. It attracts so many people. If you want some fucking power, or some big power over people, the easiest way to do it is become a copper. And then you can fuck people's lives over. And if you make if you do something that's really dumb and stupid, the whole institution will support you. Because they don't want bad fucking press. Instead of doing the right thing, they always just try and cover things up. Dirty cunts. Yeah, I'm really exhausted, but I'm going to try. But I'm not too. I mean, I'm not like super exhausted, so I'm going to try and stay up. I went to bed a bit earlier, so that's quite good. Yes, so I'll try and stay up or something. I don't know. Something like that. That's okay. I don't know really. Okay, I guess. What do you think about it? How did you sleep? Did you sleep okay? I'm really tired actually. Did you sleep okay? Let's have a look here. Mm. 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 Let's have a look at my followers. Okay, that's good. I'm still getting followers 2 hours ago, 2 hours ago. Okay, so they're still kind of coming. It's not like it's been totally nerfed. Mm. 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 Sleeping is terrible. You never get good night's sleep. It drains you, yeah, I'm sure. Mm. You constantly wake up. I wake up a lot. I snore a lot. Mm. 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 Yeah, you wake up many times. Yeah, I think I'm going to go get my thing removed today. I need to. I don't know. Hopefully. Mm. I'm terrified of going down to the station. Yeah, I'm absolutely terrified of going down there. I'm so scared of them. I'm so scared of them. I might call up and ask if I can take it out of myself or something. I'm so fucking scared of them. I'm so scared of them. I don't want to see any police anywhere. I used to feel better if there were police about. I used to feel better. Like, it's a bit safer, but I don't think it's safer. Because you don't know what they're like. They just could be a fucking weirdo. Avoid going. I just don't trust them. I just don't trust them. They're so fucking stupid. They're so fucking stupid. Like that geezer going around fucking flashing himself or whatever. I don't understand the fucking buzz of it. The buzz of it. Going around fucking naked and shit. Running around naked, like scaring women and shit. Do you know what I mean? What did you get out of that? Was he hiding in the bushes having a little wank? Tapped. Yeah, I've seen that comment a lot. What does that mean? Just he's fucked in the head. Fucking weirdo. And there's always some fucking. It's never like, I mean, it's very rarely like a really good looking person, is it? The geezer looks alright or whatever, but it's never like fucking. There's never someone who looks like a model. Do you know what I mean? There's always some fucking freak. I don't know what it is. I know that's just a stereotype or whatever. It's probably not necessarily true or whatever. Whenever you see like fucking pedos on the internet, it's like, why do they always look like that? You never seen one that looks like Brad Pitt, have you? Exactly. I don't know what they are. They're fucking freaks. Running around like dickheads. I saw another one in America. It was another copper. He was walking around with a fucking dildo hanging out of his zippers. He had some fucking dildo. And he was walking around with a dildo hanging out of his thing as if it was his knob. And they're just walking around like that. And like scaring women. It's like, I don't know how that develops. Like, I'd like to know the story of how that developed in him. How he developed that kind of like sexual like desire to go around with a fucking dildo hanging out with his knob. Hanging out with fucking flies or whatever you call it, his fucking zipper. Very, very corrupt. What are you doing today? I will feel better, yeah. Thank you. My jaw goes really bad in the morning. When you think about it, I make the best music. Chilling in your garden. Oh, so nice. Oh, so lovely. Is it quite warm? Oh, I need to go get my medication. Fuck. Okay, that's fine. You're thinking isn't it is about it. I find so many pharmacists are like power tripping or something. I don't know. It was just me. No, I don't have to go to Rochdale. I'm going up on City Way. It's not too far. When you think about it. Let me charge my phone. Maybe I'll make a live stream out of it or something. I don't know. I don't know. The one Chatham pharmacy, they're well miserable in there. They're so miserable. They can't even fucking break a smile. They're so fucking slow. Everything takes fucking ages. It's like, why does everything take ages? Can't you just go and get the medicine, put it in the box, and that's it? Put it in the bag. The pharmacist has to check it. Where the fuck is the pharmacist?
Good morning, ladies and gentlemen. I'd like to show you something about how full of it people are and how fickle and. Good morning, ladies and gentlemen. I'd like to show you something about how full of it people are and how fickle and disingenuous they are. Right, watch this bit. Right? At the end of this, I say, not a bit like this. I'd rather block. Oh. But you didn't block. You commented here. Let's have a look. So you haven't blocked me, but you'd rather block. So how about I block you instead and absolutely get wrecked?
I'd rather block. Yeah, but why didn't you block, man? You fucking cunt. I'd rather block. Yeah, but you didn't block, did you? Do you know what I mean? It's like some of the fucking people in the comments and the things like, I'm gonna go now, you're losers. And then like a minute later, they leave another comment and just carry on trying to troll me. So desperate for my attention. I'm exhausted. Just have a coffee. Just have a coffee. Just try and stay up. Try and stay up. I'm so tired. Goes. I need to sleep. I think I can't. I'm too tired. Well, like this. Oh man. Well, yeah, that's life.
Closest star to our sun. Sounds like it should be humanity's best hope.
Right now, the nearest star to our sun is sitting 4.24 light years away. That sounds close. It is not. Between here and there lies a region so empty that if you scooped a cubic centimetre of it, you would find roughly one single atom floating in that space. One atom. The air you are breathing right now contains over 20 billion molecules in that same volume. The space between the stars is not simply nothing. It is a near-perfect vacuum, flooded with cosmic radiation, threaded with invisible magnetic fields, and stretched across distances so vast that our fastest spacecraft would need over 70,000 years to cross just the gap to the nearest neighbouring star. What fills that emptiness is far more terrifying than the emptiness itself. If you enjoy deep dives that change the way you see the universe, take a moment to hit that like button and subscribe. It genuinely helps more than you might think, and keeps these stories coming. Now, settle in and get yourself comfortable. Let's begin. Look up at the night sky on a clear evening, far from the glow of city lights, and you will see something breathtaking. Thousands of stars scattered across the darkness. A dense, glowing band of light cutting across the sky from horizon to horizon. Clusters and smudges of brightness are packed so tightly together that they seem to blur into one another. The sky looks full. It looks crowded. It looks like the universe is bursting with matter, light, and energy crammed into every available corner of the cosmos. This impression is one of the greatest optical illusions in nature. Those stars that appear to sit side by side in the sky are not neighbors. They are separated by distances so extreme that light itself, the fastest thing in the universe, needs years to travel between them. The two stars that form a close visual pair in your favorite constellation might actually be hundreds of light years apart in three-dimensional space, one vastly closer to you and the other unimaginably farther away, with no physical connection between them whatsoever. The night sky flattens the universe into a dome. It compresses trillions of miles of depth into what looks like a painted ceiling. Because of that compression, we walk through our lives believing that space is a place filled with stars. It is not. Space is a place filled with space. The overwhelming majority of the volume of our galaxy contains no stars, no planets, no moons, no asteroids, no comets. Between one star and the next lies a region so devoid of anything recognizable that it challenges the human brain to even imagine it. If you could somehow stand in the middle of the gap between our sun and its nearest stellar neighbor, Proxima Centauri, and look around in every direction, you would see nothing. Not darkness, the way you experience it in a room with the lights off. Darkness on a scale that has no edges, no walls, no floor. A blackness so complete and so vast that it extends for trillions of miles in every direction before the next point of light appears. There is no sound. There is no wind. There is no warmth. And there is almost no matter. Almost. This is where most people stop thinking about it. They file interstellar space under the category of nothing. This is exactly where the real story begins. Because the space between stars is not nothing. It is something. It has structure. It has composition. It has behavior. And understanding what it actually is, what fills those incomprehensible gaps between the stars, reveals a truth about the galaxy that most people never encounter. Scientists call it the interstellar medium. The name sounds clinical, almost boring, like a technical footnote buried in an astrophysics paper. But the interstellar medium is one of the most important environments in the entire Milky Way. It is the material that fills the space between the stars, and it is not empty vacuum. It is an incredibly thin, incredibly vast sea of gas, dust, charged particles, magnetic fields, and high-energy radiation that stretches across the full width of the galaxy. Every cubic centimeter of the space between stars contains some trace of this material. It is everywhere. It is always there. And it plays a role in nearly every major process the galaxy performs, from the birth of new stars to the death of old ones. Here is what the interstellar medium is made of. By mass, approximately 99% of it is gas. The remaining 1% is dust. That ratio alone tells you something important. When scientists talk about what exists between the stars, they are overwhelmingly talking about gas, not thick, breathable gas like the atmosphere you are sitting in right now. Gas so thin, so diffuse, so spread out across such enormous volumes that it makes the best laboratory vacuum on Earth look like a thick soup by comparison. But it is gas nonetheless, and it has a composition that traces directly back to the earliest moments of the universe. Roughly 70% of the interstellar gas by mass is hydrogen. This is the simplest element in existence. One proton, one electron. It is also the most abundant element in the universe, a direct product of the Big Bang itself. Nearly all the hydrogen that exists between the stars today was created in the first few minutes after the universe began, when temperatures were high enough for protons to form, but the universe was expanding too quickly for most of them to fuse into heavier elements. That primordial hydrogen has been drifting through galaxies ever since, collecting in some regions, dispersing in others, occasionally collapsing under gravity to form new stars, and then being recycled back into interstellar space when those stars die. The next most abundant component is helium, making up roughly 28% of the interstellar gas by mass. Helium was also produced during Big Bang nucleosynthesis, in the first minutes of cosmic time. Together, hydrogen and helium account for nearly all the gas in the interstellar medium. Everything else, carbon, oxygen, nitrogen, iron, silicon, every element heavier than helium that exists between the stars adds up to less than 2% of the total mass. A Astronomers sometimes refer to all these heavier elements collectively as metals, which is a source of endless confusion for anyone who studied chemistry, because in this context, oxygen counts as a metal, and so does carbon. The convention is a quirk of astronomical history. The point it conveys is accurate. The space between stars is dominated almost entirely by the two lightest elements in the periodic table. Everything else is a trace. That remaining 1% of the interstellar medium, the dust, is something entirely different. Interstellar dust is not like the dust that accumulates on your bookshelves. It is composed of tiny solid particles, typically less than a micrometer across, made of silicates, carbon compounds, and in some cases, coatings of ice-water ice, carbon monoxide ice, ammonia ice. These grains are incredibly small, roughly comparable to the wavelength of visible light, which is precisely why they are so effective at blocking and scattering starlight. When you see a dark lane running through a photograph of the Milky Way, you are looking at interstellar dust clouds so thick that they absorb the light from billions of stars behind them. The dust does not just passively sit there, it absorbs light at shorter wavelengths, particularly blue light, and re-emits that energy as infrared radiation. This process, called interstellar reddening, makes distant stars appear redder and dimmer than they truly are. For centuries, it fooled astronomers into underestimating the size of the galaxy and the distances to faraway objects, but describing the interstellar medium as simply gas and dust gives a misleading impression of uniformity. The interstellar medium is not a smooth, evenly distributed fog. It is one of the most wildly variable environments in the galaxy. Different regions of the space between stars exist in dramatically different physical states, and scientists have identified several distinct phases that coexist and interact across the galaxy. The first is the cold neutral medium. This is gas that has cooled to temperatures around 50 to 100 Kelvin, which is roughly negative 200 degrees Celsius. At these temperatures, hydrogen exists primarily in its neutral atomic form, meaning the electrons are bound to the protons and the gas carries no net electrical charge. The cold neutral medium tends to concentrate in relatively dense clumps and clouds, and it makes up a significant fraction of the total mass of the interstellar medium, despite occupying only a small fraction of the total volume. These clouds of cold neutral hydrogen are the raw material from which molecular clouds can form. And molecular clouds are the places where new stars are born. Then there is the warm neutral medium. This is hydrogen gas at temperatures around 6,000 to 10,000 Kelvin. It is still electrically neutral, atoms with their electrons intact, but it is far warmer and far more diffuse than the cold phase. The warm neutral medium fills a much larger fraction of the galaxy's volume, spreading out between the denser cold clouds like an ocean between islands. It represents one of the most common states of interstellar gas by volume. Next comes the warm ionized medium. At similar temperatures to the warm neutral medium, around 8,000 Kelvin, this phase differs in one critical respect. The hydrogen is ionized. The electrons have been stripped from the atoms, primarily by ultraviolet radiation from hot, massive stars. The warm ionized medium fills an enormous volume of the galaxy, particularly in regions near stellar nurseries and in the galactic halo above and below the plane of the disk. It was largely invisible to early astronomers because ionized hydrogen at these temperatures does not produce the same strong radio signatures as neutral hydrogen. Its detection required specialized observations of faint emission lines, particularly a spectral line called hydrogen alpha. The warm ionized medium was a relatively late addition to our understanding of interstellar structure, and its full extent is still being mapped. Finally, there is the hot ionized medium. This is the most extreme phase of the interstellar gas, heated to temperatures exceeding 1 million Kelvin by the shock waves from supernova explosions. This phase consists of extremely diffuse, fully ionized plasma. The density is astonishingly low, as little as 1/10,000th of an atom per cubic centimeter, but its temperatures are extraordinary. Supernovae are the primary engines that create this phase. When a massive star reaches the end of its life and detonates, the blast wave expands outward at thousands of kilometers per second, sweeping up, heating, and ionizing the surrounding interstellar gas. These expanding bubbles of superheated plasma can persist for millions of years and can grow to hundreds of light years in diameter. The hot ionized medium is thought to fill a large fraction of the galactic volume, perhaps as much as 50% in some models, creating a pervasive network of overlapping bubbles and tunnels of million-degree gas threading through the cooler phases. These 4 phases do not exist in isolation. They are in constant interaction. Cold clouds are embedded within warmer gas. Supernova shock waves crash into dense molecular regions, sometimes compressing them enough to trigger gravitational collapse and new star formation, and sometimes blasting them apart and dispersing their material into the surrounding volume. The interstellar medium is a dynamic, turbulent, constantly churning system. Material cycles between phases over millions of years. Gas cools, condenses, forms stars, gets heated and dispersed by those stars, cools again, and the cycle continues. The galaxy is not a static painting. It is a living system, and the interstellar medium is the circulatory system that drives it. Our own solar system sits inside one of these dynamic features. It is called the local bubble, and it is a region of the hot, ionized medium that extends roughly 1,000 light years across. The local bubble was likely carved out by a series of supernova explosions that occurred between 10 and 20 million years ago. Those explosions swept away the denser interstellar gas that had previously occurred in this region, leaving behind a cavity of extremely low density, high temperature plasma. We live inside this cavity. When you look at the night sky, you are peering out through the walls of a bubble blown by dead stars. Immediately surrounding the solar system within this larger bubble is a smaller structure called the local interstellar cloud, sometimes referred to as the local fluff. This is a relatively warm, partially ionized cloud of gas with a density of roughly 0.3 atoms per cubic centimeter, slightly denser than the surrounding bubble, but still extraordinarily rarefied by any terrestrial standard. The Sun is currently passing through this cloud, and it is the interstellar material that Voyager 1 and Voyager 2 first encountered when they crossed beyond the heliosphere, the bubble of solar wind that surrounds our solar system. The local interstellar cloud has a temperature of approximately 6,000 to 7,000 Kelvin, and is flowing through our neighborhood of the galaxy at roughly 26 kilometers per second. In a few thousand years, the solar system will leave this cloud and enter a different region of interstellar space, possibly one that is denser or more tenuous. The environment between the stars is not static, even in our own tiny corner of the galaxy. There is one more component of the interstellar medium that most people never hear about, but that pervades the entire space between stars: magnetic fields. The galaxy is threaded with magnetic fields that extend across thousands of light years, typically measuring a few microgauss in strength. A microgauss is an almost inconceivably weak unit of magnetic force. The refrigerator magnet on your kitchen door is roughly 10 million times stronger than the interstellar magnetic field. But what the interstellar field lacks in intensity, it compensates for in scale. These magnetic fields stretch across the entire galactic disk and into the halo, influencing the motion of charged particles, shaping the structure of the interstellar gas, and playing a critical role in how cosmic rays propagate through the galaxy. Without interstellar magnetic fields, the behavior of the medium would be fundamentally different, and the galaxy would look nothing like it does today. Cosmic rays themselves are another omnipresent component of the interstellar environment. These are not rays in the traditional sense. They are particles, primarily protons, but also heavier atomic nuclei, that have been accelerated to extraordinary energies by violent astrophysical events, particularly supernova remnant shock waves. Some cosmic ray particles travel at 99.9% of the speed of light. They carry individual particle energies that can exceed anything produced by the most powerful human-built particle accelerators on Earth. These particles zip through the interstellar medium constantly, deflected and scattered by the magnetic fields, interacting with the gas and dust, penetrating deep into any structure they encounter. They are a permanent feature of the space between stars, an invisible rain of high-energy particles that fills the galaxy from edge to edge. So let us take stock of what actually exists in the space between stars. It is not nothing. It is a sea of gas, primarily hydrogen and helium, arranged in multiple coexisting phases at vastly different temperatures and densities. It contains tiny but astrophysically important grains of dust that absorb and scatter light, reshaping what we can see. It is permeated by magnetic fields that extend across thousands of light years and influence the motion of charged particles. It is saturated with cosmic rays, high-energy particles that travel at nearly the speed of light and carry enormous individual energies. And it is dynamic, shaped by the explosions of dying stars, the radiation of living ones, and the gravitational interactions of the galaxy itself. This is the environment that lies between every star you have ever seen. Not vacuum, not void, not nothing. A structured, complex, physically real medium that scientists have spent decades studying and still do not fully understand. Every phase transition, every interaction between shock waves and cold clouds, every magnetic field line threading through the galactic disk represents a piece of an ongoing puzzle that connects the largest scales of galactic evolution to the smallest scales of atomic and molecular physics. And here is the crucial detail that most people miss entirely. The interstellar medium is not just a backdrop, it is a participant. Without it, no new stars could form. Stars are born when regions of the interstellar medium, specifically the cold, dense molecular clouds, collapse under their own gravity. If the interstellar medium did not exist, star formation would have ended billions of years ago when the first generation of stars consumed the available material. The galaxy would be a graveyard of dead stellar remnants with no new light to replace them. Instead, the interstellar medium acts as a reservoir. Stars form from it, live their lives, and then return their material back into it through stellar winds, planetary nebulae, and supernova explosions, often enriched with heavier elements forged in their cores. The next generation of stars forms from this enriched material, incorporating those heavier elements into planets, moons, and ultimately the chemistry of life. Every atom of carbon in your body, every atom of oxygen you breathe, was manufactured inside a star, ejected into the interstellar medium, drifted through the space between stars for millions of years, and then was swept up into the collapsing cloud that formed our solar system. The interstellar medium is the bridge between stellar generations. It is the mechanism by which the galaxy renews itself. Understanding this changes everything about how we should think about the space between stars. It is not an absence, it is a presence. A thin, vast, structured, and essential presence that defines the character of the galaxy. But there is a trap in this understanding, and it is easy to fall into. Learning that the interstellar medium is not empty can create the impression that it is therefore substantial, that it is filled with useful material, that there is something out there to work with. There is not, because for all its scientific importance, for all its role in galactic evolution, the interstellar medium is staggeringly, almost incomprehensibly thin. The fact that it contains something does not mean it contains enough of anything to matter on any human scale. The gas densities we have been discussing, 1 atom per cubic centimetre in typical regions, a fraction of an atom per cubic centimetre in the hot phase, are so low that they represent conditions more extreme than any vacuum humans have ever created in a laboratory. The interstellar medium exists. It is real. It is measurable. And it is, for all practical purposes, as close to nothing as the universe can get while still technically being something. This tension between the interstellar medium being scientifically significant and practically negligible is the heart of the story. And it is a tension that only sharpens as we move deeper into the true scale of what lies between the stars. emptiness of the interstellar medium is not just an abstract physical fact, it is a barrier. The distances across which that emptiness stretches are far larger and far more terrifying than most people have ever been told. Let us begin with a single cubic centimetre. Hold your thumb and forefinger about a centimetre apart. That tiny gap, roughly the width of a pencil eraser, defines a volume of space so small you could fit hundreds of them inside a teaspoon. Now consider what that volume contains, depending on where in the universe it happens to be. At sea level on Earth, that cubic centimetre of air holds approximately 2.5 times 10 to the 19th power molecules. That is 25 quintillion. Written out, it is a 2 followed by a 5 followed by 18 zeros. Every cubic centimetre of every breath you take contains that many molecules of nitrogen, oxygen, argon, and trace gases, all bouncing off one another billions of times per second, creating the pressure and temperature you feel as the ordinary atmosphere of a pleasant afternoon. Now move that cubic centimetre into the best vacuum chamber ever built by human engineers. The most advanced ultra-high vacuum systems in research laboratories can pump a chamber down to a few thousand molecules per cubic centimetre. That is a reduction by a factor of more than 10 quadrillion compared to sea level air. At those densities, individual molecules travel for kilometres between collisions. These are the conditions required for manufacturing semiconductors, studying surface physics, simulating aspects of the space environment for satellite testing. They represent the most extreme emptiness that human technology can reliably produce. Now move that cubic centimetre into the space between stars. In a typical region of the interstellar medium, that same cubic centimetre contains approximately one atom. One. Not 100. Not 1,000. One single hydrogen atom drifting in a volume that, on Earth, would hold 25 quintillion molecules. In the hot, ionized phase of the interstellar medium, the number drops further. It can fall to one atom per every 10,000 cubic centimeters. Imagine a volume the size of a large moving box, the kind you would use to pack dishes when changing apartments. Place inside it a single hydrogen atom. That is the density of the hottest, most diffuse phase of the gas that fills the space between the stars. These numbers are worth pausing over because they destroy a common misconception. When people learn that interstellar space is not truly empty, and that it contains gas and dust, there is a natural tendency to picture something like a very thin fog, a haze, a faint mist that you might be able to detect if you squinted hard enough. That is so advanced it barely qualifies as the same category of physical experience. The interstellar medium is not a thin fog. It is a vacuum so extreme that it makes the most advanced vacuum chambers on Earth look positively dense. The fact that it contains anything at all is detectable only because the volumes involved are so enormous that even one atom per cubic centimetre, accumulated across trillions upon trillions of cubic centimetres, adds up to a measurable quantity of matter. On any human scale, on any scale that your body or your senses or your engineering could interact with, the interstellar medium is indistinguishable from perfect emptiness. Here is another way to grasp this. Take all the interstellar gas contained within 1 cubic light year of space. A cubic light year is an enormous volume, roughly 9.5 trillion kilometers on each side. That is a box so large that light itself would need a year to cross it. Now, take every atom of gas inside that volume, compress it down into a solid sphere of the density of water. The resulting sphere would be remarkably small. Despite starting with a volume that dwarfs the entire solar system, you would end up with a ball roughly the size of a single planet. All the matter in a cubic light year of interstellar space, squeezed together, would fit inside something no larger than Jupiter. One planet's worth of material spread across a volume that light takes a year to cross. The rest of that cubic light year, the overwhelming, crushing majority of it, is void. This is the reality that the night sky hides from you. The galaxy is not made of stars. The galaxy is made of emptiness, with stars sprinkled through it at intervals so vast that the emptiness is the dominant feature by every conceivable measure. Stars are exceptions. The interstellar void is the rule. And the void between any two neighboring stars is not a small gap to be hopped across. It is an abyss. Consider the distance to the nearest star system. Proxima Centauri, the closest known star to our Sun, sits approximately 4.24 light-years away. That translates to roughly 40 trillion kilometers, 40 followed by 12 zeros. This is the shortest stellar distance in our entire neighborhood of the galaxy, the absolute minimum gap between our Sun and any other star. And yet it is so large that human-built machines, traveling at the fastest speeds we have ever achieved, would require tens of thousands of years to cross it. To develop some intuition for what 40 trillion kilometers actually means, consider the following. The Earth orbits the Sun at a distance of about 150 million kilometers, a unit astronomers call 1 astronomical unit. Proxima Centauri is approximately 268,000 astronomical units away. If you could somehow drive a car at highway speed, roughly 100 kilometers per hour, without ever stopping for fuel or rest, you would reach the Sun in about 170 years. To reach Proxima Centauri at that same speed, you would need more than 45 million years. The dinosaurs would still be walking the Earth when you started the trip. They would have gone extinct, mammals would have risen, primates would have evolved, human civilization would have been born and possibly ended, all before you arrived. And this is the closest star. The average distance between neighboring stars in our region of the galaxy is larger, typically around 5 light-years, but varying considerably depending on location within the galactic disk. Toward the center of the Milky Way, stars pack more closely together, though closely still means trillions of kilometers. In the outer reaches of the galactic disk and in the halo above and below the plane, stars are spaced even farther apart. In every case, the gaps between them are filled with the same astonishingly tenuous interstellar medium we have been describing. Trillions of kilometers of near vacuum, atom by sparse atom, stretching between each island of light. This is not an academic observation. It has been directly confirmed by the only human-made objects that have ever reached interstellar space. Voyager 1, launched from Earth on September 5th, 1977. Its primary mission was to study Jupiter and Saturn, which it did with spectacular success. But after those encounters, it kept going. Powered by the radioactive decay of plutonium in its 3 radioisotope thermoelectric generators, Voyager 1 continued outward from the Sun at roughly 17 kilometers per second, or about 61,000 kilometers per hour. Year after year, decade after decade, it flew. It passed the orbit of Pluto. It entered the outermost regions of the heliosphere, the bubble of charged particles and magnetic fields that the Sun inflates around itself. And on August 25th, 2012, something changed. Voyager 1's instruments detected a dramatic shift in its environment. The density of charged particles around the spacecraft increased sharply. The intensity of galactic cosmic rays, high-energy particles originating from outside the solar system, jumped upward. The plasma environment transformed from one dominated by the outward-flowing solar wind to one dominated by the denser, colder plasma of the interstellar medium. After 35 years of flight and a distance of over 121 astronomical units from the Sun, Voyager 1 had crossed the heliopause, the boundary where the Sun's influence gives way to the interstellar environment, and entered the space between the stars. But this description, crossed the heliopause and entered interstellar space, makes the transition sound far cleaner than it actually was. Voyager 1 did not pass through a single doorway from the solar system into the void. It crossed a series of boundaries, each one marking a distinct physical transition, and the crossing took years, not moments. Understanding these layers matters, because they reveal just how structured the border between solar space and interstellar space truly is, and how much protection we lose when we leave. The first boundary Voyager 1 encountered was the termination shock. The sun continuously blows a wind of charged particles outward in every direction, at speeds ranging from 400 to 800 kilometers per second. This solar wind inflates the heliosphere, pushing against the pressure of the interstellar medium, but the interstellar medium pushes back. At a certain distance from the sun, the outward pressure of the solar wind can no longer sustain its supersonic speed against the inward pressure of the interstellar gas. The wind abruptly decelerates from supersonic to subsonic velocities. This deceleration creates a shock wave, a standing wave in the plasma that marks the beginning of the heliosphere's outer structure. Voyager 1 crossed the termination shock in December 2004 at a distance of roughly 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007 at approximately 84 astronomical units, a difference that revealed the heliosphere is not a perfect sphere, but an asymmetric structure compressed on one side of the interstellar medium's evolution relative to the Sun. Beyond the termination shock lies the heliosheath. This is a thick, turbulent region where the decelerated solar wind piles up against the surrounding interstellar medium, creating a zone of compressed, heated, chaotic plasma. The heliosheath is not calm. It is a roiling boundary layer where solar and interstellar materials interact, mix, and struggle for dominance. Magnetic fields tangle. Particle populations from both sides intermingle. Voyager 1 spent 8 years traversing the heliosheath before finally reaching the heliopause itself in 2012. 8 years of continuous travel at 17 kilometers per second, covering roughly 4 billion kilometers, just to cross the boundary layer between solar space and interstellar space. That single transition zone, a region most people have never heard of, is comparable to the distance from the Sun to Neptune. The heliopause is the outermost boundary, the surface where the pressure of the solar wind finally balances the pressure of the interstellar medium, and the Sun's direct influence effectively ends. This is what Voyager 1 crossed in August 2012, Voyager 2 crossed in November 2018. Beyond it, the interstellar medium begins in earnest. But even here, the transition was not perfectly sharp. Both Voyagers detected a complex layered structure of the heliopause, with magnetic field direction shifting, particle populations fluctuating, and plasma densities changing over distances of millions of kilometers. The edge of the heliosphere is not a wall. It is a membrane, thick and textured, and crossing it is a process that unfolds over months of spacecraft travel. This layered complexity matters for a simple reason. Every layer Voyager crossed on its way out, the termination shock, the heliosheath, the heliopause, represents a component of a structure that the Sun has built around itself using nothing more than the outward pressure of its own wind. That structure took Voyager 8 years to traverse. It is not a line on a map. It is a physically thick, turbulent, multi-layered boundary between two fundamentally different environments. And once a traveler passes through all of it and emerges on the other side, there is no equivalent structure ahead for light years. The medium that awaits on the far side has been waiting for billions of years. There is one more feature of the space between the heliosphere and the nearest star that deserves attention, because it is often misunderstood as offering something it does not. The Oort cloud is a hypothesized shell of icy bodies, comets, and frozen debris left over from the formation of the solar system that is thought to extend from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun, or roughly 1.5 light years. If this shell exists as current models predict, it means the solar system's gravitational influence extends far beyond the heliosphere, reaching almost halfway to Proxima Centauri in terms of the Sun's ability to loosely hold objects in distant, fragile orbits. At first glance, this might seem encouraging. Perhaps the Oort cloud offers waypoints, resource depots, or at least landmarks along the journey to the nearest star. It does not. The Oort cloud, if it exists, is estimated to contain several Earth masses of material spread across a shell trillions of kilometers thick. The average distance between individual Oort cloud objects is estimated to be tens of millions of kilometers. You could fly through the Oort cloud for centuries and never come within visual range of a single body. The objects themselves are small, cold and dark, frozen chunks of ice and rock drifting in orbits so distant that the sun appears as little more than a bright star. They offer no fuel, no shelter, and no navigational utility. They are ghosts at the edge of the sun's gravitational reach, so sparse and so scattered that they reinforce the emptiness rather than relieving it. The Oort cloud is not a resource. It is a reminder that even the solar system's most extended structure is pitifully thin compared to the gulf that separates us from the stars. Beyond the outer edge of the Oort cloud, even the sun's tenuous gravitational claim fades. From there to the corresponding outer reaches of Proxima Centauri's own gravitational domain, there is truly nothing. No objects are in orbit around any star, no remnants of any formation process, just the interstellar medium, atom by sparse atom, stretching across the remaining light years of the journey in perfect, featureless desolation. NASA confirmed this crossing in September 2013, based on detailed analysis of plasma oscillation data that indicated the electron density around Voyager 1 had increased by roughly a factor of 80 compared to conditions inside the heliosphere. The spacecraft had not just left the solar system's planetary region, it had left the solar system's entire protective envelope and entered a fundamentally different medium. Voyager 2 followed. Launched 16 days before its twin, but on a slower trajectory due to its detour past Uranus and Neptune, Voyager 2 crossed the heliopause on November 5th, 2018. At a distance of approximately 119 astronomical units from the Sun, its crossing confirmed and expanded on Voyager 1's findings. Voyager 2 carried a working plasma science instrument that Voyager 1's had lost decades earlier, allowing it to make direct measurements of the interstellar plasma that its twin could not. The data showed that the interstellar plasma was colder and significantly denser than the plasma inside the heliosphere, exactly as models had predicted. Both spacecraft observed that the interstellar magnetic field was oriented in a direction parallel to the heliosphere boundary, a finding that surprised many scientists who had expected a sharper directional change. Since those crossings, the Voyagers have continued to send back data from interstellar space, and the findings have been consistently fascinating. In 2020, Voyager 1's magnetometer registered an abrupt increase in the intensity of the local interstellar magnetic field, accompanied by a rise in plasma density. Scientists initially interpreted these as pressure waves generated when bursts of solar activity slammed into the heliopause and sent reverberations rippling outward into the interstellar medium. But the anomaly did not fade. It persisted, leading some researchers to speculate that Voyager 1 might have entered a distinct region of interstellar space, perhaps a localized cloud of ancient plasma or a pressure structure not previously predicted by models. The investigation was interrupted in November 2023 when a hardware failure in Voyager 1's flight data subsystem caused the spacecraft to stop transmitting usable data. After months of painstaking remote troubleshooting across a signal delay of more than 22 hours each way, engineers traced the problem to a corrupted memory chip, likely damaged by a cosmic ray strike. By mid-2024, science data from multiple instruments had been restored, and the investigation of the interstellar anomaly resumed. These are extraordinary achievements of engineering and perseverance, and they reveal something profoundly humbling. As of early 2025, Voyager 1 is approximately 165 astronomical units from the Sun. That is roughly 24.7 billion kilometers. It is the most distant human-made object in existence, and it has been traveling for nearly 48 years. At its current velocity of 17 kilometers per second, it covers roughly 535 million kilometers per year. That sounds fast. It is fast by any standard of human experience. You could circle the Earth more than 13,000 times in a year at that speed. But Proxima Centauri is 4.24 light years away. That is approximately 40 trillion kilometers. Voyager 1, after nearly half a century of continuous flight, has travelled less than 0.1% of that distance. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would need over 70,000 years to arrive. 70,000 years. That is roughly 10 times longer than all of recorded human civilization. When Voyager 1 hypothetically arrived, the species that launched it might no longer exist. Voyager 2, slightly slower and slightly closer to the Sun, tells the same story. Both spacecraft are moving through interstellar space at speeds that dwarf anything humans experience in daily life, and both are barely crawling relative to the distances they would need to cover to reach even the nearest neighbouring star. The interstellar medium they are now sampling, the thin plasma and the elevated cosmic ray flux, the faint magnetic field, extends ahead of them for light years in every direction. They will spend thousands of centuries drifting through this medium before they come anywhere close to another stellar system. This is the first visceral lesson about the space between stars. It is not just empty, it is vast on a scale that makes human technology irrelevant. Our fastest machines, products of decades of engineering and billions of dollars of investment, enter interstellar space and are immediately rendered negligible by the sheer distance to the next destination. The interstellar medium does not need to block you or destroy you or push you back. It simply needs to exist at the scale it exists at. The emptiness itself is the obstacle. The distance itself is the wall. The distance to Proxima Centauri is, cosmically speaking, trivially small. It represents the very shortest interstellar gap in our region of the galaxy. Most stars in the Milky Way are separated by far greater distances. Travel to a star 10 light years away and you have multiplied the problem by more than 2. Travel to a star 100 light years away, still a negligible distance within a galaxy that spans 100,000 light years, and you have multiplied it by more than 20. The interstellar medium stretches across all of it, the same sparse atoms, the same near vacuum, the same cosmic silence. There is nothing between here and there that changes the equation. Just the medium, thin and featureless and unyielding, for trillions upon trillions of kilometers. Let us put the Voyager distance into one more frame to make the point inescapable. Imagine shrinking the solar system so that the Sun is the size of a grain of sand, roughly 1 millimeter across. At this scale, the Earth would be a speck of dust orbiting about 10 centimeters away, roughly the width of your hand. Jupiter would be another tiny grain about half a meter out. Neptune, the outermost major planet, would sit about 3 meters from the Sun's grain. The entire solar system, from the Sun to Neptune, would fit comfortably inside a small room. At this same scale, Proxima Centauri would be another grain of sand sitting approximately 29 kilometers away. Nearly 30 kilometers of empty space between 2 grains of sand in a small room. Walk out of the room, through the hallway, out of the building, through the city, past the suburbs, and into the countryside for almost 30 kilometers before you reach the next grain. That is the distance between stars, scaled down to something you can hold in your hand. And everything between those 2 grains, every millimeter of those 29 kilometers, is the interstellar medium. Nearly empty, nearly featureless, just space stretching on and on and on. There is a reason this scale breaks human intuition. Our brains evolved to process distances measured in meters and kilometers. We developed spatial reasoning to navigate forests, track animals across savannas, and find our way back to shelter. Our cognitive architecture was built for a world where the farthest relevant distance was the horizon, maybe a few tens of kilometers on a clear day. Interstellar distances exceed our innate processing capacity by factors of trillions. We can write the numbers, we can perform the calculations, but we cannot feel them. The emotional reality of 40 trillion kilometers does not register in the same way that the emotional reality of a long walk home does. So, we default to abstractions. We say 4 light years as though it were a comprehensible distance, when in truth it is a number so large it might as well be a magic spell. The words carry no experiential weight. This gap between what we can calculate and what we can feel is one of the reasons the space between stars is so routinely underestimated. underestimated. Science fiction has trained us to imagine interstellar travel as a matter of better engines, faster ships, and more advanced technology. The stars are out there, and all we need is the right vehicle to reach them. What this framing ignores is the physical reality of what out there actually means. It means years of travel at the speed of light itself. It means tens of thousands of years at the fastest speeds any human technology has ever achieved. It means crossing a medium that contains, for all practical purposes, nothing useful, no fuel, no resources, no shelter, no landmarks. It means committing to a journey through a void so absolute that even the concept of progress becomes difficult to define. When the scenery does not change for millennia, when the nearest star is still light years away, when your instruments show the same sparse atoms and the same faint magnetic hum they showed a century ago, what does it mean to say you are getting closer? The density of the interstellar medium also means that there is effectively no way to harvest resources during such a journey. The concept of a Bussard ramjet, a hypothetical spacecraft that scoops up interstellar hydrogen and uses it as fusion fuel, has appeared in physics discussions and science fiction for decades. But the math is punishing. At 1 atom per cubic centimetre, a scoop hundreds of kilometres wide would collect only grams of hydrogen per second, even at high velocity. The drag created by the scoop interacting with the medium would likely exceed any thrust generated by fusing the collected fuel. The interstellar medium is simply too thin to serve as a resource. It exists, but it exists at densities so far below utility that its presence is almost taunting. There is something out there, just not nearly enough of anything. The Voyager spacecraft themselves are aging testaments to the harshness of this environment. Their radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 into electricity, lose approximately 4 watts of power each year as the plutonium decays. By 2025, the power situation has grown critical enough that NASA has begun shutting down science instruments one by one to keep the remaining ones operational. In February 2025, Voyager 1's cosmic ray subsystem was powered off. In March 2025, Voyager 2's low-energy charge particle detector followed. These decisions extend the mission's life by a few years at most. Each spacecraft now operates with only 3 functioning science instruments. Engineers estimate that both Voyagers will exhaust their usable power sometime in the late 2020s or early 2030s, after which they will fall silent, drifting through interstellar space as inert artifacts, still carrying their golden records, but no longer able to tell us anything about the medium through which they travel. When the Voyagers go quiet, humanity will have no active presence in interstellar space. No instrument measuring the density of the interstellar plasma, no magnetometer tracking the faint interstellar field, no cosmic ray detector is counting the high-energy particles that saturate the medium. We will be left with the data they collected and the knowledge that, just beyond the edge of our solar bubble, the vast and almost incomprehensibly empty environment stretches outward in every direction towards stars we cannot reach. This is the scale of what lies between the stars. Not a gap, not a void to be leaped across with sufficient ambition. A medium so thin it barely registers as matter, and so vast it swallows the fastest objects humanity has ever built without the slightest notice. The interstellar medium does not care about our spacecraft, it does not resist them, it simply extends, kilometre after kilometre, light year after light year, unchanging and indifferent, while our machines crawl through it at speeds the universe considers negligible. And yet the scale is only part of the story, because for all its staggering emptiness, for all its featureless expanse, the interstellar medium is not benign. The thin gas and the sparse dust and the faint magnetic fields are not simply obstacles of distance. They carry with them something more immediate and more dangerous than mere emptiness. The space between stars is flooded with energy. High-energy particles rain through it at nearly the speed of light, every second, from every direction. Radiation permeates it at levels that would likely filter unprotected biological tissue over any sustained exposure. The medium that seems like nothing is, in fact, actively hostile. And that hostility only grows more severe the farther you travel from the one thing that has been protecting you all along. Every second of every day, something invisible passes through your body. Not one thing, hundreds of things. Subatomic particles traveling at nearly the speed of light, remnants of catastrophic stellar explosions that occurred thousands or even millions of years ago, cross through the walls of your house, through the roof above you, through the ground beneath you, and through every cell in your body without stopping. You do not feel them, you cannot see them. They leave no trace that your senses can detect. And yet they are there, a constant rain of high-energy radiation falling from space. On the surface of the Earth, this is a minor footnote in your daily life. The planet's magnetic field deflects the majority of incoming charged particles, sweeping them into spiraling paths that funnel toward the poles rather than allowing them to strike the surface directly. The atmosphere above you, a column of gas hundreds of kilometers deep and pressing down with the weight of an ocean, absorbs most of whatever makes it past the magnetic shield. By the time cosmic radiation reaches sea level, it has been filtered, scattered, and attenuated to levels so low that the average person receives roughly 0.3 millisieverts per year from cosmic sources, a small fraction of the total background radiation exposure from all natural and medical causes combined. You live at the bottom of a double shield, magnetic and atmospheric, and that shield is so effective that most people go their entire lives without ever learning it exists. In interstellar space, both shields are gone. The heliosphere, that great bubble of solar wind plasma that the sun inflates around the entire solar system, acts as a third layer of protection that most people never think about. The solar wind, a constant outflow of charged particles streaming from the sun at 400 to 800 kilometers per second, pushes outward against the surrounding interstellar medium, creating a cavity roughly 120 astronomical units in radius. Within this cavity, the sun's magnetic field extends outward in a vast spiral. The pressure of the solar wind keeps a portion of the incoming galactic cosmic rays at bay. The heliosphere does not block all cosmic rays. Higher energy particles punch through regardless, but it significantly reduces the total flux of galactic cosmic radiation reaching the inner solar system. Measurements from neutron monitors on Earth show that cosmic ray intensity on the surface varies with the 11-year solar activity cycle. During solar maximum, when the solar wind is strongest and the heliosphere is most inflated, cosmic ray flux drops. During solar minimum, when the wind weakens, cosmic rays penetrate. The heliosphere is a dynamic shield, constantly breathing in and out, and everything inside it benefits from its presence. We already know what happens when you leave that shield behind. Voyager's instruments confirmed it directly. The galactic cosmic ray flux in the local interstellar medium is significantly higher than the flux inside the heliosphere. This was expected on theoretical grounds, but the Voyager crossings turned prediction into measured fact. Outside the bubble, the full intensity of galactic cosmic radiation arrives from every direction, unfiltered and undiminished. And the character of that radiation is what makes interstellar space so much more dangerous than the relatively sheltered environment we inhabit. This matters profoundly for any discussion of interstellar travel or survival beyond the heliosphere. Galactic cosmic rays are not ordinary radiation. They are not like the X-rays you receive during the decades, the ultraviolet light that causes sunburn. They are atomic nuclei, primarily protons, but also helium nuclei and heavier ions, up to and including iron, that have been stripped of their electrons and accelerated to tremendous energies by astrophysical processes. The primary accelerators are supernova remnant shock waves. When a massive star explodes, the blast wave expands into the surrounding interstellar medium at thousands of kilometers per second. Charged particles caught in this shock wave can bounce back and forth across the shock front, gaining energy with each crossing, until they reach velocities approaching the speed of light. Some galactic cosmic ray particles carry energies exceeding 10 to the 18th electron volts, and the most extreme particles ever detected reach 10 to the 20th. For a single subatomic particle, this highest energy is staggering, comparable to the kinetic energy of a fast-moving baseball concentrated into a volume smaller than an atomic nucleus. When these particles strike matter, the results are destructive at the molecular level. A single high-energy cosmic ray nucleus passing through biological tissue ionizes atoms along its track, breaking chemical bonds, damaging DNA, creating cascades of secondary particles that spread the damage over a wider area. The heavier the nucleus, the greater the ionization damage. Iron nuclei, though they make up only a tiny fraction of the total cosmic ray flux, are particularly devastating because their high charge means they strip electrons from atoms far more aggressively than protons do. NASA classifies these heavy ions as HZE particles, standing for high atomic number and high energy, and considers them one of the most serious radiation hazards for deep space missions. The biological effects of sustained cosmic ray exposure are still not fully understood, in part because no human being has ever been exposed to the full interstellar cosmic ray environment for an extended period. Astronauts aboard the International Space Station receive elevated radiation doses compared to the surface, roughly 72 millisieverts over a 6-month mission, but they still orbit within the protective envelope of Earth's magnetic field. The station's altitude keeps it below the most intense regions of the Van Allen radiation belts, and its orbit never takes it beyond the magnetosphere. Even on a hypothetical mission to Mars, which would take astronauts outside the magnetosphere for roughly 8 to 9 months each way, the total cosmic ray dose is estimated at several hundred millisieverts, enough to meaningfully increase lifetime cancer risk, but probably survivable with careful mission planning. Interstellar space is a different category of problem entirely. Outside the heliosphere, with no magnetic field and no solar wind to attenuate the cosmic ray flux, the radiation dose rate increases substantially. Estimates based on Voyager data and cosmic ray transport models suggest that an unshielded human in interstellar space would receive a radiation dose on the order of several hundred millisieverts per year, possibly higher depending on the local cosmic ray environment. Over a journey lasting decades or centuries, the cumulative dose would be enormous, far exceeding the levels at which cancer, central nervous system damage, cardiovascular disease, and other radiation-induced pathologies become near certainties. And here is where the problem compounds in a way that defies easy engineering solutions. The instinctive response to radiation is to add shielding. Build thicker walls, surround the crew with dense material, block the particles before they reach living tissue. For ordinary radiation, this works. Lead stops gamma rays. A few centimeters of aluminum stop most solar energetic particles, but galactic cosmic rays are not ordinary radiation. The highest energy cosmic ray particles can penetrate meters of solid material. Worse, when a high energy cosmic ray nucleus strikes a dense shield, it does not simply stop. It undergoes a nuclear reaction with the atoms in the shield material, producing a shower of secondary particles, neutrons, protons, pions, and fragments of nuclei that spray inward toward the very crew the shield was meant to protect. These secondary particles can be more biologically damaging than the original cosmic ray. Studies have shown that thin aluminum shielding, the kind used on the International Space Station, can actually increase the effective radiation dose in interplanetary space compared to having no shielding at all, because the secondary particle production outweighs the primary particle attenuation. Thicker shielding helps, but only up to a point, and the mass required for truly effective cosmic ray shielding is enormous. Materials with low atomic numbers, such as polyethylene or water, perform better than metals because they produce fewer secondary particles, but even these materials would need to be applied in layers many tens of centimeters thick to make a meaningful difference, adding thousands of kilograms to any spacecraft design. It is worth dwelling on this secondary radiation problem because it is one of the most counterintuitive and disturbing aspects of the cosmic ray hazard, and it runs directly against every intuition we have about how shielding should work. On Earth, radiation shielding is straightforward in principle. You put a dense material between yourself and the source of radiation, and the radiation gets absorbed. Lead aprons protect dental patients from X-rays. Concrete walls surround nuclear reactors. Water pools cover spent fuel rods. In each case, the shielding material intercepts the incoming radiation and converts its energy into heat, which dissipates harmlessly. The radiation stops. The person behind the shield is safe. This principle is so reliable, so deeply embedded in our engineering practice, that it feels like a universal law. More shielding equals more protection. In interstellar space, for the highest energy galactic cosmic rays, this principle breaks down. When a galactic cosmic ray nucleus, say an iron traveling at 90% of the speed of light, strikes an aluminum hull plate, it does not gently slow down and stop the way an X-ray photon is absorbed by a lead apron. Instead, the incoming nucleus collides with an aluminum nucleus in the hull, and both nuclei shatter. The iron nucleus breaks apart into a spray of lighter fragments, protons, neutrons, helium nuclei, and pieces of heavier elements. The aluminum nucleus does the same. The collision also generates a cascade of secondary particles that did not exist before the impact. Pions, which quickly decay into muons and gamma rays. Neutrons, which are electrically neutral, therefore completely unaffected by magnetic shielding. And a general shower of lower energy but still biologically damaging particles that fans out behind the impact point, penetrates deeper into the spacecraft. This is called a nuclear spallation cascade, and it transforms a single incoming high-energy particle into dozens or hundreds of secondary particles, many of which are more effective at damaging biological tissue than the original cosmic ray would have been. Neutrons are particularly insidious because they carry no electrical charge, which means they cannot be deflected by magnetic fields, and they pass easily through materials that would stop charged particles. When a neutron finally does interact with an atom in human tissue, the result is typically a heavy recoil event that deposits a large amount of energy in a very small volume, exactly the kind of interaction that causes the worst DNA damage. The net effect is paradoxical. A thin shield, say a few centimeters of aluminum, generates a significant number of secondary particles from every cosmic ray it intercepts, while failing to stop the secondaries it creates. The crew behind such a shield can receive a higher total radiation dose than they would with no shield at all, because the spallation products are more numerous and in some cases more harmful than the original cosmic ray flux. A thicker shield reduces this problem, because the additional material absorbs some of the secondary particles before they reach the interior, but the improvement is slow and expensive in terms of mass. To achieve a meaningful reduction in dose from a pure aluminum shield, you would need thickness on the order of a meter or more, which translates to tens of thousands of kilograms of shielding mass for even a modest crew habitat. Lower atomic number materials, particularly hydrogen-rich compounds like polyethylene and water, perform better because lighter target nuclei produce fewer and less energetic spallation products. A proton hitting a hydrogen nucleus can only produce a recoil proton, not a shower of heavy fragments. This is why water has been proposed as a shielding material for interstellar habitats, serving the dual purpose of radiation protection and life support resource. But even water shielding needs to be applied in layers of 30 centimeters or more to make a significant difference against the full galactic cosmic ray spectrum. And the mass penalty remains severe for any vehicle that must also accelerate to interstellar velocities. The secondary radiation problem means there is no simple engineering fix for cosmic ray exposure in interstellar space. You cannot just build a thicker wall. The wall fights back. For a short duration mission to Mars, lasting perhaps 2 to 3 years round trip, the radiation problem is serious but potentially manageable through a combination of modest shielding, mission timing to coincide with solar maximum, when galactic cosmic ray flux is lower, and acceptance of some elevated long-term health risk. For an interstellar mission lasting decades, centuries or millennia, the problem is qualitatively different. The cumulative exposure grows without limit. There is no solar maximum to time the journey around. There is no possibility of a quick return if the shielding proves insufficient. The cosmic ray environment of interstellar space is a permanent condition, and any vessel traveling through it must either carry shielding massive enough to reduce the dose to acceptable levels for the entire duration of the journey, or accept that its occupants, biological or electronic, will be steadily degraded by radiation damage the entire way. Electronics face their own version of this problem. Cosmic ray particles striking semiconductor components can cause single event upsets, where a charged particle deposits enough energy in a transistor to flip a memory bit from one state to another. In spacecraft electronics, this manifests as corrupted data, unexpected software behavior, and in severe cases, permanent damage to circuit components. Voyager 1's 2023 communication failure, the corrupted memory chip we discussed earlier, was likely caused by exactly this kind of event. For a probe designed in the 1970s with relatively simple radiation-hardened electronics, this was a recoverable problem. For a more complex interstellar vehicle carrying sophisticated navigation, life support, and communication systems, the chronic bombardment of galactic cosmic rays would represent a continuous reliability threat that compounds over time. Every year in interstellar space is another year of radiation exposure, another year of accumulated damage to circuits, sensors, structural materials, and any biological payload. But cosmic rays are not the only hazard embedded in the interstellar medium. The dust that makes up roughly 1% of the medium by mass presents a completely different category of danger, one that scales not with time, but with velocity. Interstellar dust grains are small, typically a fraction of a micrometer across, composed of silicates, carbon compounds, and in some cases, mantles of frozen volatiles. And the densities found in the general interstellar medium, these grains are incredibly sparse. You might encounter only a few per cubic kilometer in typical conditions, and in the low-density hot phase, even fewer. At the speeds of the Voyager spacecraft, 17 kilometers per second, collisions with individual dust grains are minor events. The kinetic energy involved is tiny, and the impacts produce negligible damage. But interstellar travel proposals do not envision traveling at 17 kilometers per second. The whole point of interstellar propulsion concepts is to reach a significant fraction of the speed of light. Breakthrough Starshot, one of the most concrete interstellar proposals currently under development, aims to accelerate gram-scale probes to 20% of the speed of light using ground-based laser arrays. At that velocity, 60,000 kilometers per second, the physics of dust grain collisions changes completely. Kinetic energy scales with the square of velocity. The dust grain that barely registers at 17 kilometers per second becomes a tiny bomb at 60,000 kilometers per second. A grain of interstellar dust weighing 1/billionth of a gram, striking a spacecraft at 20% of the speed of light, releases energy equivalent to roughly the detonation of a small explosive charge. The grain does not bounce off. It vaporizes on impact, along with a portion of the surface it strikes, creating a microscopic crater and a spray of plasma and debris. Individually, these impacts might be survivable for a robust spacecraft, but accumulated over years of travel through even the sparse general interstellar medium, the total number of impacts could amount to significant surface erosion, damage to optical systems, degradation of thermal shielding, and, in worst-case scenarios, penetration of critical structural components. For crewed vessels, which would necessarily be larger and more complex than gram-scale probes, the dust problem is even more acute. Larger cross-sectional areas intercept more grains. Longer journey times mean more total impacts. And the systems at risk windows, radiators, antenna surfaces, solar panels are precisely the ones that are most difficult to armor without adding prohibitive mass. Some proposals have suggested forward-mounted shields or deflector systems, but these add mass, complexity, and their own failure modes. The interstellar dust hazard is not a showstopper at low velocities, but it becomes increasingly serious as the desired speed increases, which creates an uncomfortable paradox. Faster travel reduces the time spent in the hostile interstellar environment, but increases the severity of dust collisions. Slower travel reduces collision energy and extends the total exposure time to cosmic radiation and every other cumulative hazard. There is no free variable. Every parameter trades off against another. The magnetic fields of the interstellar medium add another layer of physical reality that any interstellar traveler would have to contend with. The large-scale interstellar magnetic field, measuring roughly 3 to 5 microgauss in our region of the galaxy, is extraordinarily weak by any human standard. It is roughly 100,000 times weaker than Earth's surface magnetic field and billions of times weaker than the field in a medical MRI machine. But its weakness is compensated for by its scale. The interstellar magnetic field extends coherently across parsecs, which is to say, across distances of several light years. It threads through the entire interstellar medium, influencing the motion of every charged particle within it. For a spacecraft carrying no net electrical charge, the interstellar magnetic field is essentially irrelevant as a direct force. But for any propulsion or navigation concept that involves charged particles, plasma interactions, or electromagnetic systems, the background magnetic field becomes a factor that must be accounted for. The magnetic field also governs the propagation of cosmic rays through the medium, scattering them in complex ways that make the local cosmic ray environment variable and difficult to predict in detail. Regions of enhanced magnetic field strength can funnel or focus cosmic rays, creating localized zones of higher radiation intensity. Regions of weaker or more tangled fields may allow cosmic rays to diffuse more freely. The magnetic landscape of the interstellar medium is not uniform, and a traveler moving through it would encounter varying radiation conditions along the route, some better, some worse than the average. Interstellar magnetic fields also carry energy. The magnetic pressure in the interstellar medium is comparable to the thermal pressure of the gas and the pressure exerted by cosmic rays. All three contribute roughly equally to the total pressure balance that determines the structure and dynamics of the medium. This means the magnetic field is not a passive background feature. It actively participates in shaping the interstellar environment, influencing how gas clouds compress and fragment, how shock waves propagate, and how energy is transferred across vast distances. Any model of interstellar conditions that ignores magnetic fields is fundamentally incomplete. Then there is the thermal environment, which presents its own set of challenges. The interstellar medium exists at a wide range of temperatures, from around 10 Kelvin in the coldest molecular clouds to over 1 million Kelvin in the hot ionized phase. But these temperatures are misleading in a way that many people do not immediately grasp. Temperature, in the physics of gases, describes the average kinetic energy of the particles. In the hot ionized medium, individual ions are moving at very high speeds, corresponding to temperatures of 1 million degrees. But because the density is so incredibly low, the total thermal energy per unit volume is negligible. You could pass through million-degree interstellar plasma and not feel any heat at all. Because there are so few particles per cubic centimeter, and the total energy they can transfer to your spacecraft is vanishingly small. The real thermal problem in interstellar space is not overheating, it is heat loss. In the near vacuum of the interstellar medium, there is no convective or conductive heat transfer. The only way to shed or gain heat is through radiation. And in a region far from any star, the ambient radiation field is extremely faint. Any warm object in interstellar space, whether a spacecraft, a human body, or a piece of equipment, will slowly radiate its heat away into the surrounding emptiness. Without a star nearby to provide a continuous input of energy, maintaining thermal equilibrium requires an onboard power source. For the Voyager spacecraft, the radioisotope thermoelectric generators serve this dual purpose, generating both electricity and waste heat that keeps the spacecraft systems within operating temperature ranges. As those generators fade, the spacecraft will eventually cool to the ambient temperature of interstellar space, a few degrees above absolute zero. and all its systems will cease to function, even if the electronics were otherwise intact. For a crude interstellar vessel, thermal management would be a continuous engineering challenge for the entire duration of the journey. Reactors or other power sources would need to run without interruption to maintain habitable temperatures. Heat rejection systems, typically large radiator panels, would need to function perfectly for decades or centuries. Any failure in the thermal control system, even a partial failure, could cascade into habitability crises within hours or days, and there is no external source of warmth to fall back on, no star to orbit, no atmosphere to trap heat, just the cold, empty medium, patient and indifferent, drawing heat away from any warm body within it at the implacable rate dictated by the Stefan Boltzmann law. What makes all these hazards so insidious is that none of them, taken individually, is necessarily catastrophic over short time scales. A burst of cosmic radiation does not kill you instantly. A single dust grain impact does not destroy a spacecraft. One cold night does not freeze a habitat. The danger lies in accumulation, the relentless compounding of small insults over enormous spans of time and distance. Interstellar space does not attack. It erodes. It degrades. It slowly, patiently wears down every system, biological and mechanical, that dares to enter it. A journey of decades through this medium means decades of continuous cosmic ray bombardment, decades of thermal management without resupply, decades of micrometeorite impacts, decades of electronic degradation, decades of radiation damage to structural materials, seals, lubricants, and polymers. Nothing in the interstellar medium is aggressive on a human timescale. Everything in it is lethal on an interstellar one. The interstellar medium is sometimes described as the vacuum of space, but this phrase understates its character. A vacuum implies absence, passivity, the mere lack of something. The interstellar medium is not passive. It is an environment. It has properties, behaviors, and effects. It pushes back, not with walls or storms, but with physics. The cosmic rays do not stop. The cold does not relent. The distance does not shrink. The dust does not clear. Every light year of interstellar medium is functionally identical to the last, presenting the same suite of low-level hazards at the same low-level intensities. The only thing that changes is the total accumulated dose, the total accumulated damage, and the total accumulated wear. This is an environment that punishes duration, and duration is the one thing that interstellar travel demands in absolute abundance. All of this leads to an uncomfortable realization. The space between stars is not simply far. It is not simply empty. It is a physical environment that creates compounding, escalating obstacles for anything that attempts to cross it. Distance alone would be a challenge enough. But the interstellar medium adds a second layer of difficulty. It fills that distance with a thin, pervasive, inescapable medium that slowly damages everything passing through it. And there is no shortcut through it. The interstellar medium is everywhere between every star in the galaxy. It is the default condition of the Milky Way. And it is far more formidable than its near invisible thickness would suggest. What remains to be understood is what all of this means when you pull back from the details and look at the galaxy as a whole. Because when you combine the emptiness, the distance, the radiation, and the hostility into a single picture, what emerges is not merely a list of engineering challenges. What emerges is a barrier, perhaps the most fundamental barrier in the natural universe, and one that reshapes how we must think about our place within the galaxy. Step back from the details for a moment. Forget the individual numbers. Forget the density of one atom per cubic centimeter, the cosmic ray flux measurements, and the temperature phases of the interstellar gas. Instead, try to see the galaxy the way it actually is, not as a glittering pinwheel of light, but as a physical structure defined by what lies between the light. The Milky Way contains roughly 400 billion stars. That number sounds like abundance. It sounds like a galaxy overflowing with suns, packed wall to wall with stellar furnaces and their attendant planets and moons. 400 billion is a number so large that it overwhelms intuition. And the natural conclusion is that the galaxy must be a crowded, busy place. But that conclusion is catastrophically wrong, because those 400 billion stars are scattered across a disk, roughly 100,000 light years in diameter, and 1 to 2,000 light years thick. When you distribute even 400 billion objects across a volume that size, you get something that is overwhelmingly, crushingly empty. The galaxy is not a city of stars. It is a desert with stars in it. Consider the proportions. If you could somehow gather all 400 billion stars in the Milky Way and push them together into a single mass, that mass would occupy an almost vanishingly small fraction of the galaxy's total volume. The rest, the vast and overwhelming majority, is the interstellar medium, the thin, nearly empty, radiation-saturated, magnetically threaded void we have been describing throughout this story. Stars are bright. Stars are important. Stars are where energy is generated, where elements are forged, where planets form, and where life can emerge. But stars are not what the galaxy is made of. The galaxy is made of the space between them. By volume, the interstellar medium is the galaxy. The stars are the exceptions, tiny pockets of dense, luminous matter embedded in an ocean of near-nothingness that stretches in every direction for distances that light itself takes years to cross. This is the perspective shift that changes everything. When you look at the night sky, you see the exceptions. You see the rare concentrations of matter that manage to collapse under gravity, ignite nuclear fusion, and shine. You do not see the medium in which they float. You cannot see it. It is too thin to scatter light in any way your eyes can detect. It is too cold and too diffuse to glow visibly, except in a few specialized wavelengths that require telescopes tuned to radio or infrared frequencies. The interstellar medium is, for all practical purposes, invisible. And because it is invisible, we ignore it. We build our mental model of the galaxy around the things we can see, the stars. We treat the space between them as though it were simply distance, a number to be overcome by better technology. But it is not simply distance, it is an environment. And that environment has properties that make crossing it one of the most difficult challenges the laws of physics permit. Begin with energy. To move any object across interstellar distances within a time frame shorter than geological epochs, you need velocity. Not the kind of velocity that gets a satellite into orbit or sends a probe to Jupiter. You need a significant fraction of the speed of light. 10% of light speed, roughly 30,000 kilometers per second, is often cited as the minimum practical velocity for interstellar travel, because at that speed, the journey to the nearest star takes approximately 42 years. Slower than that, you are looking at centuries. Faster than that, and you begin to approach timescales that a single human generation might survive, but the energy costs become staggering. The kinetic energy of a moving object scales with the square of its velocity. This means that reaching 10% of the speed of light requires not 10% of the energy needed to reach light speed, but 1%, which sounds like a discount until you calculate the actual numbers. For a spacecraft with a mass of just 1,000 kilograms, roughly the mass of a small car, accelerating to 10% of the speed of light requires approximately 4.5 times 10 to the 17th joules of energy. That is 450 quadrillion joules. For comparison, the total energy output of all the power plants on Earth in an entire year is roughly 5.8 times 10 to the 20th joules. So, accelerating a single small car-sized object to the minimum practical interstellar speed would consume roughly 1,000th of the entire planet's annual energy production. And that is just the acceleration. Slowing down at the destination requires the same amount of energy again. A round trip doubles it further. Scaling up from a 1,000 kilogram probe to a crewed vessel carrying life support, shielding, supplies, and a crew multiplies the energy requirement by factors of thousands or millions. These are not engineering problems in the conventional sense. Engineering problems have solutions that can be reached through incremental improvements in technology. The energy requirements for interstellar travel are problems of physics, dictated by the mass-energy relationship and the scale of the distances involved. No amount of clever engineering changes the kinetic energy equation. You can choose different propulsion methods: nuclear pulse, fusion, antimatter, laser sail. But every method must ultimately provide the same total energy to achieve the same velocity. The interstellar medium does not create this energy barrier directly, but it is the reason the barrier exists. If stars were separated by millions of kilometers instead of trillions, the energy requirements would be trivial. It is the sheer extent of the interstellar void, light years of almost nothing, that forces the velocity requirements so high and the energy budget so far beyond current capability. Several propulsion concepts have been proposed that attempt to address this challenge, and each one reveals how formidable the barrier truly is. Nuclear pulse propulsion, the concept explored in Project Orion during the 1950s and 60s, envisioned detonating nuclear bombs behind a spacecraft to accelerate it. Theoretical studies suggested that an Orion-type vessel could reach perhaps 3 to 5% of the speed of light using fission bombs, or up to 8 to 10% using thermonuclear devices. These are impressive figures on paper, but they require a spacecraft massing hundreds of thousands of tons, carrying thousands of nuclear weapons, and they still produce a journey time to Alpha Centauri measured in decades to centuries. The concept was never tested at scale, and the political and practical obstacles to launching a nuclear bomb-powered spacecraft from Earth are considerable. Fusion propulsion offers theoretical improvements, using the energy released by fusing hydrogen or helium isotopes to generate thrust, but sustained, controlled fusion remains one of the great unsolved engineering challenges on Earth, let alone in a spacecraft. Even optimistic projections place practical fusion rockets decades in the future, and even if they are realized, the exhaust velocities they could achieve still limit interstellar cruise speeds to a few percent of light speed without extraordinary mass ratios. Breakthrough Starshot, the laser sail initiative backed by the late physicist Stephen Hawking and investor Yuri Milner, takes a radically different approach. Instead of carrying fuel, the spacecraft is a wafer-scale chip attached to a reflective sail, accelerated by a ground-based laser array to 20% of the speed of light. This concept sidesteps the fuel problem entirely by leaving the energy source on the ground. At 20% of light speed, the probe could reach Alpha Centauri in roughly 20 years. It is the most plausible near-term interstellar concept currently under serious study, and it elegantly solves the propulsion challenge for tiny, gram-scale payloads. But it solves nothing else. A gram-scale probe cannot carry meaningful shielding against cosmic rays or dust impacts at 20% of light speed. It cannot slow down at the destination. It cannot carry instruments much more sophisticated than a simple camera and a communication laser. And it does absolutely nothing for the problem of sending humans or even substantial robotic payloads across interstellar distances. Breakthrough Starshot demonstrates that it might be possible to fling a tiny chip across the interstellar medium. It does not demonstrate that the interstellar medium can be meaningfully crossed by anything resembling a mission of exploration, habitation, or survival. The most common response to the timescale problem of interstellar travel is a concept so deeply embedded in science fiction that many people treat it as an inevitability rather than a hypothesis. The generation ship. The idea is simple in principle. If no single human lifespan is long enough to complete the journey, build a vessel large enough to sustain a self-reproducing population across multiple generations. The crew that launches from the solar system is not the crew that arrives at the destination. Their great-great-great-grandchildren are. The generation ship accepts the interstellar medium's timescale and attempts to outlast it through biology rather than velocity. It is an elegant concept on a whiteboard. It is a nightmare in practice. Consider what a generation ship must actually achieve. It must sustain a human population in complete isolation for centuries, not in the sense that a submarine sustains a crew for months, with resupply missions scheduled and a return to port guaranteed. In the sense of total, irrevocable self-sufficiency, with zero external input for the entire duration of the journey, every calorie of food must be grown on board. Every litre of water must be recycled with near-perfect efficiency. Every cubic metre of breathable atmosphere must be maintained by closed-loop life support systems that cannot fail catastrophically, even once across a span of 300, 500, or 1,000 years. The ship is not a vehicle, it is a world. And it must function as a world with no margin for error over time, scales longer than any human civilization has ever remained stable. Now layer onto this the hazards of the interstellar medium. The cosmic ray flux outside the heliosphere bombards the vessel continuously for the entire journey. Over centuries, the cumulative radiation dose to the hull, the internal systems, and the population itself would be enormous. Shielding helps, but as we have discussed, shielding against galactic cosmic rays requires massive amounts of material, and every kilogram of shielding is a kilogram that must be accelerated to interstellar velocity, decelerated at the destination. A generation ship large enough to sustain a breeding population, estimates vary but typically start at several thousand people minimum to maintain genetic diversity, would need to be vastly larger and more massive than any structure humanity has ever built in space. The shielding requirements alone could dwarf the mass of the habitable volume. The structural integrity of such a vessel presents its own category of concern. Materials fatigue, seals degrade, metals suffer radiation embrittlement over decades of cosmic ray exposure, polymers break down, lubricants evaporate or decompose. Every mechanical system on board, every pump, every valve, every bearing, every seal in every airlock and pressure vessel must either last for centuries without maintenance or be replaceable using only the resources carried on board. There is no resupply. There are no spare parts from Earth. If a critical system fails in year 200 of a 500-year journey, the crew must repair it with whatever they have or die. The biological challenges are equally severe. A small, closed population living in a confined environment for centuries would face genetic bottleneck effects, inbreeding risks, and the psychological toll of multi-generational confinement. Social stability over centuries is not guaranteed. Human societies on Earth, with vastly greater resources and space, routinely undergo revolutions, collapses, famines, and civil conflicts over timescales of mere decades. A generation ship would need to maintain social cohesion, institutional knowledge, technical competence, and a shared sense of purpose across dozens of generations, all while confined to a structure that, however large, would still be incomprehensibly small compared to a planetary surface. The descendants who arrive at the destination would bear no personal connection to the decision to launch. They would have been born into the journey, raised within its walls, and asked to continue a mission conceived by ancestors they never knew. Whether such a population would choose to continue, or would fracture, rebel, or simply lose the technical capacity to operate the ship, is an open and deeply troubling question. The generation ship concept does not solve the problem of the interstellar medium. It absorbs the problem and attempts to endure it through brute persistence. And every hazard the medium presents, radiation, thermal management, dust erosion, material degradation, compounds across the centuries, such a ship would spend in transit. A generation ship is not a shortcut around the barrier. It is a decision to live inside the barrier for the entire crossing, accepting every insult it delivers for longer than most civilizations have ever lasted. There is one more dimension of the interstellar medium's barrier that we have not yet addressed, and it applies regardless of propulsion method or mission architecture. The interstellar medium is not uniform across the galaxy. Its density, temperature, radiation environment, and magnetic structure vary dramatically depending on where in the Milky Way you happen to be. And for the most part, the variations make things harder, not easier. The galaxy's spiral arms are regions of enhanced density where interstellar gas and dust concentrate compressed by density waves propagating through the galactic disk. Within the spiral arms, molecular clouds are more common, dust extinction is higher, and the interstellar medium is generally thicker and more structured. Supernova rates are also higher in spiral arms because the denser gas fuels more vigorous star formation, which produces more massive stars that die quickly and violently. This means the cosmic ray production rate is elevated within and near the spiral arms. A vessel passing through a spiral arm region would encounter both higher gas and dust densities and a more intense radiation environment compared to the interarm regions. Between the spiral arms, conditions are somewhat more favorable. Gas densities drop, dust is sparser, and the cosmic ray flux is modestly lower. The interarm regions are the closest thing the galaxy offers to clear corridors between stars, but more favorable is a relative term. The interarm interstellar medium is still a near vacuum, flooded with cosmic radiation. It is still light years wide. It is still devoid of resources and shelter. Calling it easier to cross than a spiral arm is like saying the deep ocean is easier to swim across than a hurricane. Technically true, practically meaningless. Near the galactic center, conditions become dramatically worse. The density of stars, gas, and dust increases sharply. The radiation environment intensifies. Supermassive stellar clusters, energetic nebulae, and the supermassive black hole Sagittarius A star and its associated accretion activity create a radiation-drenched environment that is hostile at scales far exceeding the general interstellar medium. The galactic center is not a place that any known or foreseeable technology can traverse safely, even in principle. In the galactic halo, above and below the plane of the disk, the interstellar medium thins further, but the distances between stars increase enormously. Halo stars are scattered across tens of thousands of light years with vast empty spaces between them. The medium is thinner, but the journey is longer, and the isolation is even more absolute. There is no direction you can travel in the Milky Way, where the interstellar medium becomes easy. There is no corridor, no gap, no convenient low-density tunnel connecting one star to another. The medium varies, but it never relents. Every route between any two stars in the galaxy passes through light years of structured, radiation-permeated, resource-free void. The barrier is not localized, it is galactic, it is everywhere. Every propulsion concept, no matter how advanced, runs into the same fundamental wall. The interstellar medium is too vast to cross quickly, too empty to harvest for resources along the way, too hostile to endure for extended periods without enormous investments in shielding, power, and life support. The barrier is not any single one of these factors. The barrier is all of them, simultaneously, compounding across distances that dwarf every other scale of human experience. And there is one more element of the barrier that is easy to overlook, because it is so absolute. Between one star and the next, there is nothing to stop at. On Earth, long journeys are punctuated by waypoints. You can rest, refuel, resupply, and repair at intervals along the route. Even in the age of exploration, when European sailors crossed the Atlantic or rounded the Cape of Good Hope, they could anchor at islands, take on fresh water, patch their hulls, and continue. The ocean was vast and dangerous, but it contained stopping points. The interstellar medium contains none. Between the Sun and Proxima Centauri, there are no planets, no moons, no asteroids of any useful size, no comets, no space stations, no fuel depots, no harbors. There is nothing. Just the medium itself, thin and hostile and featureless, extending without interruption for over 4 light years. A vessel that departs the solar system is committed. There is no turning back without expending the same energy again. There is no coasting into a convenient port. There is no rescue if something breaks. The journey is all or nothing, a crossing of a void that offers no shelter, no resources, and no second chances. This is why the concept of the heliosphere matters so deeply to the story of interstellar space. The heliosphere is not just a scientific curiosity or a boundary on a diagram. It is the last shelter. It is the final protective environment before the full severity of the interstellar medium takes hold. Inside the heliosphere, the solar wind provides a buffer against the worst of the galactic cosmic ray flux. Inside the heliosphere, the sun's magnetic field offers a measure of order and protection. Inside the heliosphere, there is a star nearby, providing energy, warmth, and a gravitational anchor that makes navigation and orbital mechanics possible. The moment you cross the heliopause, all of that ends. The cosmic ray flux jumps. The magnetic environment shifts to the interstellar field, organized on scales of light years rather than astronomical units. The nearest source of energy, the sun, begins to dwindle behind you, its light and warmth fading with the square of the distance until it is just another star in the sky, indistinguishable from the billions of others. Voyager 1 experienced this transition firsthand. Before the crossing, it existed within a bubble maintained by the sun. After the crossing, it existed in the interstellar medium, exposed to conditions that had been the default state of the galaxy for billions of years. The spacecraft did not notice, of course. It is a machine, built to endure a vacuum and radiation. But for any living thing, or any complex system dependent on long-term reliability, the transition from the heliosphere to the interstellar medium is a transition from a sheltered environment to an unsheltered one, and there is no equivalent shelter ahead. The next heliosphere, the astrosphere surrounding Proxima Centauri, does not begin until you are very close to that star, within perhaps 100 astronomical units of it. Between the edge of our heliosphere and the edge of the next, there is nothing but raw interstellar medium for the vast majority of the journey. When you hold all of this in your mind at once, the distance, the emptiness, the radiation, the dust, the cold, the absence of resources, the absence of shelter, the energy requirements, the timescales, the compounding degradation, what emerges is not a list of problems to be solved. What emerges is a picture of the galaxy itself. The Milky Way is a structure in which islands of warmth and light are separated by an ocean that is functionally uncrossable by any technology that currently exists or is likely to exist within the foreseeable future. The interstellar medium is that ocean, and it is not a passive obstacle. It is an active environment with properties specifically hostile to sustained crossing. This does not mean interstellar travel is impossible in principle. Physics does not forbid it. There is no law that prevents a sufficiently advanced civilization from building a vessel capable of enduring the interstellar medium for decades or centuries and arriving intact at another star. But the resources, the energy, the engineering tolerances, and the sheer duration required are so extreme that they place interstellar travel in a category fundamentally different from any other journey humanity has ever contemplated. Going to the moon took 3 days. Going to Mars might take 8 months. Going to the nearest star, at the fastest speeds any proposed technology can achieve, takes decades. And that is the nearest star. The overwhelming majority of the 400 billion stars in the galaxy are not 4 light years away. They are hundreds or thousands or tens of thousands of light years away, separated by proportionally vaster stretches of the same hostile medium. The galaxy is not small and is cluttered with stars. It is enormous and defined by the emptiness between them. This is why the galaxy is silent. This is why, despite hundreds of billions of stars and likely billions of planets, we detect no signals, no probes, no evidence of traffic between stellar systems. The interstellar medium is the answer. Not because other civilizations do not exist. We have no way of knowing them, but because the medium between the stars creates a barrier so formidable that crossing it may be something that very few civilizations ever achieve. And even those that do may find the cost so extreme that they do so only rarely, or on time scales so long that their efforts are invisible to us. The silence of the galaxy is not mysterious when you understand the medium. It is expected. The stars are isolated. They have always been isolated. The interstellar medium ensures it. And yet, in the midst of all this austerity, there is something else. Something that pushes back against the bleakness. Because the interstellar medium is not just a barrier. it is also a record. Every atom of gas drifting between the stars carries information about where it came from and what happened to it. The hydrogen that fills the interstellar void is primordial, forged in the first minutes after the Big Bang. The heavier elements mixed into it, the carbon, the oxygen, the iron, were synthesized inside stars that lived and died billions of years ago, their ashes scattered by supernova explosions into the medium where they now drift. The dust grains are built from those same stellar ashes, assembled atom by atom, floating down giants and exploding shells of supernova remnants. The cosmic rays that flood the medium are accelerated by the shock waves of those same explosions, carrying energy across the galaxy at nearly the speed of light. The interstellar medium is the galaxy's memory. It holds the chemical record of every generation of stars that has ever lived and died in the Milky Way. It contains the raw material from which the next generation of stars and planets will form. It connects the past and the future of the galaxy through a slow, continuous cycle of creation, destruction, and renewal that has been running for over 13 billion years. The same medium that isolates every star from every other star is also the medium that gave birth to all of them. Our own solar system condensed from a cloud of interstellar gas and dust, roughly 4.6 billion years ago. Every atom in the Earth, every molecule in your body, spent millions of years drifting through the interstellar medium before gravity gathered it into the collapsing cloud that became the Sun and its planets. You are made of interstellar material. The calcium in your bones was forged in a star that exploded before the Sun existed, and the atoms of that calcium drifted through the cold, thin, radiation-soaked space between the stars before finding their way into the nebula that became your world. The interstellar medium is not just the barrier that separates you from the rest of the galaxy. It is the substance from which you are made. There is a strange and disquieting beauty in this. The same environment that makes the galaxy unreachable is the environment that made you possible. The vast emptiness that isolates every star system from every other is also the vast reservoir from which every star system was born. The medium is simultaneously the galaxy's greatest obstacle and its most essential feature. Without it, there would be no barrier between the stars, but there would also be no stars to have barriers between. This is the terrifying truth about the space between stars. It is not that it is empty. Calling it empty misses the point entirely. It is that the space between stars is a physical environment, real, structured, and measurable, that creates one of the most formidable natural barriers in the known universe. The distance is the barrier. The emptiness is the barrier. The radiation is the barrier. The cold is the barrier. The absence of shelter is the barrier. The absence of resources is the barrier. Every one of these factors alone would be a serious obstacle. Together, reinforcing and compounding across light years of unbroken void, they form a wall that the galaxy has built around every single one of its 400 billion stars. We look up at the night sky and we see light, we see beauty, we see a possibility, and all of that is real. There are worlds out there, orbiting other suns, some of them perhaps teeming with life, perhaps home to civilizations that have looked back at our sun and wondered the same things we wonder about them. But between us and every one of those worlds lies the interstellar medium, not nothing, something vast, something hostile, something patient, something that does not care whether the medium will still be there in a billion years, thin and cold and saturated with cosmic rays, stretching between stars that have not yet been born. It is the permanent condition of the galaxy. It is the ocean we cannot sail. Perhaps that is the deepest lesson the interstellar medium has to teach us. Not that we are small, though we are. Not that the universe is indifferent, though it is. But that the galaxy is structured in a way that makes isolation the default state of every star, every planet, every civilization that has ever existed or ever will. The space between stars is not a problem to be solved. It is a feature of the cosmos. It is how the galaxy is built. The stars shine in solitude, separated by light years of structured emptiness, The emptiness is not a failure of the universe to fill itself. It is the architecture of the universe itself. We live on one small world orbiting one ordinary star, protected by a thin bubble of solar wind from the full severity of the medium that surrounds us. Beyond that bubble, in every direction, the interstellar void extends outward toward other stars we can see but cannot touch. We are not separated from the rest of the galaxy by nothing. We are separated by something, a medium so vast and so hostile that it may be the single greatest barrier nature has ever constructed. And in the face of that barrier, what we have accomplished is not insignificant. We have sent 2 small machines beyond the edge of our bubble and into the medium itself. We have measured its density, its temperature, its magnetic field, and its radiation. We have confirmed that it is real, that it is there. 2 tiny spacecraft, barely the size of a compact car, drifting at 17 kilometers per second through a void that stretches for light years in every direction, still sending data home through a signal so faint it carries less power than a refrigerator light bulb. That is what we have done so far. 2 probes in an ocean that spans 100,000 light years. It is almost nothing, and it is extraordinary.
When you think about it, really sad. When you think about it. Good morning, ladies and gentlemen. I'd like to show you something about how full of it people are and how fickle and disingenuous they are. Right, watch this. Right? At the end of this essay, what do we like this? I'd rather block. Oh, you didn't block. Commented here, Elizabeth. So you haven't blocked me. You'd rather block. So how about I block you instead and absolutely get wrecked? Yes, hello? Yes, and I'm going to have it with some rice crackers. Yes, please. Rice cakes. Thanks, Diana. Ladies. Yes, and I'm going to have it with some. Yes, and I'm going to have it Amazing, you like it, dear. Thank you. Amazing, you like it. Why, I wholeheartedly agree with you, my friend. I find you so good, so clever, so nicely. I even in a way. You know, could be. When you think about it. Anyway, and you didn't talk about it in the first place anyway. Anyway, we didn't about how you never thought of it in the first place. I mean, sometimes you just have to think about it. Anyway, no, I mean, anyway. Think about it now. You don't have in order to work something out. You have to think about it. Think about it. Anyway, if you're ever about to make a life-changing decision, yeah. Think about it. If you're ever about to make a life-changing decision, yeah. Think about it. If you're ever about to make a life, I might advise you, here's the best thing to do. Think about it. And you know, there's a right way. I want to ask you.
I feel so tired. What's going on? Why am I so tired? Why am I so fucking tired?
Grab my hand. There's a choice like your face. Wasn't ready for that. Try your weapon. Damn, disarmed. You're getting pretty quick and disarmed. Okay, I need to take your weapon. Hey, little bro. I'm my shit real. How this shit fake, little bro? Like real. Diamond shining. My shit glistening. I'm so little bro. I got diamonds in my veins. Fake. If your videos are stuck in our okay, go on. What did you say?
Okay, so I'm getting married to a man I met on Hinge. This is the first ever photo I saw of my future husband.
If you don't know this man, then you probably know someone like him. He's one of those people who can't take anything seriously.
Hello, Martin. Oh, I'm afraid I got some very bad news. Alright, let's see what you got. Okay, so these are lightsabers. Correct. So, where'd you get them? Estate sale. Estate sale. The previous owners no longer needed them. I've been a collector for many years of this great collection. Each lightsaber has a story, a history, there is a certain thrill in the acquisition. It is rewarding. Right, so this is a pretty big collection. What has you looking to sell them? I have a long condition, the separatist flag does not cover it. Oh, so silver collection. That's wrong, man. How much are you looking to get for them? 100,000 credits. Look, I'll give you $50. Whoa, our product is flying off the back of the shelf.
Karakere de metafasa kutoka Samsuri msuri like metakal.
What do you call half a rail? Fire. I'm here, Honeycomb. trees. Right. Well, you can grow sorts of things. Well, you can't grow concrete. You can. See you, Cameron. Cheerio. What are you glued to, Cameron?
We are looking for people to.
The longer a man stays without a relationship, the more dangerous he becomes. Who the fuck you calling Hulk Hogan? You know what? Blocking your ass. Blocking your ass. Who the fuck you? China just did it again and jumped in air and all of the beach ChatGPT.
Want to grow followers?
Back at customs, you don't need more time. Better priority one. Back at customs, Officers Roberts and Stewart continue their investigation. You don't need more. 1, 2, 3, 4, 5, 6. You see what I'm saying? Exactly that muscles. Amber. Amber. Don't you name that 8 syllables in some place? Does that look like an Amber? No, she put here with me as you check out.
All women say they want a good man until they actually meet one and realize they're not equipped to handle it.
This is one of the rare second half opportunities to try and test City. There's the shot from
My spies thought she could say anything until she messed with the wrong names. On an IG Live, she laughed and called Eminem overrated and said 50 Cent fell off after Pop.
You won't toss me off, but you wouldn't stick anything bloody close to box in your eyeballs. It's mental.
Why, where are the gloves? Where are the gloves then?
She's off the toilet with one hand and waking me off with the other. That's no skin off your nose. It's a fucking problem. Let's go in for treatment.
People say they want the truth.
private. Usually this is your take now. Join the TikTok private.
Selling your stuff.
Base the Libra City.
Sometimes a nicer
Today, my woman, if he shows up without asking, make sure he doesn't regret it. A man who picks up your calls right away, replies to your text in.
If you need work but can't leave home, I have an opportunity.
Someone matching your description as Joe Harris on a bike and call my colleague a wanker while I'm dealing with a serious incident. Have you used Legally?
perception changes. It's not cute.
I think the guidance smells good.
Why isn't everything laid out since 2000?
First, you suffer. Then you awaken. And only then do you begin to ascend. Strange, isn't it? That pain is not a punishment, but a summons. A knock on the inner door that says, wake up. Not to the world, but to yourself. You see, suffering shakes the foundation of who you think you are, so that you may discover who you truly are. And when that veil lifts, something extraordinary happens. You stop identifying with the wound and begin identifying with the witness. This is awakening. From here, ascension isn't about floating off into the clouds. It's about returning fully to the present, unburdened by the past, undistracted by illusion, unmoved by the ego's hunger for control. You begin to live as the soul, not the story, and you realize the pain didn't break you. It built the staircase. And now, you're rising.
You want fucking answers? I don't fucking got.
Because I don't fuck with nobody. Yeah, I don't
First, you suffer.
Oh man, why am I so tired? I'm fucking exhausted. Mm. 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 Oh, Jesus Christ. Mm. 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 I don't know. I'm fucking exhausted. How you doing, Casey? I'm fucking exhausted. I don't know why. Well, I guess it's all the walking. I don't know. Just so fucking tired. How about you? I woke up at like 8. I woke up at 10. I still feel knackered now. Yeah, woke up yourself, yeah. I don't know. I just feel so fucking shattered. Oh shit, I need to restart my live stream. It's gone long. Be back in a sec.